Hey everyone, I'm Morgan Willis, Senior Cloud Technologist at AWS, and I want to welcome you to this course. In this course, you will learn the key concepts behind cloud computing and explore AWS services using real-life examples, covering compute, networking, storage, databases, security, and more. This course is intended for people working in IT or IT-related fields, who have a general knowledge of IT topics, but have yet to learn much about the AWS Cloud. To kick off this course, we will cover the basics of what the cloud is, the benefits of the cloud, the AWS global infrastructure, and identity and access management. This will give you a solid foundation for learning the rest of the more technical topics contained in the course. Then we will focus on computing. And for this topic, we will dig into services like Amazon Elastic Compute Cloud, AWS Container Services like Amazon Elastic Container Service, and serverless compute options like AWS LAMBDA. Then we will discuss networking in AWS, using services like Amazon Virtual Private Cloud and other networking technologies used for creating, securing, and connecting to your own private network in AWS. For storage, we'll explore how and when to use Amazon S3, Amazon Elastic Block Store, and others. For databases, we will cover use cases around the many different database services AWS has to offer, but with a special focus on Amazon Relational Database Service and Amazon Dynamodb. Then finally, we will discuss monitoring and scaling your application. For that, we'll use Amazon Cloudwatch and Amazon EC2 auto-scaling alongside Elastic Load Balancing. We aren't going to focus on theory alone in this course. Instead, we will use a hands-on example through a cloud-based application that will build over the duration of the course piece by piece. The app we will build is an employee directory application that stores images and information about fictional employees in a company. There is no coding requirement for this course. For all of the exercises, you'll use the AWS Management Console within your own AWS account. You will also have access to the source code if you do want to explore further. This course includes written segments we refer to as readings or notes to reinforce ideas, dive deeper into topics, as well as provide background information on concepts that we perhaps did not cover in the videos. Because of this, I highly suggest that you take the time to complete all of the readings to get the full benefit of the course. So again, welcome. And as we say at Amazon, work hard, have fun, and make history. Hey everyone, my name is Morgan Willis, and I'm a Senior Cloud Technologist with AWS. What that means is I essentially get to build things, learn AWS, learn about new and different technologies, and then I get to share my knowledge with you all. I had a career in software development before I started working in training and certification at AWS, and I also have a degree in computer science. I really love technology and have been in the field for about over 10 years at this point, in roles that range from technical support to database administration to web application development. And while it's true that I do love technology, I also have a regular life outside of work where I like to hike in the beautiful sun, rain, sleet, or snow, and I also like to ski. Pretty much any outdoor activity, all seasons of the year, I am here for it. And this here is Meowsy. He's my trusted sidekick. He spends time with me while I type away in my computer, and I think he's picked up a thing or two over the years. His knowledge of AWS at this point is pretty great for a cat, I must say. I think I can even hear him sneaking on my computer at night to build his solutions on AWS. I have a feeling that his knowledge will come in handy in this course. More on that later.
Hey y'all, I'm Alana Layton, and I'm also a cloud technologist here at AWS. I've been with AWS for a while now in a variety of different roles, but I love being an instructor in courses like this one. It's so much fun to bring this content to life and get everyone learning. In my spare time, I love being outside, hanging out with my family, which includes my 4-year-old wonder dog named Kiwi. Speaking of Kiwi, sometimes I think she knows more about AWS than she lets on. Every once in a while, I notice her drawing AWS architectures in a journal, and I wonder where she learned all of this. She can't bring me the ball back when we play fetch, but she always wags her tail when I mention cloud computing. I think these reactions will come up every once in a while, so stay tuned for some of her helpful tips and tricks.
Hey there. I hope you're excited to learn about cloud computing on AWS. I'm excited too, so let's go ahead and hop in. This week, we are going to cover some of the foundational concepts that you'll need to know about when working with AWS. Working with AWS is part theory, part technical knowledge, part vocabulary, and lots of practice and experimentation. This first week is going to help you establish a little bit from each of those categories. You will learn the theory behind cloud computing and the benefits of the cloud. This will help you make informed decisions about the cloud from a high level and give you some reasoning around why and when to use the cloud. Then we will dive into the AWS global infrastructure, covering both regions and availability zones, followed by lessons on how to interact with AWS resources. This portion of the week is going to give you the technical knowledge and vocabulary that you need to create and discuss AWS architectures and properly understand AWS documentation and examples. A lot of what AWS offers can relate back to concepts used on traditional on-premises computing. And getting started with AWS means comparing those concepts to AWS concepts. After that, we will begin to discuss security and identity and access management. This is important to understand when you're getting started because as soon as you create an AWS account, you'll have some actionable knowledge on how to secure that account right from the start. Starting off secure is a good place to be. Throughout all of the topics this week and over the duration of the entire course, we will be using a sample employee directory web application to demonstrate how AWS services are used, and we'll be using the same application to give you some hands-on experience through exercises done in your own AWS account. Let's go ahead and take a look at the employee directory application. You can see I am already in the browser and I have this employee directory application up and running. And what I want to do now is show you the functionality of this app. This is a basic CRUD app or a create, read, update, delete application. This app keeps track of employees working within a company. So the first thing I want to do here is create a new employee. So to do that, I'm going to go ahead and click add. And then I'm going to give the employee a name. I'm just going to add myself here. My location is USA. My title is Senior Cloud Technologist. And then you have the ability to add some badges to employees. So I'm going to go ahead and select Mac user, frequent flyer, and coffee snob for myself. So I'll go ahead and click save. And that you can see now we have the saved banner popped up and we're back on the home page. And I actually forgot to add a picture for myself. So I'm going to go ahead and click on the employee. And then I'm going to click the edit button. And now I'm going to select a file here, which is just a picture of me. And then I'll click save. And now we can see that this employee has a photo. One more thing that this app can do is we can delete employees. So I'll go ahead and do that. And now you can see we have an empty directory again. And then one final thing to know about is we have something called an info page. And this gives some information about where the app is hosted, and this will come in handy later on in the course. So those are the features of the app from a user's perspective. Time to review now how we will build this app using AWS services. This application will be built in a private network using Amazon Virtual Private Cloud or VPC. We will host the application's backend code on Amazon Elastic Compute Cloud or EC2, which is a service that essentially offers virtual machines on AWS. So let's go ahead and add those servers to our diagram as well. The employee data will be stored in a database, which will also live inside of this network. And this will be hosted using a service called Amazon Relational Database Service, or RDS, or we might be hosting it on Amazon DynamoDB. So we'll add both of these to our diagram. The images for the employees will be stored using the object storage service Amazon Simple Storage Service, or what we call S3, which will allow the unlimited storage of any file type, like the images in this example. So these are the basic building blocks of our application, but we're not done yet. We are also going to use Amazon Cloudwatch for monitoring this solution. And we want to ensure that our application is scalable and fault tolerant. So I'm also going to add an elastic load balancer here, which will distribute the traffic across the EC2 instances. And we will also add Amazon EC2 auto scaling to this diagram. So that way our solution can scale out with demand and scale in when demand decreases. For security and identity, we will be using Amazon Identity and Access Management, or IAM. So you can see that there are a lot of different pieces on this diagram, but don't worry. We're going to build this app step by step using the AWS Management Console. We will add to this diagram, reference it, and change it throughout the course to meet our needs, and we're going to let it evolve as new ideas and techniques enter our world. One more thing to note about this course before I let you go. If you hear this noise, it means that you are going to be seeing one of our informational pop-ups on the screen, which convey extra information like word definitions, AWS best practices, tips and tricks, or general commentary written for you by our lively furry sidekicks, Meowsy and Kiwi. They know all the tips and are very helpful little friends to have around during this course. So that's it for now. Have fun and make sure you complete both exercises for this week so that you can start working hands-on with AWS.
For our employee directory application, we'll be using photos of each of our employees. We have to store them somewhere safe. Currently, the only copy of these photos are saved on my laptop right now. But if my laptop breaks, then what happens? No more photos. I want to make sure this doesn't happen, so I'm going to upload the photos to AWS to ensure that the copies exist even if my laptop is destroyed. This also allows me to access my photos from anywhere. My home, my phone, a plane, on a train, everywhere. When I store these photos in an AWS service, unbeknownst to me, I'm storing it in a data center somewhere, and servers inside that data center. But if a natural disaster happens, or a fire, or let's say a giant lizard comes out of nowhere, stomps on the data center, then what do we do? Luckily, AWS has planned for this event and many others, including natural disasters and other unavoidable accidents. The way they plan for it is through redundancy. AWS clusters data centers together around the world. So here, AWS might have a second data center connected to the first data center through redundant high-speed and low-latency links. That way, if the first data center goes down, the second data center is still up and running. This cluster of data centers is called an availability zone, or AZ. An AZ consists of one or more data centers with redundant power, networking, and connectivity. Unfortunately, sometimes natural disasters like hurricanes or giant lizards might also extend to impacting an entire AZ. But AWS has planned for that too, with redundancy. Like data centers, AWS also clusters AZs together and also connects them with redundant high-speed and low-latency links. A cluster of AZs is simply called a region. In AWS, you get to choose the location of your resources by picking a region. Regions are generally named by location, so you can easily tell where they are. For example, I could put our employee photos in a region in Northern Virginia called the Northern Virginia region. And remember, AWS is not going to name a region in Germany after Northern Virginia. As a basic rule, there are 4 aspects you need to consider when deciding which AWS region to use: compliance, latency, price, and service availability. Let's start with compliance. Before any other factors, you must first look at your compliance requirements. You might find that your application, company, or country that you live in requires you to handle your data and IT resources in a certain way. Do you have a requirement that your data must live in the UK boundaries? Then you should choose the London region, full stop. None of the rest of the factors even matter. Or if you operate in Canada, then you may be required to run inside the Canada Central Region. But if you don't have a compliance or regulatory control dictating your region, then you can look at the other factors. For example, our employee photos are not restricted by regulations, so I can continue looking at the next factor, which is latency. Latency is all about how close your IT resources are to your user base. If I want every employee around the world to be able to view the employee photos quickly, then I should place the infrastructure that hosts those photos close to my employees. We are all bound by the speed of light. Applied to your business, that means if all your users live in Oregon, then it makes sense to run your application in the Oregon region. You could run it in the Brazil region, but the latency from Oregon to Brazil might impact your users and create slower load times. But maybe I really want to run my application or store my employee photos in Brazil. One problem I might run into is the pricing, which is the next factor we'll talk about. The pricing can vary from region to region, so it may be that some regions, like the Sao Paulo region, are more expensive than others due to different tax structures. So even if I wanted to store my employee photos in Brazil, it might not make sense from the latency perspective or the pricing perspective. And then finally, the fourth factor you'll want to consider is the services you want to use. Often, when we create new services or new features in AWS, we don't roll out those services to every region we have right away. Meaning, if you want to begin using a new service on day one after it launches, then you'll want to make sure it operates in the region that you're looking at running your infrastructure in. To recap, regions, availability zones, and data centers exist in a redundant, nested sort of way. There are data centers inside availability zones and availability zones inside regions. And how do you choose a region? By looking at compliance, latency, pricing, and service availability. When you own the infrastructure, it's easy to understand how you interact with it, because you can see it, touch it, and work with it on every level. If I have a server that I've stood up in my closet, interacting with that server is easy because it's mine. I can touch it. When I remove the ability for me to touch and see something, when the infrastructure becomes virtual, the way that I work with that infrastructure has to change a bit. Instead of physically managing my infrastructure, I now logically manage it through the AWS Application Programming Interface, or API. So now when I create, delete, or change any AWS resource, whether it's a virtual server or a storage system for employee photos, I use API calls to AWS to do that. You can make these API calls in several ways, but the three main ways we're going to talk about are the AWS Management Console, the AWS Command Line Interface, and the AWS Software Development Kits, or SDKs. When people are first getting started with AWS, they'll typically use the AWS Management Console. This is a web-based console that you log into from your browser. The great thing about the console is that you can point and click. By simply clicking and following prompts, you can get started with some of the services without knowing anything about the service. With the console, there's no need to worry about scripting or finding the proper syntax. When you log into the console, the landing page will show you all of the possible services that you can work with, organizing them into relevant categories such as compute, databases, storage, and more. On the upper right-hand corner is where you select the region you want to work in. Changing the region directs the browser to make requests to that region, represented by a different URL. If I change the region to Paris, you're making requests to eu-west-3.console.aws.amazon.com, or the Paris region's web console. After you work with the console for a while, you may want to move away from the manual creation of resources. For example, in the console, you have to go through multiple screens to set configurations to create a virtual machine. And if I wanted to create a second virtual machine, I would need to go through that process all over again. While this is helpful, it also leaves room for human error. I might miss a checkbox or misspell something or even skip important settings by accident. So when you get more familiar with AWS, or if you're working in a production environment that requires a degree of risk management, you should move to a tool that enables you to script or program these API calls. One of these tools is called the AWS Command Line Interface, or CLI. You can download this tool and then use the terminal on your machine to create and configure AWS services. Instead of having a GUI to interact with like the console, you instead create commands using a defined AWS syntax. For example, if I wanted to launch a virtual machine, I first type in AWS, which is how we know we interact with the API. Then type in the service, in this case, which is EC2, the service that allows us to create and manage virtual machines, which we'll learn about later, and then the command that we want to perform in that service, and then any other configurations we want to set. One command versus multiple screens you have to click through in the console can help reduce accidental human errors. But that also means you have to work with defined syntax and get that syntax correct in order for your command to run successfully. So there is some upfront cost in just understanding how to form commands. But after a while, you can begin to script these commands out, making them repeatable, which will save you time in the long run. The other tool that allows you to interact with the AWS API programmatically is the AWS Software Development Kits, or SDKs. SDKs are created and maintained by AWS for the most popular programming languages, such as Python, Java, Node.js, .NET, Ruby, and more. This comes in handy when you want to integrate your application source code with AWS services. For example, our employee directory application runs using Python and Flask. If I wanted to store all the employee photos in an AWS storage service, I could use the Python SDK to write code to interact with the AWS storage service. The ability of managing AWS services from a place where you can run source code with conditions, loops, arrays, lists, and other programming elements provides a lot of power and creativity. All right, that wraps up this video. To recap, you have three main options to connect with AWS: the console, the CLI, and the SDKs. And this course will mainly be using the console to interact with the services. But feel free to challenge yourself by using the CLI if you're a bit more advanced.
It's time for your first hands-on exercise with AWS. Before you can begin building an AWS, you'll have to have an AWS account. So, for your first exercise, we ask that you create an account with AWS, verify the account, and then you'll set up some billing alerts. When you create an AWS account, you can then begin using the services. And a lot of different AWS services offer a free tier. The free tier varies from service to service, and all of the services that we chose for this course do have a free tier where you can use the resources for free with a limited capacity for a limited amount of time. If you have an existing AWS account that you are trying to use, there's a chance that you won't qualify for the free tier and would incur costs for the exercises that you complete in this course. So, for this first exercise, it's going to be pretty straightforward, and we are building up to the more complex tasks involved with hosting our employee directory application. You'll create and confirm your new AWS account, log into that account, and then you'll explore how to do some basic management tasks like where to find your account information, how to change regions using the management console, and setting up those billing alerts. You will set up a billing alert just in case you create a resource and then you forget to turn it off or delete it. You'll at least be notified when you've hit a certain threshold in the account for cost. So that's it for now. And make sure you utilize the discussion forums to ask questions if you get stuck or want more information on a specific topic. In order to begin using AWS effectively, it's important to understand how security works in the cloud. You already know that by using AWS, you won't be managing every single aspect of hosting your solutions. You'll rely on AWS to manage portions of your workload for you, taking care of that undifferentiated heavy lifting, like running the day-to-day of the operations of the data center and managing the various virtualization techniques employed to keep your AWS account isolated from, say, my AWS account. So the question is, who is ultimately responsible for security in AWS? Is it A, you, the customer, or B, AWS? The answer? Well, the correct answer is yes. Both you and AWS are responsible for securing your AWS environment. Let's explore this concept a little bit more. AWS follows something called the shared responsibility model. We don't view solutions built on AWS as one singular thing to be secured. We see it as a collection of parts that build on each other. AWS is responsible for the security of some aspects, and the others, you are responsible for their security. Together with both you and AWS following best practices, you have an environment that you can trust. Let's take a look at the shared responsibility model diagram. You can see we have the responsibility of security broken into two groupings, you and AWS each being responsible for different components. We describe AWS as being responsible for security of the cloud. For example, one piece of the puzzle AWS is responsible for is the AWS global infrastructure. And when I say global infrastructure, I mean the physical infrastructure that the cloud is running on. This is iron and concrete, buildings with fences protected by security guards, and various other security measures. It also includes the AWS global backbone, or the private fiber cables that connect each AWS region to each other. Managing the security of these pieces is all on AWS. You don't need to worry about that as far as security goes. Then there is the infrastructure and various software components that run AWS services. This includes compute, databases, storage, and networking. AWS is responsible for securing these services from the host operating system up through the virtualization layer. For example, let's say you want to host some virtual machines or VMs on the cloud. We primarily use the service Amazon EC2 for this use case. When you create a VM using EC2, AWS manages the physical host that the VM is placed on, as well as everything up through the hypervisor level. If the host operating system or the hypervisor needed to be patched or updated, that is the responsibility of AWS. This is good news for you as the customer, as it greatly reduces the operational overhead in running a scalable and elastic solution leveraging virtualization. We will talk more about EC2 and elastic solutions in upcoming lessons. For now, let's get back to the security aspect. So, if AWS manages the underlying hardware up through the virtualization layer, what are you responsible for? Well, you are responsible for security in the cloud. Similar to how a construction company builds a building, and it's on them to make sure that the building itself is stable and secure. Then you can rent an apartment in that building. It's up to you to lock the door to your apartment. Security of the building and security in the building are two different elements. For security in the cloud, the base layer is secured by AWS. It's up to you to lock the door. So for our EC2 example, you are responsible for tasks like patching the operating systems of your VMs, encrypting the data in transit and at rest, configuring firewalls, and controlling who has access to these resources, as well as controlling how much access they have. The main thing to understand is that you own your data in AWS. You are ultimately responsible for ensuring that your data is encrypted, secure, and has proper access controls in place. In many cases, AWS services offer native features that you can enable to achieve a secure solution. It's up to you to actually use them. In other cases, you may devise your own solutions to meet compliance and security standards for your own specific industry or use case. So that's the shared responsibility model at a high level. I do want you to keep something in mind though. There is some amount of nuance that you should understand as we move through this course regarding the shared responsibility model. Each AWS service is different and serves a different purpose. and a different use case. Therefore, the shared responsibility model can vary from service to service as well. This is a good thing, as you get to decide how to build your solutions on AWS. When you create an AWS account, you sign up with an email address and you create a password. The email address you sign up with becomes the root user of the AWS account. This root user has unrestricted access to everything in your account. We will discuss in a later lesson what types of users can be restricted and how to do that. But for now, I want you to understand that when you log into your AWS account using an email address and password, it means that you are logging in as the root user. This root user can do whatever they want in the account. It has all of the powers that can be had. And with great power comes great responsibility, or something like that. So, knowing that the root user is all-powerful, you should do everything you can to make sure that no one can gain access to this root user. Let's say there's a nefarious actor of sorts, and they have an evil plan to log into your AWS account with your root user, gaining access to all of the powers and permissions that can be had, and they go and delete all of your valuable data and AWS resources. And in its place, they spin up a lovely and expensive cryptocurrency mining operation, leaving you with the bill and none of your data as they walk away with a full crypto wallet. Sounds less than ideal. Well, how can you prevent that from happening? You could, of course, create a hard-to-crack password, and that will give you some level of security. This, however, is an example of single-factor authentication, where all someone needs to do is match the password with the email address and they're in. We recommend as a best practice that right after you create your AWS account, you enable multi-factor authentication, or MFA, for the root user. MFA introduces an additional unique piece of information that you need in order to gain access to the account. There are a variety of devices, virtual or physical, that generate one-time passwords that can be integrated with your AWS account for MFA. For example, I personally use a virtual MFA device that's an app on my phone. This app produces a string of numbers for one-time use that I type into the console after I log in using my email address and password. Even if someone had guessed my password, they cannot gain access to the account without the numbers generated by the virtual MFA device. No matter what type of MFA device you choose to use, and I will include a link in the notes for supported devices, the most important thing is that you are using MFA at least on the root user. That way, even if someone, the nefarious actor, cracks your password, they still cannot gain access to your account, and all thanks to MFA. On top of enabling MFA for the root user, we strongly recommend that you do not use the root user for your everyday tasks, even the administrative ones. There are really only a few actions that require root user access. Coming up, you'll learn how to create an IAM user and then use that to log in to your AWS account instead of using the root user. Let's take a look at the application we are going to be building throughout this course. We've already gone over the design of this application, and what I want to do is focus now on the access control. There are multiple places on this diagram where we can identify the need for access control and credential management. The first being that we need to manage how users log in and use the employee directory application. We could require that people have a valid credential, like a username and password to log into the app. That is access management on the application level. Then there's the fact that we know the code running the employee directory application is running on a virtual machine being hosted by the service Amazon EC2. That code will need to make API calls to the object storage service Amazon S3 in order to read and write data like the images for the employees. Well, here's the thing. Just because both Amazon EC2 and Amazon S3 have existing resources in an account, it doesn't mean that the API calls made from the code running on the EC2 instance to S3 are going to be automatically allowed to be made. In fact, All API calls in AWS must be both signed and authenticated in order to be allowed, no matter if the resources live in the same account or not. The application code running on Amazon EC2 needs access to credentials to make the signed API call to Amazon S3. So that's another place with a need for credential and access management. Now, let's take this a step further. How are you going to build out this architecture? Well, you'll need access to an AWS account through the use of a login. Your identity within this AWS account will need permissions to be able to do things like create this network, launch EC2 instances, and create the resources that host and run this solution in AWS. Yet another place you need credentials. The root user, which you have already learned about in a previous lesson, has these permissions. But you don't want to be using the root user to administer your AWS resources. And also, let's assume that you won't be the only one working on building out this application. It's more likely that within one AWS account, there will be many people who need access to build and support your solutions. You'll have different groups of people responsible for different parts of the architecture. The people who would write and deploy the code might be software developers, whereas the people who would be responsible for making changes to, say, the network would be a totally different group of people. You wouldn't and shouldn't give everyone who needs access to the AWS account the root user credentials to log in. You instead would have unique credentials for each person logging in. This is where the service AWS Identity and Access Management comes in. We identified 3 places that we will need access and credential management for this solution. AWS Identity and Access Management, or what we call IAM, can help take care of these 2 spots on the diagram. AWS IAM manages the login credentials and permissions to the AWS account itself. And it also can manage credentials used to sign API calls made to AWS services. IAM would not, however, be responsible for the application-level access management. The code running on this instance would use separate appropriate mechanisms for authenticating users into the application itself, not IAM. All right, so let's start with the AWS account level. IAM allows you to create users, and each individual person who needs access to your AWS account would have their own unique IAM user. Creating users for everyone who needs access to the account takes care of the authentication piece. Authentication being verifying if someone is who they say they are because they logged in with the proper credentials. Now it's time to introduce authorization. Authorization is this. Let's say you've logged in and you are who you say you are. You've been authenticated. Now, you want to create and manage AWS resources, like create an Amazon EC2 instance, for example. So sure, you've logged in, but do you have the correct permissions to be able to complete that action? The idea that your permissions control what you can or cannot do is authorization. Are you authorized to launch an EC2 instance? IAM users take care of the authentication. And to take care of authorization, you can attach an IAM policy to a user in order to grant or deny permissions to take specific actions within an AWS account. And keep in mind, when I say action here, I'm referring to an AWS API call. Everything in AWS is an API call. IAM policies are JSON-based documents. Let's take a look at an example. This IAM policy document contains permissions that allow the identity to which it's attached to perform any EC2-related action. The structure of an IAM policy has an effect, which is either allow or deny. An action, which is the AWS API call. In this case, we have EC2:*, which that would include all of the EC2-related actions. You can restrict this to be specific API calls. For example, I can restrict this action to be just run instances. And then any user with this policy attached would be able to run EC2 instances, but perform no other EC2 related tasks. IAM lets you get very granular with your permissions in that way. We see the resource, which allows you to restrict which AWS resources the actions are allowed to be performed against. You can also include conditions in your policies that can further restrict actions. IAM policies can also be attached to groups. IAM groups are very simply just groupings of IAM users. You can attach a policy to a specific user or to a group. When you attach a policy to a group, any users that are a part of that group would inherit the permissions. We recommend that as a best practice, you organize users into groups and assign permissions to groups instead of individual users where possible. This makes it easier to manage when people change job roles, or maybe multiple users need permissions to be applied or revoked. Another best practice to follow is that we recommend when you create your AWS account, you first set up MFA for the root user. Then create an IAM user with administrator permissions. Log out of the root user and then log in with the new IAM user that you just created. From there, you can use this user to create the IAM groups, users, and policies for the rest of the people using this AWS account. The reason we suggest that you do this is because you cannot apply a policy to the root user, but you can to an IAM user. Now, I've told you about IAM users, groups, and policies. So we addressed this part of access management that we needed for our application. But what about this part? The EC2 instance needs credentials to be able to make the signed API call to S3 for reading and writing employee images. Am I suggesting that you make an IAM user with a username and password for the application running on EC2 to use? No, I am not. This is where role-based access comes into picture. Coming up next, we will learn about the temporary access that IAM roles provide and how it can be applied in this use case. Stay tuned. In a previous lesson, you learned about IAM users, groups, and policies. Policies can be applied to AWS identities, like users and groups, to assign permissions. They also, however, can be applied to another AWS identity, IAM roles. An IAM role is an identity that can be assumed by someone or something who needs temporary access to AWS credentials. Let's dive into what exactly I mean when I say AWS credentials. Most AWS API calls that are made must be signed and authenticated. But how does that process work? Well, from a high level, when you send an HTTP request to AWS, you must sign the request. This signing process allows AWS to verify your identity when a request is made, and it's run through various security processes to ensure that a request is legit. IAM users have associated credentials like an access key ID and secret access key that are used to sign requests. However, with regards to our architecture, the code running on the EC2 instance needs to sign the request sent to S3 for the employee photos. I already told you that I do not intend for you to create an IAM user with credentials to be used by this app. I also do not intend for you to hard code credentials into this app at any point in time. So, how will the application gain access to the needed AWS Access Key ID and AWS Secret Access Key to sign the API calls? The answer? IAM roles. IAM roles are identities in AWS that, like an IAM user, also have associated AWS credentials used to sign requests. However, IAM users have usernames and passwords as well as static credentials like the access key and secret access key. Whereas IAM roles do not have any login credentials like a username and password, and the credentials used to sign requests are programmatically acquired, temporary in nature, and they are automatically rotated. In our example, the EC2 instance will be assigned an IAM role whenever you launch it. This role can then be assumed by the application running on the virtual machine to gain access to the temporary credentials needed to sign the AWS API calls being made. A role can be assumed by many different identities, and they have many use cases. The important thing to know about roles is that the credentials that they provide expire, and roles are assumed programmatically. To get an idea of this, let's go ahead and create a role using the AWS Management Console. I'm already logged into my AWS account, and now what I'm going to do is navigate to the IAM service by just typing IAM in the toolbar here and selecting this. And now what I want to do is create the role that our AWS EC2 instance is going to use for the employee directory application. So to do that, I'm going to click on roles over here in the left-hand side, and then I'm going to click create role. From here, you have to select what trusted entity is allowed to assume the role, because again, remember, these roles are being assumed programmatically. So we are going to go ahead and select EC2 as the trusted entity to assume this role, and then we will click next. And now we can attach permissions to this role. On this screen, you can look through the AWS managed policies, which are policies that are created and maintained by AWS, or you can create your own policy where you can get really specific and granular with the types of permissions that you want to give to this role. For this specific example, I need this application to be able to read and write to Amazon S3, and we're also going to need to give this application access to Amazon Dynamodb, which is a database. So what I'm going to do is I'm going to use the AWS managed policies here. So I'm going to type in S3, and then I'm going to select the Amazon S3 full access role. And if we open this up, you can see what the policy looks like. This policy here has one statement where we are allowing the action of S3:*, so that is all S3 actions, against all S3 resources. So this is a very broadly scoped permission. For our simple proof of concept, we're going to use this. In real life, you probably want to create custom policies that really narrow down the scope of those permissions. But I'm going to go ahead and select S3 full access. And then I'm also going to look up Dynamodb, and we will select Amazon Dynamodb full access. Next, we will click tags. And from here, we can add tags. Tags are just user-defined key value pairs that are associated with a resource. These can come in handy for billing and resource management and all sorts of things. So we are going to go ahead and give this a name, and this will just be employee directory app. That's the value of our tag. Next, we will click review, and now we will give this role a name, the name being EC2 S3 Dynamodb full access. And now we can click create role, and we can see that that role has now been created. The role that we just created is going to be used in future lessons and demos when we build out our employee directory application. It's very common for roles to be used for access between different AWS services. Just because two resources exist in the same AWS account, it doesn't mean that they can send API calls to each other. If one AWS service needs to send an API call to another AWS service, it will most likely use role-based access, where the AWS service assumes a role, gains access to the temporary credentials, and then sends the API call to the other AWS service, who then verifies the request. Another identity that can assume an IAM role to gain access to AWS is external identity providers. For example, let's say you have a business that employs 5,000 technical employees, and they all need access to an AWS account. You already have an identity provider in place that allows these employees to log into their laptops and access various corporate resources. Should you also now go create 5,000 IAM users for these employees to access AWS? Well, you can, but that doesn't sound very efficient. You can leverage IAM roles to grant access to existing identities from your enterprise user directory. These are known as federated users. AWS assigns a role to a federated user when access is requested through an identity provider. We also have AWS services that can make this process a little bit easier, such as AWS Single Sign-On. These are a couple of examples of role-based access in AWS. and this is just the introduction. Check out the class readings for more information, and don't worry if you don't quite grasp this concept yet, as we will use roles in our demos throughout this entire course, and you will also gain experience using IAM roles in your own account through our hands-on exercises. Let's keep the momentum going, shall we? Time for another hands-on exercise. This time, since you have already created your AWS account and you've learned about some of the best practices for securing AWS accounts, let's put those best practices into practice. First, you'll log into your AWS account with the root user and you'll enable multi-factor authentication. Next, you'll find the root access keys, which provide unlimited access to your AWS resources. And as stated in a previous lesson, it's not recommended to use these unrestricted keys in normal situations. So you're going to go ahead and delete yours from the account. Then, once that is taken care of, you'll create an IAM user with administrator privileges. Then you'll log out of the root user and log in with the new IAM user. This user will be used to manage your AWS account from this point forward, unless the root user is specifically needed, which again will not be very often. The first task you'll complete with this new IAM user is you'll create an IAM role with more limited privileges that will come in handy in future exercises. Have fun. All right, you've learned some AWS vocabulary, some of the concepts behind cloud computing, as well as some specifics around cloud identity and access management. As a refresher, let's take a look at the architecture diagram we'll be building out. You can see here it's fairly complicated at a glance. There are many different services working together to host this solution, and to get this entire thing built out will take some time and understanding. You'll get the opportunity to build out each individual piece in your own account. What I want to do now is show you how we are going to host our employee directory application using a service called Amazon EC2, which I have mentioned briefly in previous videos. I find that the best way for me to explain to you how these services work is just to show you how they work. So what we are going to do is we are going to call Alana in to launch an Amazon EC2 instance and host the employee directory application using the defaults provided by AWS. AWS provides you with something called the default VPC, which is a private network for your AWS resources. Every EC2 instance you launch using AWS must live inside of a network. So, in order to complete this demo with the limited information that we've shown you about AWS services, we will be using the default network provided by AWS, and we will accept most of the default values for launching an EC2 instance. Let's call in Alana to help us out. Hey Alana, where you at?
Oh, hey Morgan. Is it time to launch our first EC2 instance?
It is. We will be using the default VPC to launch this first instance, and we will configure the bare minimum to get our application up and running. Sound good?
Yep, I got it. Let's get started. I'm already in the AWS Management Console, and I will go ahead and navigate to the service Amazon EC2. As Morgan already mentioned, Amazon EC2 is a compute service that allows you to host virtual machines. You'll learn a lot about this topic coming up soon, but for now, we are going to simply create an EC2 instance to try to help you wrap your mind around using AWS services on demand. From here, we will go ahead and launch a new EC2 instance, and an instance is just what we call one single virtual machine. Now we have to select the configurations for this EC2 instance. You will go over these configurations in detail later. But for now, we will select the free tier eligible options using a Linux AMI, and then also a T2 micro instance type, and then click Next. Then we will select the network we want the instance to be launched into, and as we discussed earlier, we'll be using the default VPC. The default VPC has configurations in place that make this experimentation process a lot easier when you're first getting started with AWS. If we scroll down, we will also select the role that will be used by the application. though this won't come into play until later when we have our S3 bucket created. Then we are going to accept the defaults and scroll down some more. In this box here, we're going to paste in a script. This script is going to run when the instance boots up. The script will download the source code to the app, start the web server, and kick off the application code so it's ready to start handling requests. While you could have launched the instance, then connected to it via SSH, configured and started your application manually, we have decided to use a script to automate this process on launch. This is called user data for future reference. Then we will click Next. Through the defaults for storage, click Next again. And then here we're going to go ahead and give our instance a name. So I'm going to click Add Tag, put name for the key, and then the value will be employee-web app, and then click Next. Then we will create a new security group, which is an instance-level firewall that will allow HTTP and HTTPS traffic to reach the instance. We will cover this in detail in future lessons. Then we will go ahead and click Review and Launch. Click Launch again, acknowledge the key pair, and click Launch. Now, it can take a few minutes for the instance to boot up, so let's go ahead and wait for that. And now it's up and running. To access the instance, I first select it, then I'll bring up this tab here, and then I'll go ahead and copy the public IP address. All right, now we can paste it into a new tab. And there you go, it's up. Morgan, what do you think?
That looks good. It's exactly what I would expect at this point. Because there is no data being served from a database, I expect to just see the home page with no info. So that's great. Thank you, Elena, for walking us through that. Coming up next week, we will discuss the specifics of not only EC2, but also networking on AWS, and you'll understand how everything we just kind of glossed over actually works. You'll also have a chance to build it out yourself in your own account, so stay tuned.
Hey everyone, and welcome to week 2. Last week was all about the setup, making sure you understand AWS, the global infrastructure, as well as setting up an account and providing yourself the right level of permissions. But you may also remember that we ended last week by launching an EC2 instance to host our application. An EC2 instance is simply just a form of compute, meaning it gives our application power in the form of CPU, memory, and networking capacity so that we can process our users' requests. This concept of compute leads us into this week, where we discuss your compute options on AWS. Of course, you've already seen one of those options, EC2, but we'll also discuss other common solutions, such as container services, like Amazon Elastic Container Service, or ECS, and Amazon Elastic Kubernetes Service, or EKS, as well as serverless options like AWS LAMBDA. By the end of the week, you'll not only understand each of these services, but you'll also be able to compare them to one another. That way, you'll know when and how to apply each service to different use cases. You'll also get an opportunity to be hands-on with Amazon EC2. In the middle of the week, you'll complete an exercise to launch an EC2 instance to host the employee directory application. But as you imagine, we can't just launch the EC2 instance into space. We have to put it somewhere. And where do we put it? In a network that we'll need to customize for our application. Every EC2 instance needs to exist inside of a network, and on AWS, these networks are called VPCs. At the end of this week, you'll be testing your knowledge on networks in a hands-on exercise where you build a VPC. You'll then launch another EC2 instance in the VPC to host your application. But rest assured, this won't be too hard. You'll have everything you need to complete this. Remember that if you get stuck at any point, you can always ask questions in the class discussion forums. Our team will be monitoring those and getting you answers shortly. Also, make sure you're checking out the readings that follow the videos. There's additional information in those readings that you won't see in the videos, like use cases, features we didn't have time to cover, and more. All right, I think it's time for us to get started. Enjoy the week, and I will see you soon.
Let's talk about compute. Every business needs raw compute capacity to run applications. These applications could be web servers, batch jobs, databases, HR software, machine learning, or just about whatever you can think of. The time, money, and effort it takes to get up and running with on-premises computing resources is fairly high. When you own your own fleet of physical servers, you first have to do a bunch of research to see what types of servers you want to buy and how many you need to buy. Then you purchase that hardware up front. You'll wait multiple weeks or months for the servers to be delivered. Then you take them to a data center space that you either rent or own, and you install them, rack them and stack them, and wire them all up. Then you make sure that the servers are secured, powered up, and ready to be used. Only then can you begin to host your applications on top of those servers. And the worst part is, once you buy these servers, you are stuck with them, whether you use them or not. It's not easy to just suddenly provision more physical compute capacity when you need it. And it's even harder to get your money back on servers that you no longer need. Impossible to get the time back. Following a compute as a service model is much easier to get started and easier to support operations over time. AWS took care of the hard part for you already as far as getting started goes. AWS already built and secured the data centers. AWS has already bought the servers, racked them and stacked them, and they are already online, ready to be used. In a previous lesson, we showed you how to launch the employee directory application with Amazon EC2. We didn't really talk about the details, how EC2 works, what configurations exist for it, and we definitely didn't discuss any other compute options that exist on AWS. AWS has different services for different use cases. And Amazon EC2 is one of the AWS services that is important to understand. We will be spending most of our time in these upcoming lessons exploring EC2. That being said, though virtual machines like EC2 are great, there are other compute services out there too, like container services and serverless compute. You'll learn about these other compute options and their use cases. Don't always assume that VMs are the default and correct answer. Sometimes it makes sense to architect applications for serverless compute or containers from the start, depending on what you are building for and what you are optimizing for. EC2 instances give you a lot of flexibility and control in the cloud, and you can configure them to meet your needs. You can provision one or many EC2 instances easily, and at the end of the billing cycle, you only pay for what you use, either per second or per hour, depending on the type of instance. When you no longer need an instance, you can terminate or stop the instance and you will stop incurring charges. Not all servers are the same, and you are probably looking to run a specific type of operating system on your EC2 instance. AWS supports a range of operating systems, including Linux, macOS, Ubuntu, Windows, and more. To select the operating system for your server, you must choose an Amazon machine image or an AMI. The AMI contains information about how you want your instance to be configured, including the operating system, possible applications to be pre-installed on that instance upon launch, and other configurations. You can launch one or many instances from a single AMI, which would create multiple instances that all have the same configurations. Some AMIs are provided by AWS, whereas others are provided by the community and can be found using the AWS Marketplace. For example, Amazon Linux 2 is the AMI we selected when we launched our employee directory application. This AMI is provided by AWS, and it is essentially a pre-built EC2 optimized Linux image that has long-term support provided by AWS. Beyond the properties determined by the AMI, you can also configure the instance type and size, which correspond to the amount of compute, memory, and network capabilities available per instance. Different applications have different hardware requirements, and choosing the instance type for your application gives you the ability to pick the hardware that it runs on. It's also really nice that you have a wide variety of choices for instance type, as it's hard to achieve the same level of variety with on-premises resources. The instance type you choose are grouped for use cases like compute optimized, memory optimized, storage optimized, and more. There is a list of instance types that you can find in AWS documentation, and you can expect that this page will be updated regularly as new instance types are released. For example, the G instance family are optimized for graphics-intensive applications, which would work best for use cases like 3D visualizations or video encoding. Whereas the M5 general purpose EC2 instance family provides a balance of resources and are great for applications that use these resources in equal proportions, like web servers, our employee directory application, for example, or things like code repositories. When you are launching an EC2 instance, you will see something like this when selecting an instance type and size. The T3 or A1 is the instance family that determines the blend of the hardware capabilities. Then there's the dot. Then there's the size, like small, medium, large. It goes down to nano and up to many, many extra large sizes, depending on the instance type. The great thing about this type of selection existing right at your fingertips is that you are no longer locked into hardware decisions up front. You can choose an initial EC2 instance type, evaluate its performance for your specific use case, and then later you can change to a different type that is better suited for your application. EC2 is also resizable with a few clicks in the console or can be done programmatically through an API call. All of these configurations being available to you via API enables you to embrace change over time easily as your workloads mature and change. So, all right, virtual machines are cool and totally not new. So how does this impact your business? The important thing is this: the flexible and low-cost nature of EC2 instances, as well as the ease of provisioning servers, allows for programmers and businesses to innovate more quickly by spinning up servers for a short amount of time to run experiments and find optimal configurations for your applications. EC2 offers a wide variety of hardware options to choose from, so you can optimize for your solutions by selecting the right EC2 instance type for your application, and then you can optimize even further by right-sizing the resource, or selecting an instance size that is appropriate for your application and not over-provisioning like is often done on premises. This type of optimization is hard to achieve on your own because with traditional on-premises deployments, you are working with hardware constraints that simply don't exist in the same way in the cloud. The ability to adapt changes and choose really specific configurations for your virtual machines all through a couple of API calls is very powerful. And really, EC2 is just the beginning of the story. One of the main reasons why EC2 provides so much value is the fact that you can provision new EC2 instances on demand, and just as easily, you can get rid of instances that you no longer need. In most cases, you only get charged for instances that are currently running. EC2 allows you to stop and start instances at will, which enables you to treat your fleet of EC2 instances as elastic, scaling them in or out. Then, at the end of the billing cycle, you only pay for what you use. We are building up to the idea of scaling your fleet of EC2 instances in and out to serve demand. But before we get there, it's important to understand some of the basics of EC2. Let's talk about the EC2 lifecycle. An Amazon EC2 instance transitions through different states from the moment you launch it through to its termination. You launch an EC2 instance from an AMI, as you learned in a previous lesson. And once the EC2 instance is launched, it enters a pending state. This state is essentially your VM booting up. Once the instance is ready for use, it enters the running state. In the running state, you will be charged for the EC2 instance. From running, you have a couple of different options. You can reboot the instance, which is similar to rebooting, say, your laptop. It turns off and then it turns back on. Pretty straightforward. You also can choose to stop your instance. it will enter a stopping phase, and then it will enter the stopped phase. Stopping an instance is like powering down your laptop. You can always turn it back on, and it will go through the usual boot sequence, moving through the pending state and then back to the running state. Another option, which is similar to stop, is stop hibernate. This also enters the stopping phase and then the stopped phase. You can compare this to how you lock your laptop and just shut the lid, but when you open it back up, everything is still in place exactly where you left it. There's no boot sequence required. You are back up and running after a couple of seconds of the computer waking up. Since the state of the machine was written to memory when you stopped it, the state of the machine can be drawn from memory and put back into place. Then you're back up and running. Now, the last option depicted here is the terminate option. When you terminate an instance, it enters the shutting down phase and then the terminated phase. Terminating an EC2 instance is like taking your laptop out for a long boat ride on the coast and then throwing it in the ocean, getting rid of it forever. It's now lost to the great blue sea. There is no hope in finding your laptop on a shipwrecked island one day, having been saved after spelling SOS in the sand. Anyways, I hope any data that you had stored on an EC2 instance that you did terminate, you had backed up somewhere, because whenever you do terminate an instance, anything on that instance goes with it. That being said, there is a feature called termination protection that you can enable if you're worried about instances being terminated accidentally. You also will learn about persistent storage in EC2 in future lessons. So don't fret. We will show you ways where you can make sure that any data that you have sticks around, even if the EC2 instance doesn't. So that is the EC2 instance lifecycle. It's definitely a good idea to remember how all of this works if you plan on using EC2 to host your applications. And don't think of terminating instances as a bad thing. If your EC2 instance is having technical trouble for one reason or another, or maybe it needs an update or a patch, instead of logging into the instance to fix it or install software, you can launch a new one with the new changes in place, and then you could terminate the old instance, having the new one take its place. You, of course, can do in-place updates as well, but just know that you have the option to decide how to handle these sorts of tasks. You can also launch or terminate EC2 instances to meet demand. So as demand for your application increases, you can launch more instances, and then as it decreases, you can terminate instances. This keeps your EC2 instance fleet in line with demand. So again, terminating an instance isn't a bad thing, and it should not be feared. Now, let's discuss the cost aspect of this. You only get charged for an EC2 instance if you are in the running state or if you are in the stopping state preparing to hibernate. This means that you can stop instances when they aren't in use. Say, if you have applications that are only really used during the work week, run them when your employees are clocked in, and then stop them when they aren't. Remember, you can always start from a stopped state, allowing them to resume working when necessary. In this next exercise, you are going to put all that new EC2 knowledge to good use. You're going to launch a new Amazon EC2 instance into your default VPC, just as we did for our demo in a previous lesson. You'll select an AMI, an instance type and size, configure the instance, and then you'll launch it. Part of the configuration will be to paste a user data script into the advanced configurations. This user data script is a script that runs when an EC2 instance is booted up for the first time. This is most commonly used to download and configure any software packages or dependencies that are needed to run the application on the instance. It's good for you to pay close attention to these sorts of details as you move through the exercise, especially if you plan on using EC2 outside of a classroom environment. Once your EC2 instance is booted up, you'll be able to send a request to the employee directory application and view its response in the browser. This EC2 instance will not yet be connected to any backend database to store employee information. So the expected result for this is simply to load the home page with no data displayed. If you are having trouble, please write your questions in the discussion forums. I also encourage you to help others troubleshoot their technical issues in the discussion forums if you were successful yourself. Once you are done verifying your EC2 instance is up and running and configured correctly, you will then stop the instance so that you can view the state change. Then finally, you'll terminate the instance as some cleanup. In a future exercise, you will relaunch this application, but using your own private network or VPC. The default network settings we are using for this lab are not secure, and I do not recommend that you continue to use these settings outside of this course. It is simply a proof of concept so that you can have experience going into the next lesson, making it all a little bit easier to wrap your mind around. EC2 is great for all sorts of different use cases, from running basic web servers to running high-performance computing clusters. That being said, though EC2 is incredibly flexible, reliable, and scalable, depending on your use case, you might be looking at alternatives for your compute capacity. For example, let's say you are looking for a way to run containers at scale on AWS. Containers provide you with efficiency and portability. And in this context, I'm specifically referring to containers like Docker containers. If you aren't sure what containers are, please review the readings on containers. AWS offers container services like Amazon Elastic Container Service, otherwise known as ECS, or Amazon Elastic Kubernetes Service, otherwise known as EKS. Both of these services are container orchestration tools. When you use containers on AWS, you need processes to start, stop, restart, and monitor containers running across not just one EC2 instance, but a number of them together that we call a cluster of EC2 instances. The process of doing these tasks is called container orchestration, and it turns out it's pretty hard to do it on your own. If you have a few containers, it's not so bad. But once you get to hundreds or thousands of containers that you are managing, it can be quite complex. Orchestration tools were created to help you run and manage containers. ECS is designed to help you run your containerized applications at scale without the hassle of managing your own container orchestration software. EKS does a similar thing but uses different tooling and has different features. We aren't going to go too much into this now. However, I did include a link to more learning resources around containerized applications on AWS in the readings following this video. The way you interact with these container services is you manage the containers running on a cluster through the orchestration tool's API. And then the orchestration tool carries out the management tasks. You can automate scaling of your cluster hosting your containers, as well as automate the scaling of the containers themselves. Containers have a shorter boot up time when compared to virtual machines. So if you need super fast response to increasing demand, then containers might be the service for you. So you can choose to host containers on top of clusters of EC2 instances as your hosting options for either ECS or EKS. However, what if you were looking for an alternative to hosting your containers? Because you either don't need access to the underlying operating system of EC2, or you don't want to manage that cluster of EC2 instances. Well, you can use a compute platform called AWS Fargate, which handles most of the underlying details for you. Fargate is a serverless compute platform for ECS or EKS, and we'll talk more about what serverless is coming up next. When using Amazon EC2 or container services running on top of EC2 as a compute platform, you are required to set up and manage your fleet of instances. This means that you are responsible for patching your instances when new software packages come out or when new security updates come out. You're responsible for setting up the scaling of those instances, as well as ensuring that you've architected your solutions to be hosted in a highly available manner, which means deploying instances across at least 2 availability zones. This is less management and less operational overhead than you would have if you hosted the same solutions on premises. But management processes will still need to be in place, and it's your responsibility to create those processes to fit your specific use case. This is actually really great, and in many cases, exactly what you want because it gives you a great deal of control over your solutions. Whatever happens on your instances and with your instances is in your hands. You can create simple or complicated setups that run and scale on AWS exactly to your specification. That being said, not every single solution requires this level of control over the environment. Oftentimes, you might be looking to focus on your own business solutions and let somebody else take care of the undifferentiated heavy lifting for you. Or perhaps you just simply don't want to fiddle around with scaling controls and fault-tolerant designs, but you still want all the benefits of doing so. This is where the term serverless comes in. A lot of AWS services are serverless in nature. Serverless means that you cannot see or access the underlying infrastructure or instances that are hosting your solution. Instead, the management of the underlying environment from a provisioning, scaling, fault tolerance, and maintenance perspective is taken care of for you. All you need to do is focus on your application. The rest is taken care of, or more accurately, the rest is abstracted from you. This means that serverless offerings are very convenient to use. You get to focus on the value of the service and what that service delivers, and not the underlying implementation details, thus reducing the number of operational support processes that you need to have in place. Remember the shared responsibility model that we had covered in an earlier lesson? This idea of serverless impacts that as well. So, for example, with Amazon EC2 instances, you are required to patch the operating system and security updates as they are released. With serverless offerings, the line between what you are responsible for versus what AWS is responsible for moves up. You do not have access to the underlying operating system that is running the service. Therefore, you are not responsible for carrying out tasks like patching. You are, however, still responsible for things like data encryption and access management. One example of serverless compute is AWS Fargate. AWS Fargate, which we mentioned briefly earlier, is a serverless compute platform that you can run either ECS or EKS on top of. Previously, you learned that ECS and EKS run on clusters of EC2 instances. And in that case, you are using EC2 as the compute platform for your containers. And you also have tight control over those instances. With AWS Fargate as the compute platform, you run your containers on a managed serverless compute platform. The scaling and fault tolerance is built in, and you don't need to worry about the underlying operating system or the environment. Instead, you just define your container, how you want your container to be run, and then it scales on demand. All right, let's wrap this up. I like to think of AWS services as existing on a spectrum. On one side of the spectrum, you have convenience, and on the other, you have control. Many services exist to give you control, like Amazon EC2, whereas other services exist to give you convenience, like the container hosting platform Fargate and the serverless compute AWS Lambda. We'll dive deeper into AWS Lambda coming up. AWS Lambda is one of the serverless compute options you have available to you on AWS. Lambda allows you to package and upload your code to the Lambda service, creating what's called a Lambda function. Once you create a Lambda function, it isn't always running all of the time. Instead, Lambda functions run in response to triggers. You configure a trigger for when you want your function to run, and from there, the Lambda service waits for the trigger. There's a long list of available triggers for AWS Lambda, and new ones are being supported frequently, so I won't run through them all now. However, a couple of common examples of triggers for Lambda functions are an HTTP request, an upload of a file to the storage service Amazon S3, events originating from other AWS services, or even in-app activity from mobile devices. When the trigger is detected, the code is automatically run in a managed environment, an environment you do not need to worry too much about because it is automatically scalable, highly available, and all of the maintenance of the environment itself is done by AWS. You do, however, get to choose the language your Lambda function is coded in, the amount of memory and CPU your function is allocated in the environment, its permissions, dependencies, and many other aspects of how the function runs. If you have 1 or 1,000 incoming triggers, AWS Lambda will scale your function to meet demand, each in its own isolated environment. Lambda is currently designed to run code that has a runtime of under 15 minutes. So this isn't for long-running processes like deep learning or batch jobs. You wouldn't host something like a WordPress site on AWS Lambda. It's more suited for quick processing like a web backend for handling requests or a backend report processing service. One of the best things about Lambda is that you aren't billed for code that isn't running. You only get billed for the resources that you use down to 100 millisecond intervals. To understand Lambda more, let's run through a quick demo. In this demo, I will create a Lambda function that resizes images uploaded into the employee directory application to be a uniform thumbnail size. It makes sense to create this sort of logic with the Lambda function. You don't need an application to be running 24/7 on EC2 to resize photos uploaded to the application. You really only need the resize logic to run when a new photo is uploaded. So here's our diagram for the app. What I want to do is add this. When a new photo is uploaded to Amazon S3, it triggers a Lambda function that resizes the image and uploads it to the same S3 bucket, but to a different location than where the original image is stored. Okay, let's go ahead and build this out. You can see that I'm already in the AWS Management Console, and I'm going to go ahead and click Create Function. From here, you have a couple of choices of how you want to create this function. We are going to author this one from scratch, and I already have the code written and downloaded to my local machine. So we're going to author from scratch. We'll name this resize photo, and then we get to select the runtime, and that's basically the language that you've coded your function to be. So for us, we coded this in Python, so I'm going to select the Python runtime. And then I'm also going to expand this permissions section here, and I'm going to use an existing IAM role for this code. The Python code that we wrote is using the AWS SDK to make API calls to S3. Therefore, those API calls must be signed and authenticated as we discussed in earlier lessons. So, in order for this code to gain access to the temporary credentials needed to sign the request, we are going to associate an IAM role with the appropriate S3 permissions to this Lambda function. So I'm going to go ahead and select the existing role, which is called AWS Lambda S3 Access, and then I'll click Create Function. At this point, we are now seeing the designer view, and I'm going to add a trigger for this Lambda function. I will select a trigger, and you can see here as I scroll down all of the different triggers that are available for Lambda. There are quite a bit, and there are also partner event sources powered by a service called Amazon Event Bridge, but I'm going to go ahead and select S3. Then I will select the employee photos bucket, which is the bucket that our app is using, and then I will use the prefix employee pick, because I know that that is the prefix where the function is uploading the images. And then I will scroll down, and I'm going to acknowledge this recursive invocation piece here. And this is essentially just letting us know that if I were to have this Lambda function read from the employee pick prefix, which is what triggered the event, and then process the image and upload it to the same spot, it would trigger another Lambda function run, and that would kind of just go on forever. So you want to make sure that you are using a different place for the output than you are for the input. So I'm going to go ahead and click Add. And now I will scroll down, and we are going to add the source code. So if you have source code with no dependencies, you can just type it right in here, which is really nice for experimentation. But for us, we're using some outside dependencies for resizing the image in Python. So I'm going to upload a zip file from my local machine. Then I'm going to click Save. Then I'm going to scroll down and change this Lambda handler. Go ahead and check out the class notes if you want to learn more about Lambda handlers and how this works. I'm just changing this so that it's referring to my actual file, and then I'll click Save. And now what I want to do is test this through the employee directory application. So I'm going to add a new employee. We'll name this Alana, locations USA, role is Cloud Technologist. She is a Mac user. And then we will upload her photo and click Save. So now it's been saved. I want to then test to see if this worked. So I'm going to click Monitoring here. And then I want to view the logs in Cloudwatch logs. So Cloudwatch logs is where the output goes from your Lambda function. I'm going to scroll down and click on the latest log stream, which is just the latest collection of log files from the Lambda function. And we can see that we did get the image resized output here, so I know that this code ran in response to the incoming event from S3. And that's it. That's how you create an AWS Lambda function at a high level. You could host the entire employee directory application's backend on Lambda with some refactoring, but I think I'm going to save that for a later conversation. If you're interested in the code that we used and more information about how Lambda works and handlers and how you write code for Lambda, I'll go ahead and include some resources for you in the reading section following this video. At this point, you've covered a few different AWS Compute services. The services covered so far can handle a wide variety of use cases. So, how do you know when to use each one? To figure that out, I think it's time to play a game. Welcome to the Which AWS Compute Service Should I Choose for My Use Case game show. We're your hosts, and you are the contestant.
We will present 3 different use cases that require compute on AWS, and it's up to you to choose the right service for the use case. You'll have 5 seconds to answer each question. Ready?
I'm ready, and I hope you are too. So let's do it. First question is up. Consider a scenario where you are a developer who is tasked with creating a new feature for a web application being hosted on EC2. The web application is an online store, and right now, all of the items being sold in the store are loaded into a database manually behind the scenes. By manually, I mean there is a person who adds each row into a database for each new item to be sold in the store. This process takes a long time and isn't very scalable, and on top of that, it's also prone to error. You are tasked with automating this process of getting new item information loaded into the inventory database. The goal is to have a person upload an inventory spreadsheet into Amazon S3, the object storage service, then have a process automatically load the data into the inventory database. What compute service would you use to host the processing logic to load the items from the file into the database? You have 5 seconds on the clock.
All right, let's discuss how you could have answered this question. You could have decided to use Amazon EC2 here. You could spin up a new instance specifically for this process and write some code that pulls the location of the spreadsheet for a new upload every so often, updating the database when it finds a new file. That would work. But before I make my answer final here, I have a question. How often does new inventory get added to the database?
New inventory gets updated 1 time per quarter.
Good to know. So it's not very often, which means this process would only run once a quarter. And that does change my answer. Here's why. Amazon EC2 charges per second or per hour. So if I have an instance running all the time to serve a request that happens once per quarter, that seems like a lost opportunity to optimize for cost. I would be spending money on a resource I rarely use. It certainly would work, but maybe not the best fit for this use case. I could automate the process of starting and stopping the instance when needed, but instead, what about using AWS Lambda?
Bingo. AWS Lambda is the correct answer for this one. There are a few reasons. First of all, to address your concern on cost, AWS Lambda only charges you for the compute you consume when the code is actually running. And the code is run in response to triggers or a direct invocation. So here's my suggestion. You know that the goal is to have someone upload an inventory document to S3, which should kick off the process of updating the database. You also learned that AWS Lambda has triggers that run your Lambda functions code. AWS Lambda integrates with many AWS services to act as triggers, and Amazon S3 is one of them. So my suggestion would be to create an AWS Lambda function, configure a put event as the trigger from Amazon S3. Then, when the inventory is uploaded to Amazon S3, it will trigger the Lambda function to run, and the code in the function will parse the inventory document and add each item into the database.
Time for the next question. Let's say you have an application currently hosted in your on-premises data center, which needs to be migrated to AWS. It's currently running on Linux servers in the data center, and you want to minimize the amount of refactoring needed to migrate to AWS. It's important that this workload is elastic and can support varying demand. What compute option would you choose? 5 seconds on the clock.
Time's up. Now, I'll go over the answer. Considering the fact that minimizing refactoring is an important aspect of this workload, I would architect a solution using Amazon EC2 as the compute service. EC2 instances can be launched from Linux-based AMIs, and the application could be hosted on the EC2 instance the same way it would be hosted on a Linux server on premises. Amazon EC2 also has the ability to scale in or out based on demand. So I think EC2 is the best service for this one.
That is correct. So if you answered EC2 at home, good work. Before we move on to the final question, let's dive into this answer a little more. Morgan, can you explain the thought process behind eliminating the other compute services we covered as answers to this question?
Sure thing. So, AWS Lambda could work, but you can't just upload the same code you would run on an Amazon EC2 instance into a Lambda function. There would be a decent amount of refactoring in order to take advantage of that service. Same idea with any of the AWS container services like ECS or EKS. Again, you'd have some amount of rework required to migrate to using containers. Therefore, Amazon EC2 is the best option for this migration. Now, time for one final use case. And this one is for all the marbles. Imagine a scenario where you are planning to write a brand new application using microservices or a service-oriented design. And you want to architect the application where it can scale up or down quickly, and you want to lower the risk of deploying new changes to production. Which AWS Compute service would you use? 5 seconds.
Okay, time's up. The answer for this use case is AWS container services like Amazon ECS or Amazon EKS.
Correct. The answer is either ECS or EKS for this one, because using containers makes it easier to support microservices or service-oriented designs. Containers boot up quickly, so scaling is quicker than with EC2 instances, and the use of containers helps with code portability. Meaning, if I write the code on my laptop and I run it in a container, then I test it in QA in a container, I can then expect that the same container would behave the same way once deployed to production, thus reducing the risk of any issues that might occur because of environmental issues.
All right, there you have it. out different use cases for a few of the AWS Compute services. Make sure you read up on AWS's other compute offerings and make informed decisions when architecting your solutions. You'll find there are a lot of options.
Remembering that these services exist to best suit different use cases helps. Don't try to use the same compute service for all of your use cases. Instead, pick the right one for the job and consider reevaluating choices for existing workloads as AWS continues to release new services and improve offerings.
If we look back at the architecture diagram for our application, the part that we want to focus on for this section of the course is this part, the network, or VPC, and its many components. But before we dive into networking on AWS, let's first put this into context. In the exercise you completed earlier, you launched an instance and connected to that instance over the internet. But to launch this instance, you needed to select a network. How you configure this network, or VPC, is actually what helps enable internet traffic to flow into your application. You might be asking, Alana, how did we select a VPC when we haven't even built a VPC yet? You're right, we haven't built a VPC, but fortunately, AWS creates VPCs for us in every region by default. When we launched our EC2 instance earlier in the course, we simply chose the default VPC. These default VPCs are meant to provide an easy way for you to get started with EC2 instances quickly and view your applications over the internet. However, you have to be careful what you put inside these default VPCs, as these resources will be subject to, well, the internet. And with internet access comes potential dangers. If we didn't select this default VPC, we would have needed to select a VPC that we custom built. In this section of the course, we'll focus on doing just that, building a custom VPC for our application that is more secure and provides more granular access to the internet than the default option we originally chose. While viewing this section, keep in mind that this information is geared towards EC2 related services. If you're using a different kind of compute, such as a LAMBDA function, you might not need a network at all. However, that doesn't mean that this isn't important. Networking on AWS is the basis of most architectures, so consider this information highly valuable. Coming up, we'll dive into some key VPC concepts. But for now, take some time to review the upcoming notes, which will cover some important networking basics that you should know before jumping into networking on AWS. In this video, you'll be learning how to create a VPC. With Morgan's help, we'll be both conceptualizing and building a VPC throughout the next few videos. The idea of a VPC is similar to how you think of walls around a data center. In a data center, walls act as the boundary between the outside world and all of your infrastructure. A VPC in AWS acts the same way. It creates a boundary where your applications and resources are isolated from any outside movement. So nothing comes into the VPC, nothing comes out of the VPC without your explicit permission. When you create a VPC, you have to declare two specific settings: the region you're selecting and the IP range for the VPC in the form of CIDR notation. For our VPC, we'll be locating it in the region where the rest of our infrastructure will be, the Oregon region. And our IP range we'll say is 10.1.0.0/16. All right, so currently our VPC just looks like a box. But with Morgan's help, we're going to build this out. All right, let's call Morgan. Hey Morgan, are you there?
Yep, I'm here. What do we need?
I was hoping you could build us a VPC that matches this diagram.
Sure, let's do it. If you're looking at the console, you'll first check to make sure that you're in the correct region by clicking in the upper right-hand corner. Alana mentioned that we're going to run out of the Oregon region, so we'll go ahead and make sure that this says Oregon. Once we choose the right region, we can now build our network. You'll type VPC in the service search bar, and that will bring up your VPC dashboard for this region. From there, you'll click on your VPCs and then Create VPC. Now we have a few settings to configure. We'll put in the IP range, which is 10.1.0.0/16, and the VPC name, which we'll say is app VPC. We'll leave the rest as default and then click Create VPC. Easy as that. Okay, Alana, what's next?
Nice, that was fast. After you create your VPC, you then divide the space inside the VPC into smaller segments called subnets. You put your resources, such as your EC2 instances, inside of these subnets. The goal of these subnets is to provide more granular controls over access to your resources. So if I have public resources, like our employee directory app, that we want to be accessed over the internet, I could put those resources inside a subnet with internet connectivity. If I have more private resources, like a database, I could create another subnet and have different controls to keep those resources private. To create a subnet, you need three main things. The VPC you want your subnet to live in, which is this one. The AZ you want your subnet to live in this case we'll choose AZA, or in other words, US West 2A, and then the IP range for your subnet, which must be a subset of the VPC IP range. For this, we'll choose the IP range 10.1.1.0/24. We'll call this our public subnet for public-facing resources. Then we'll create another subnet for our private resources. We'll place it in the same AZ, specify a different non-overlapping IP range, say 10.1.3.0/24, and then name it our private subnet. All right, now that we've got two subnets added to our VPC, it's time to put Morgan to the test again and have her build these out. And this time, I'm timing her.
Okay, we're on a time limit here, so let's create these subnets. Let's go ahead and start creating the public subnet. Back in the console, we'll click on Subnets in the side panel and then select Create Subnet. Then we'll select the VPC we're working with. In this case, it's the app VPC that we just created. Once you do that, you'll be prompted to provide a name. We'll call this Public Subnet 1. Then we choose the AZ, which Alana mentioned was US West 2A. And then the IP range of this subnet will be 10.1.1.0/24. We'll leave the rest as the defaults, scroll down to the bottom, and click Add New Subnet. Now we're going to repeat the same steps for our private subnet. Give it a name, such as Private Subnet 1, put it in the same availability zone, US West 2A, and then type in the IP range 10.1.3.0/24. Now we can click Create Subnet, and both subnets will be created. All right, Alana, what was my time?
Well, that was so fast that my watch didn't even register it. Wow. Okay, moving on. As we mentioned earlier, when you create a new VPC, all the resources you put in it are isolated and only have access to other resources in that VPC by default. For websites like our employee directory application, we want users to access our site over the internet. To enable internet connectivity, we need a component called an internet gateway. Think of this gateway as similar to a modem. Just as a modem connects your computer to the internet gateway connects your VPC to the internet. When you create an internet gateway, you then need to attach it to your VPC. If you create an internet gateway and don't attach it, it won't do anything except sit there. Okay, Morgan, show us how it's done. Create an internet gateway and attach it to our VPC.
All right, so let's hop back in. Back in the VPC dashboard, you'll click on Internet Gateways in the side panel. Then create Internet Gateway. You'll give the Internet Gateway a name and then click Create. On the Details page, you'll then select the Actions drop-down box and select Attach to VPC, choosing the app-VPC we've been working with, and then you'll click Attach. Back to you, Alana.
Sorry. I thought I'd have a bit more time to drink my tea. Right, okay. What's next? So we have an internet gateway that we can use to allow access from the internet. but what if we had a VPC with all internal private resources that we want to reach only from our on-premises data center? If we only want traffic to flow between AWS and our data center, and we don't want to allow direct access from the internet, what do? Luckily, there's another gateway designed for this very purpose, called a Virtual Private Gateway, or VGW. It allows you to create a VPN connection between a private network, like an on-premises data center or internal corporate network, to your VPC. With the help of a VGW, you can establish an encrypted VPN connection to your private internal AWS resources. We won't be using a VGW for our application, but it's good to know anyway. All right, so we have one VPC, 2 subnets, and an internet gateway attached to the VPC. Now, every time you look at an architecture, you should begin to think, how do I make this better? You're not going to have all the answers right away, but I do want you to take 10 seconds and think about some solutions. Okay, well, one option to make this better is the idea of having high availability. What that means is if this AZ goes down for whatever reason, what happens to our resources in that AZ? They go down too. So ideally, we would have resources in another AZ to take on the traffic coming to our application. To do this, we'd need to duplicate the resources in this AZ into the second AZ. So that means we need to create 2 additional subnets, each within another AZ, say AZ-B. All right, you get the point. You'll be able to create these additional subnets yourself later on in the exercise. But in the meantime, Morgan is going to build these out in the background for the rest of our demos. She's also going to launch an EC2 instance, hosting our application, and one of the public subnets. Sound good, Morgan?
Sounds good. I'll get right on that.
Okay. We'll see you next time. Let's take a look at our current VPC state. In the last video, we left off with a VPC with an internet gateway attached to it and 2 subnets, one public, one private, and one availability zone. However, Morgan was kind enough to build additional resources in the background to make sure our application was highly available. So now we have 2 additional subnets, one public, one private, and a different AZ, for a total of 4 subnets. She also created an EC2 instance hosting our employee directory inside of the public subnet in AZA. But we're missing one large component here. Say we have a user, and that user wants to access our employee directory. Eventually, that internet traffic would flow through the internet gateway, but then where would it go? Just because the traffic entered through the door of the VPC, it doesn't mean it ever made it to the right room. What we need to do is provide a path for the internet traffic to not only enter the door, but also make sure the traffic reaches the right room. Or, in other words, enter the internet gateway and find the right subnet. The way that we provide that path is through route tables. A route table contains a set of rules, called routes, that are used to determine where network traffic is directed. These route tables can be applied at either the subnet level or at the VPC level. When you create a brand new VPC, AWS creates a route table called the main route table and applies it to the entire VPC. AWS assumes that when you create a new VPC with subnets, you want traffic to flow between those subnets. In the last video, when we talked about VPCs being isolated, this is what we meant. The default configuration of the main route table is to allow traffic between all subnets local to the VPC. Let's get a quick look at the main route table of the VPC we just built out in the last video. Hey Morgan, do you mind showing us a quick example of the main route table?
Sure thing, Alana. Let's hop into the console. Here in the VPC console, we'll click on Route Tables on the side panel that will bring up all of the route tables that exist in this region. If we scroll to the side, you can see the main column and the VPC column. We're going to look for the main route table for the app VPC, which is this one here. When we click on it, we can bring up the bottom panel and then click on Routes. Here we can see the local route that has a destination of the VPC IP range. This means that all of the components inside of our VPC can communicate with one another locally by default. This local route will be present in every route table that you create. All right, that's the main route table. Okay, what's next, Alana?
While the main route table controls the routing for your entire VPC, you may want to be more granular about how you route your traffic to specific subnets. Remember we mentioned that subnets can be used to group your resources together based on whether they are publicly or privately accessible? Well, the subnet itself doesn't provide that access. Whether a subnet has access to the public internet or not depends on its associated route table. If a route from the internet gateway to the subnet exists, it has public access. If the route table doesn't have a route between the subnet and internet gateway, then it doesn't have public access. So we call subnets public or private, but it's really the route table that provides that access. So for your subnets, you'll create custom route tables. Inside these custom route tables, you'll have that default local route inside of it that allows traffic to flow freely within the VPC. But then you'll need to create additional routes. So the subnet with the internet-facing resources, in this case our EC2 instance with the employee directory website on it, will need a route to the internet gateway. All right, Morgan, we need your help again. Do you mind creating a custom route table and associating it to our public subnet?
Sure can. Let's go ahead and get started. Let's create the route table for our public subnet. Back in the VPC console once again, we'll click on Route Tables on the side panel and then Create Route Table. We'll give it a name, such as App Route Table Public, choose the App VPC, and then click Create. Okay, our route table is now created. But we're not done yet. We still have to edit the routes to allow traffic to flow from the internet gateway. To do this, we'll click on the ID of the route table and then we'll go to the routes section in the bottom summary table. We'll click Edit Routes, Add Route, put 0.0.0.0/0 for the destination, meaning it can take and deliver traffic from anywhere, and then we'll specify the target as an internet gateway. This will bring up available internet gateways to attach it to, and from here we'll select the app IGW. We're done with the routes, so we'll click Save. Now the route table is created, but we need to associate it with a subnet. If we only want this route table to apply to our public subnets, we'll need to associate it with our 2 public subnets only. To do this, we'll click on the Subnet Associations tab, select Edit Subnet Associations, and choose the public subnets we created earlier, then click Save. So you can see here that the subnet itself isn't providing the public access, it's the configuration of the routes. All right, we've hooked up our public subnets to a route table that allows internet traffic from the IGW to our employee directory application. If we wanted to create a route table for the private subnets, we would follow similar steps. You'd create the route table, make sure there's no route to the internet gateway this time, and then associate it to the private subnets. We'll let you do this part in the exercise at the end of this week. Okay, now we've configured a route to the internet gateway. We'll configure additional firewall rules later on. Okay, back to you, Alana.
Nice job, Morgan. So this is our final state of the diagram. 1 VPC, 4 subnets, 1 public, 1 private, in both availability zones. Our 2 public subnets are associated with a route table that allows traffic flow from the internet gateway. Our private subnets don't have a route table associated to them yet, so they follow the rules of the main route table. Local traffic only. Now we have a complete network that enables internet traffic flow to our public subnet. But how do we know it's secure? Well, at the base level, we know that any new VPC is isolated from internet traffic, so that prevents risk. But when you start allowing internet traffic by opening up routes, you need other options to keep your network secure. In AWS, you have 2 options to secure your VPC resources: Network Access Control Lists, which are often referred to as network ACLs, and security groups. We'll start with network ACLs. You can think of a network ACL as a firewall at the subnet level. With network ACLs, you can control what kind of traffic is allowed to enter and leave your subnet. So if I were to draw network ACLs in our diagram, they are placed around each of our subnets by default. The default network ACL allows all traffic in and out of your subnet. Using this default configuration is a good starting place, but if needed, you can change the configuration of your network ACLs to further lock down your subnets. For example, if I only wanted to allow HTTPS traffic into my subnet, I can do that. I can create a rule in my ACL that allows HTTPS traffic from anywhere on port 443 and denies everything else. However, just because I allow inbound HTTPS traffic does not mean my job is done. If I don't open up the corresponding outbound port used for that protocol, then that means the traffic is allowed in, but the web server's response will never leave the subnet. This is because network ACLs are considered to be stateless. I need to include both the inbound and the outbound ports used for the protocol. What that means for our HTTPS example is that I need to allow outbound HTTPS traffic from the subnet to the internet by creating an outbound rule. The other security feature is security groups. These are firewalls that exist at the EC2 instance level. Security groups are not optional, so anytime you create an EC2 instance, you'll need to place that EC2 instance inside a security group that allows the appropriate kinds of traffic to flow to your application. In our diagram, if I were to draw security groups, I would draw them around every EC2 instance in the VPC. In our case, we simply just have one EC2 instance, so we would need a security group around that instance. You know what? I think it's time for a demo. Let's get Morgan back in here. Hey, Morgan.
Hey, Alana. What's going on?
Do you have some time to build out a security group for our employee directory application? I think we need an example.
Sure. Let's get started. The default configuration of a security group blocks all inbound traffic and allows all outbound traffic. If you want your EC2 instance to accept traffic from the internet, you'll need to open up inbound ports. If you have a web server, you might need to accept HTTP and HTTPS requests to allow that type of traffic through your security group. You can create an inbound rule that will allow port 80 HTTP and port 443 HTTPS as shown here. The beauty of security groups is that I don't need to open up an outbound port for traffic to be able to leave the instance. That's because security groups are considered to be stateful resources. They will remember if a connection is originally initiated by the EC2 instance or from outside and temporarily allow traffic to respond without having to modify the inbound rules. All right, Alana, is that everything?
That's all for this one. Thanks, Morgan. Remember that security groups and network ACLs are powerful tools to filter network-wide traffic for a single instance or subnet's traffic. With security groups, everything is blocked by default, so you can only use allow roles. Whereas with network ACLs, everything is allowed by default, but you can use both allow and deny roles. To round out this week, it's time for an exercise. In this exercise, you'll be building out a custom VPC for your application. You'll then spin up an EC2 instance, place it in the network, and then connect to it to see your app. So you'll first create the VPC, and then you'll create 4 subnets, 2 public and 2 private. You'll then want to provide internet connectivity to your public subnets. To do this, you'll create an internet gateway and attach it to your VPC. You'll then need to create 2 custom route tables. The first will be a public route table, where you will add a route to the internet gateway. You'll then associate it with your 2 public subnets. The second route table will be the private route table, which will only have the local route. And you'll associate it with your 2 private subnets. Next, you'll launch an instance hosting your application. When selecting the network for that instance, you'll choose the VPC you just created and one of the public subnets to place it in. From there, you'll access your application through the browser. Note that because the application isn't hooked up to a database, you won't be able to actually interact with it yet. That's coming soon. Remember, if you get stuck, make sure you check out the class discussion forums. Have fun.
Hello again. I'm so happy to see that you've made it to week 3 of the course. So far, you've learned about compute and networking on AWS. It's time to move on to 2 other major categories: storage and databases. The employee directory application that we are building out currently has a solid network in place using Amazon VPC, and it's being hosted on top of Amazon EC2. The only issue is the app doesn't actually work yet because we haven't set up anywhere for it to store the employee information or the employee photos. This week, we are going to fix that. We will start off by learning about the different storage offerings AWS has, and we will compare and contrast them. Then you will create an Amazon S3 bucket in your account that the employee directory app is going to use to store the employee images. Then we will explore the different database services AWS has, and there are a lot. Though not to worry, we are going to focus on 2: Amazon Relational Database Service, otherwise known as RDS, and Amazon DynamoDB. You will then complete one final exercise for this week by creating a DynamoDB table where the employee information will reside. As always, make sure that you are utilizing the class discussion forums to ask any questions that you may have along the way. Take your quizzes, and please take a good look at the readings that we have placed between the video lessons. There's a lot of extra information in there that could be useful to you as you continue your journey with AWS. So, great work so far. Keep it up, and I'll see you in a bit.
Let's recap the architecture for our employee directory application. We've created the VPC and launched the app on an EC2 instance. The next thing we need to configure is the storage. Our application requires several types of storage for its data. For one, we need to store the operating system, software and system files of our app. We also need to store static assets like photos for the employee headshots. And then we have more structured data, such as the name, title, and location of each employee as well. All of that needs a home. The structured data usually requires a database, which we'll talk about later this week. So for now, we'll focus on storing the application files as well as the static content. There are 2 main types of storage that we can use to store this data: block and object. Here's the difference. Let's say that I have a 1 GB file with text in it. If I'm storing this in block storage, what happens is that this file is split into fixed size chunks of data and then stored. Object storage, on the other hand, treats each file like a single unit of data. This might seem like a small difference, but it can change how you access and work with your data. For example, let's say I want to change one character out of that 1 GB file. If my file is stored in block storage, changing that one character is simple, mainly because we can change the block, or the piece of the file that the character is in, and leave the rest of the file alone. In object storage, if I want to change that one character, I instead have to update the entire file. Let's take these 2 types of storage and access patterns and try to apply them to the data we want to store. For example, our static data, like the employee photos, will most likely be accessed often but modified rarely. Therefore, storing it in object storage is fine. For more frequently updated data, or data that has a high transaction rate, like our application or system files, block storage will perform better. In this section of the course, we'll discuss both block and object AWS storage services and how they interact with our employee directory application. Before we do that, take a look at the notes to get a refresher of the different types of storage. That way you can easily match the storage type to the AWS storage services that we talk about. When you launch an EC2 instance, you're going to need some kind of block storage to go with it. This block storage can be used as a boot volume for your operating system or as a separate data volume. For example, think about your laptop. With a laptop, you store your data in drives, and those drives can either be built in internally to your laptop or connected externally. EC2 instances have the same options as far as block storage goes. This internal storage is called Instance Store, and the external connected storage is called Amazon Elastic Block Store or Amazon EBS. Let's talk about Instance Store first. Instance Store is a form of directly attached storage, which means the underlying physical server has at least one storage unit directly attached to it. This direct attachment is also the main advantage of using this form of storage. Because it's so close to the physical server, it can be very fast and respond very quickly. But while it can be very fast, there is also one big downside. Because Instance Store is directly attached to an EC2 instance, its lifecycle is tied to the lifecycle of your instance. That means if you stop or terminate an instance, all data in Instance Store is gone. It can no longer be used or accessed. Over time, customers wanted the ability to keep their data even if they shut their EC2 instance down. So to provide that ability, Amazon created another storage option for EC2 called EBS volumes. These volumes, as the name implies, are drives of a user-configured size that are separate from an EC2 instance. The drives are simply network-attached storage for your instance. You can think of it as similar to how you might attach an external drive to your laptop. EBS volumes act similarly to external drives in more than one way. For example, I can plug in my drive to only one laptop at a time. The same goes for EBS. Most EBS volumes have a one-to-one relationship with EC2 instances, so they can't be shared or attached to multiple instances at one time. When I connect that EBS volume to my instance now has a direct communication line to the data in that volume. Nobody else can directly talk to that volume so that it maintains secure communication. If I decided I want to use that EBS volume with another instance, we can stop the instance, detach the volume, and then attach it to another instance in the same AZ, much like you can unplug your drive from your laptop and plug it into another one. Or depending on the instance type and EBS volume we're using, we may be able to attach it to multiple instances at a time, which is called EBS multi-attach. And perhaps the most important similarity is that an EBS volume is separate from your instance, just like an external drive is separate from your laptop. That means if an accident happens and the instance goes down, you still have your data on your EBS volume. This is what we refer to as persistent storage. You can stop or terminate your instance and your EBS volume can still exist with your data on it. EBS is often the right storage type for workloads that require persistence of data. However, the question typically comes down to, which EBS volume type do I use? That's right, there are many different types of volumes, but they're divided into two main types: SSD-backed volumes and HDD-backed volumes. In the readings, you'll learn more about both of these types. The last thing we'll need to talk about here is backing up data. Things fail, errors happen, so you need to back up your data, even in AWS. The way you back up EBS volumes is by taking what are called snapshots. EBS snapshots are incremental backups that are stored redundantly. The idea here is that if something goes wrong, you can create new volumes from your snapshots and restore your data to a safe state. All right, so we figured out block storage for our application. Now we need to figure out where to store our employee photos. A natural question is, why can't we just store these photos in Amazon EBS? Well, there's a few reasons. Number one, most EBS volumes can only be connected to one EC2 instance at a time. Eventually, as my app scales, I'll need to figure out how to access those photos from all of my instances. That's an issue. The second consideration is that an EBS volume has size limitations. That means that eventually there will be a limit to how many HD 4K photos I store of my employees in one drive. Ideally, I'd store these photos in a more scalable solution. So EBS probably isn't the right choice. Fortunately, AWS has a service called Amazon Simple Storage Service, or Amazon S3, that was designed to be a standalone storage solution that isn't tied to compute, meaning you don't mount this type of storage onto your EC2 instances. Instead, you can access your data through URLs from anywhere on the web, which gives this service its nickname, Storage for the Internet. S3 also allows you to store as many objects as you'd like, with an individual object size limit of 5 terabytes. This makes it ideal for our employee photos. Now let's talk about how we store things in S3. The underlying storage type for S3 is object storage. That means that all of the same characteristics of object storage are also characteristics of S3. So S3 uses a flat structure. It uses unique identifiers to look up objects when requested. You get the idea. S3 is also considered distributed storage, meaning that we store your data across multiple different facilities within one AWS region. This is what makes S3 designed for 99.99% availability and gives it 11 nines of durability. All right, let's learn about some S3 concepts. The first concept is a bucket. In S3, you store your objects in buckets. You can't upload any object, not even a single photo, to S3 without creating a bucket first. You then place your objects inside these buckets, and if you want to organize and arrange those objects, you can also have folders inside of the buckets. Let's create a bucket in the console. When you log in, you'll type in S3 in the service search bar. Once you click on it, you'll see the S3 dashboard, showing you all the available buckets for every region. I'll then select Create Bucket. And what I want to point out here is that buckets are region specific. So what that means is we can choose where we want to place our bucket. In this case, we want to place our bucket close to our infrastructure for our application, which is in the Oregon region. So we'll go ahead and leave it as Oregon. Next, we have the name of our bucket. Even though our bucket is specific to one region, our bucket name has to be globally unique across all AWS accounts and must be DNS compliant. Once you create your bucket, AWS will construct a URL using this name, so it has to be something that can be reachable over HTTP or HTTPS, meaning there can be no special characters, no spaces, etc. So for this bucket's name, let's choose employee-photos-buckets-al-001, which is DNS compliant. Now we can leave the rest as defaults, scroll down, and click Create. To work with this bucket, I'll need to find it in the list and click on its name. Here we can start uploading our objects. To do this, I'll click Upload, and then click Add Files. Find the file I want to upload, and click Open. Then scroll down and click Upload. So, as you can see, the object upload was successful. If I click on the name of my object, I get to see quite a bit of detail here. I can see the owner, region, and size. But most importantly, we can see the URL of my object. The first part of this URL is simply just the bucket URL that AWS created using my bucket name. Then AWS appended the name of my object, also referred to as the object key, to the bucket URL. Now what happens if I click on this URL? Access denied. That's weird, right? Well, not really. That access denied message leads us to a bigger question that most people have when they start out on AWS, and that's who can access my data. Earlier, I mentioned that you can retrieve your data from anywhere on the web. and people often think that means that anyone can retrieve that data. But by default, it's actually the opposite. Everything in S3 is private by default. This means that all S3 resources, such as buckets, folders, and objects, can only be viewed by the user or AWS account that created that resource. That's why I get that access denied message, because I was acting as an anonymous user on the internet trying to access an S3 object that's private. Now, that's not to say that no object or bucket can be open to the world. They absolutely can be, if you explicitly choose that option. And it's actually kind of a process to make something public. The reason it's difficult to make your objects public is to prevent accidental exposure of data. Let's try it. Okay, so if we want to make the object we created public, we need to do a few things. First thing is, from the object detail page, we'll want to click on the Actions dropdown, and then select Make Public. Then click it again. Now, once we do that, a message will pop up saying that our setting is blocked. So to ensure that we allow public access to our objects, we'll click on this link in the message. From here, we'll go ahead and click Edit Block Public Access Settings, uncheck the top box, and then click Save Changes. Type in Confirm, and confirm it. Now we'll go ahead and go back to our object by clicking on Objects, clicking on the object name, click Object Actions and Make Public again. And then we can go ahead and click on our object name again. And then click on the object URL. Now we can view our photo. That's how you make an object public. That being said, most of the time, you don't want your permissions to be all or nothing, to where either nobody can see it or everybody can see it. Typically, you want to be more granular about the way you provide access to resources. As far as access control, you can use IAM policies attached to users, groups, and roles to access your S3 content, and you can also use a feature called S3 bucket policies. S3 bucket policies are similar to IAM policies, in that they are both defined using the same policy language in a JSON format. The difference is IAM policies are attached to users, groups, and roles, whereas S3 bucket policies are only attached to buckets. S3 bucket policies specify what actions are allowed or denied on the bucket. For example, you might want to attach an S3 bucket policy to it that allows another AWS account to put objects in that bucket. Or you might want to create a bucket policy that allows read-only permissions to anonymous viewers. S3 bucket policies can only be placed on buckets and cannot be used for folders or objects. However, the policy that is placed on the buckets can apply to every object in that bucket. All right, to recap, S3 uses containers called buckets to store your objects. And you have several options to control access to those objects through the use of IAM policies and bucket policies. Thank you, and welcome back to everybody's favorite game show, Which AWS storage service do I use for my use case? Today we have one contestant during the final round of our show, and that's you.
In order to win the grand prize, you must answer the next 3 questions correctly. There will also be a bonus question, so there's an opportunity to get extra points. All right. Once we read the question, you have 5 seconds to answer and earn some points. Okay, let's get started.
All right, this is the first question. Let's say you're a developer and you plan to build out an application to transcode large media files like videos. You'll be using an AWS LAMBDA function to perform the transcoding, but you need a place to store both the original media files and the transcoded media files. Due to regulations, you need to store these files for at least a year. Which of the storage services that we've talked about in this course should you use? You have 5 seconds to answer. The answer is Amazon S3. Why is S3 the best solution here, Morgan?
Well, first off, the question says they're using a Lambda function. Because of that, I'm already ruling EBS out, as EBS volumes can only be attached to EC2 instances. Even if they were using EC2, video files are typically large in size, so you may have to use multiple EBS volumes to store that data, which might not be cost-effective in the long run. So EBS is out. Instance storage is also out for the same reason. We're not using EC2 here. But also, we want to make sure that this data will persist for a year, and instance storage is considered ephemeral.
All right, S3 it is. Let's put some points on the board for those who got it right. Morgan, tell us the next question.
The next question is, you're an architect for an e-commerce company. They want to run their MySQL database on an EC2 instance. This database needs a storage layer to store their order and customer information. The database will be frequently accessed and updated, so the storage layer needs to respond quickly. It's important that the storage is fast and durable. Which AWS storage service should you use? You have 5 seconds. And the answer is Amazon EBS. Add 30 points to your score if you got that right.
It seems like we're looking for storage attached to compute here. So why not Amazon EC2 Instant Store?
Right, that's also an option, but it's not ideal. Since it's an e-commerce company, their order and customer data is what drives the business, which means that the persistence and durability of that data is really important. Using EC2 Instance Store would definitely give us the speed that we're looking for, but it wouldn't give us the durability needed to store this data long term. So EBS is the right option.
That makes sense. All right, moving on. 2 more questions. You have a web application that needs to write to disk in order to perform certain calculations. The application will store temporary data during the calculation. The most important aspects of this architecture are speed and cost. With 5 seconds on the clock, which storage solution would you choose? And the answer is EC2 Instant Store.
Elena, would you mind telling us how we chose Instant Store and not EBS?
Sure. Once again, we're looking for storage attached to compute in this case. The first thing I want to point out is that this is temporary shuffle space we're talking about. So we're not looking at a huge amount of data, and we also don't necessarily care about the durability of that data. If the instance fails mid-calculation and you want to plan for failure, you can just restart the calculation from scratch. So durability doesn't matter, but cost does. By not using EBS and instead using Instant Store, you may save yourself some cost. That's because Instant Store is included in the overall EC2 instance price. So Instant Store is the best option in this case.
Okay, 30 more points on the board for those of you who got it. Now, the final bonus question for an extra 10 points is next. This is a tricky one, and you might have to think outside of the storage options that we've talked about so far. Okay, let's try it out. Let's say you're creating a WordPress site on multiple instances. By default, WordPress stores user uploads on the local file system. Since you want to use multiple instances, you'll need to move the WordPress installation and all user customizations into a shared storage platform. Which storage option would you use? 5 seconds to go. And the answer is Amazon Elastic File System, or Amazon EFS. We haven't talked about this service yet, so if you got points for this, great job. For those of you who didn't, no worries.
Let's go ahead and talk about the options. Morgan, typically when we talk about shared storage systems that multiple instances can access, we think Amazon S3. Why wouldn't we use it in this case?
Well, S3 isn't a file system. It actually uses a flat structure for storing objects instead of a hierarchy. Because S3 is a different type of underlying storage, it's actually not right for this WordPress use case. So, by moving the entire WordPress installation directory onto an EFS file system and mounting it to each of the EC2 instances when they boot, your WordPress site and all of its data is automatically stored on a distributed file system.
Wow, good to know. Well, you answered all 4 questions, and you win the grand prize of getting to do an exercise next. Congratulations, and that's it for today's show. Remember to check out the readings after this video. Now that you have a better understanding of storage on AWS, it's time for a hands-on exercise. In this exercise, you'll be working with Amazon S3. You'll have the opportunity to create an S3 bucket, upload an object, and create a bucket policy. Let's quickly go through what you'll be doing in the console. The first thing you'll need to do is create an S3 bucket. To do this, you'll find Amazon S3 in the search bar. And then in the S3 dashboard, you'll click Create Bucket. We'll name this bucket employee-photo-bucket. And then at the end of the bucket name, we'll append your initials and also a random number. This is to ensure that the bucket name is unique across all AWS accounts. We'll also locate this bucket in the Oregon region. Once you create a bucket, you can then upload your photos. I'll do this by clicking on my bucket name and then click Upload. From here, I'll click Add Files, find the object I want to upload, and then click Open. And then upload once more. From there, you should get a message saying you successfully uploaded your photo. Now, just because you uploaded a photo in S3 doesn't mean your application can read it by default. You'll need to give it permission to do so by creating a bucket policy that allows access from your application. The next step is we'll click Exit, which will take us back to our bucket, and then we'll click on the Permissions tab. From there, we'll scroll down and click Edit Bucket Policy. We'll supply you with the correct bucket policy, so you'll just need to copy and paste, and then click Save. The next thing you'll need to do is modify your application so that it knows which S3 bucket to access. To do this, we'll launch a new EC2 instance hosting your application and change the user data. So we'll first find the EC2 service. Click on Instances. Find the instance you launched earlier, then click on Actions, Images and Templates, and then click Launch More like this. This will use the exact configuration of your instance that you had before. However, you need to modify the user data. So you'll click on Step 3 from above, scroll down to the bottom where it shows your user data, and then where it shows Export Photos Bucket, you'll type in the name of your bucket. All right, once you're done with that, you'll click Review and Launch, click Launch, and then click Launch again. Your application will now use the S3 bucket you created and has access through the bucket policy to your objects. That's it for this one. If you get stuck, remember you can always post questions in the discussion forums. All right, have fun.
The employee directory application that we've been building out lets you keep track of employee data like their name, location, job title, and the different badges. The app supports adding new employees, viewing existing employees, as well as editing and deleting employees. All of this data will be stored in a database, which we haven't created yet. According to the architecture diagram you've chosen, Amazon Relational Database Service, or Amazon RDS, is used to store this data. So let's talk about databases for a moment. Relational databases are widely used across all industries, and it's likely that your company has many databases supporting a variety of applications and solutions. You can install and operate database applications on Amazon EC2 instances. And this is a good option for migrating existing databases into AWS. By running databases on EC2, you are already simplifying things from an operational perspective when you compare it to on-premises. And it's also a very common use case for EC2. When migrating a database from on-premises to EC2, you are no longer responsible for the physical infrastructure or operating system installation. But you are still responsible for the installation of the database engine, the setup across multiple availability zones with data replication in place, as well as the database server management tasks like installing security patches and updating database software when necessary. So EC2 makes it easier, but there is a way to lift even more of the operational burden of running relational databases on AWS. What if, instead of managing a database on EC2, you use one of the managed AWS database offerings, like Amazon RDS? The big difference between these two options is instead of taking care of the instances, the patching, the upgrades, and the install of the database, AWS takes care of all of that undifferentiated heavy lifting for you. The tasks that you are then responsible for is the creation, maintenance, and optimization of the database itself. So, you are still in charge of creating the right schema, indexing the data, creating stored procedures, enabling encryption, managing access control, and more. But all of the rest of the undifferentiated heavy lifting that goes into operating relational databases, AWS takes care of. To start off this section of lessons on databases, we will first focus on RDS. The upcoming reading after this video will dive into the history of enterprise relational databases and explain what relational databases are and how they are used. If you aren't familiar with databases, the readings coming up will give you some of that useful background information. Amazon RDS is a service that makes it easier for you to set up, operate, and scale a relational database. Now, instead of just telling you the features of RDS, I'm going to show you. As you can see, I'm already in the Amazon RDS dashboard. We are going to create the relational database our employee directory application can use to store the employee data. First, we will click Create Database, and then we are going to select the Easy Create option. This gives us the ability to accept the standard best practices for things like backups and high availability. You could select the standard create if you wanted to have more of a granular control to pick these sorts of features for your database setup. Next, we can scroll down and you will see the different database engines to choose from. What you see here on the screen is currently what is supported at this time of filming for database engines on RDS. There are the common engines out there like MySQL, PostgreSQL, Microsoft SQL Server, or Oracle, and then there's this one, Amazon Aurora. Amazon Aurora is an AWS-specific database that was built to take advantage of the scalability and durability of the AWS Cloud. Aurora is designed to be drop-in compatible with either MySQL or PostgreSQL. It can be up to 5 times faster than a standard MySQL database, and it can be up to 3 times faster than a standard PostgreSQL database. So if you have some use cases that require large amounts of data to be stored with high availability, durability, and low latency for data retrieval time, maybe consider using Amazon Aurora over a standard MySQL or PostgreSQL RDS instance. You can also compare this with other enterprise database options. In our case, we really only need a simple database without any high performance or large storage requirements, so I'm going to go ahead and select a standard MySQL instance. Next up, we need to choose the database instance size. This database instance is what we call one instance of RDS. You can think of it similar to an EC2 instance. And also similar to an EC2 instance is that you can choose the size of your database instance. Since this is just a demo, I'm going to go ahead and select a free tier eligible instance. Now we'll go ahead and scroll down and we'll give this database a name. We'll call this employee database. And then we will give the database a password for the admin user that would be used to connect to the database. We'll go ahead and just give this a simple password. Then we will scroll down and we're going to accept all of the rest of the defaults, which you can see here if you wanted to review. And then we will click Create Database. You can see the DB instance is in the process of booting up. You can see it's in this creating status. So that's going to take a couple of minutes to complete. In the meantime, let's talk about high availability and RDS. When you create an RDS DB instance, it gets placed inside a subnet inside of a VPC, very similar to an EC2 instance. As you learned in a previous lesson, subnets are bound to one AZ. And as a best practice for production workloads, we recommend that you always replicate your solutions across at least 2 AZs for high availability. With RDS, one DB instance belongs to one subnet inside of one AZ. So that isn't meeting the criteria for best practices. Now, before you get worried about managing all of this on your own, just know that you can easily configure RDS to launch a secondary DB instance in another subnet in another AZ using an RDS multi-AZ deployment. And RDS will manage all of the data replication between the two instances so that they stay in sync. The other cool thing about RDS multi-AZ deployments is that RDS also manages the failover for the instances. One instance is the primary, and the other is the secondary. Your app connects to one endpoint. If the primary instance goes down, the secondary instance gets promoted. The endpoint doesn't change, so no code change is needed. All the failover happens behind the scenes and is handled by RDS. All you need to do is make sure that your app can reconnect to the database if it experiences a momentary outage by updating any cached DNS lookups and reconnecting to the endpoint, which now points to the secondary instance. That's pretty cool if you ask me. All right, now let's hop back into the console. All right, and we're back, and you can see that the instance is up and running because the status is now available. At this point, you could connect to this database instance using something like MySQL Workbench, and then you could load your database schema onto it, ready to go, and much simpler than trying to install and manage this all on your own using something like EC2, for example. Using services like RDS makes operating databases significantly more accessible and lowers the operational overhead that comes along with relational database management. Before we move on to learning about Amazon Dynamodb, I want to touch on an idea that is important when you're making architecture decisions for your AWS solutions. Choosing the right database to fit your business requirements, rather than forcing your data to fit a certain database choice. There is no one-size-fits-all database for all purposes. You should pick a database that fits your specific use case. And with AWS, you have many choices for databases. We covered Amazon RDS and relational databases, and that was the default option for businesses for a long time. But relational databases aren't the best choice for all business needs. AWS creates services to support purpose-built databases, meaning that there are many database services AWS offers, and they each were built with specific use cases in mind, and therefore they are optimized for those use cases. Let's think about the employee directory application. We had originally decided that we would use RDS for the database, but now, after thinking about it some more, RDS might not be the best fit for our needs. all we are really doing is storing one record in a table for each employee. There are no complex relationships that need to be managed, and it's essentially just a lookup table. Relational databases offer all sorts of features that are great for complex schemas and relationships. But those features add overhead that is unnecessarily complex for simple things like lookup tables. On top of that, the RDS option we chose charges per hour of instance runtime. So we will get charged for the instances regardless of if we are using them or not. Our employee directory application will have much higher usage during the week and no usage on the weekends. Is there an AWS database offering that better fits our needs? Introducing Amazon DynamoDB. Amazon DynamoDB is a non-relational database that is great for storing key value pairs or documents or non-relational data. This service works great at a massive scale and provides millisecond latency. It also charges based on the usage of the table and the amount of data that you are storing in that table, not by the hour or by the second. This is a better option for our simple employee lookup table. Now, besides the employee directory application, there are other use cases that require databases of varying types. What if you are writing an application that needs a full content management system? Neither RDS nor DynamoDB would be the best solution for that. Luckily, AWS has quite a number of other database offerings. For this use case, you might look into Amazon DocumentDB. It's great for content management, catalogs, or user profiles. Now let's think of another use case. What if you had a social network that you were trying to keep track of? Keeping track of those kinds of social webs, figuring out who is connected to who, and querying that sort of data can be difficult to manage in a traditional relational database. So you could use Amazon Neptune, a graph database. This graph database is engineered for social networking and things like recommendation engines, but it's also good for use cases like fraud detection. Now, perhaps you have a supply chain and you need to keep track of everything with assurances that nothing is lost. Or maybe you are a banking or financial institution with records that require 100% immutability. What you really need is an immutable ledger. So perhaps look into Amazon QLDB or Quantum Ledger Database as a better fit for this use case. It's an immutable system of record where any entry can never be removed, and therefore it's great for industries that need to be audited for regulatory and compliance reasons. So, that was a quick rundown of some of the database offerings AWS has that are purpose-built. It can take a lot of experience and expertise to operate databases at scale, and that's why it's so beneficial to utilize one of the AWS database offerings. You don't need to be an expert on running a graph database to get to use one. Instead, you can just use the database service that is best for your use case and focus on your application and providing value to your end users. You don't need to build up a ton of in-house expertise to operate a highly scalable, immutable ledger database. You can just use AWS QLDB instead. The key thing to understand is AWS wants to make sure that you are using the best tool for the job. Coming up next, we will explore Amazon DynamoDB and get a look at more of the details. Let's talk some more about Amazon DynamoDB. At the most basic level, DynamoDB is a database. It's a serverless database, meaning you don't need to manage the underlying instances or infrastructure powering it. With DynamoDB, you don't create a database with tables that relate to each other like a relational database. Instead, you create standalone tables. A DynamoDB table is just a place where you can store and query your data. Data is organized into items, and items have attributes. If you have one item in your table or 2 million items in your table, DynamoDB manages the underlying storage for you, and you don't need to worry about scaling the system up or down for storage. DynamoDB stores the data redundantly across availability zones and mirrors the data across multiple drives for you under the hood. This lessens the burden of operating a highly available database. DynamoDB, beyond being massively scalable, is also highly performant. DynamoDB has a millisecond response time, and when you have applications with potentially millions of users, like an online game, having scalability and reliable, lightning-fast response times is important. Now, DynamoDB isn't a normal database in the sense that DynamoDB doesn't require a rigid schema or manage complex relationships or constraints. Relational databases work great for a lot of use cases and have been the standard type of database historically. However, these types of rigid SQL databases can have performance and scaling issues when under stress. The rigid schema also makes it so that you cannot have any variation in the types of data that you store in a single table. So it might not be the best fit for a dataset that is a little bit less rigid and is being accessed at a very high rate. This is where non-relational databases like DynamoDB come in handy. Non-relational databases have flexible schemas. With DynamoDB, you can add or remove attributes from items in the table at any time, and not every item in the table has to have the same attributes. This is great for datasets that do have some natural variation from item to item. The types of queries you run on non-relational databases tend to be simpler and focus on a collection of items from one table, not queries that span multiple tables. This, along with other factors, including the way the underlying system is designed, allows DynamoDB to be very quick in response time and highly scalable. So, things to remember. DynamoDB is non-relational. It is purpose-built, meaning it has specific use cases, and it isn't the best fit for every single workload out there. Taking a look at our architecture, we modified it to be using DynamoDB. We are now going to need to create an employees table for the app to write to and read from. We will create this DynamoDB table using the console. And you know what? Let's call Alana in here for this one. Hey Alana, can I get some help in here?
Hey y'all!
We changed our minds about using RDS and decided to change it over to DynamoDB. It's only one table, and it's essentially a lookup table for the employees. How hard do you think it would be to make this change?
Well, our app is actually designed to handle either RDS or DynamoDB as the backend database, so this won't take long at all. Here, I'll show you how. I'm in the console, and I'll go ahead and navigate to the DynamoDB service. From here, all you need to do is create a new table. Tables in DynamoDB require you to designate certain attributes as keys that make an item unique. We will select employee ID as the unique identifier for the items in this table. So we'll call the table name employees, and the primary key will be ID. Then we will just accept the defaults and create the table. Our app was coded to look for a table specifically called employees, so this actually should all work now that the table is created. To test it out, let's head over to the website hosted on EC2 and try to add a new employee. Click Add, and I'll go ahead and add myself. My name is Alana Layton. My location is Seattle. My job is a cloud technologist. And then let's see, I'm a Mac user. We'll say I'm Employee of the Month. Sorry, Morgan. And I am also a Seattle fan. Then I'll go ahead and add my picture. Click Open. And then click Save. All right, so now I'm added on the website. Now let's go back into DynamoDB and refresh the page. Then we'll click on Items to view all the items in the table. And there you can see my item. It's really that simple for a lookup table like this one. Back to you, Morgan.
Well then, that was easy. Nice. Now, not every use case is this simple. In the readings after this video, there will be more information about how Dynamodb works, use cases, how to create indexes, some information on table design, and links to further learning materials on Dynamodb. Let's put your new database knowledge to use. So far, the employee directory application is operating on EC2, and you have already created the Amazon S3 bucket from which the application will read from and write to for the employee photos. But you aren't really able to test that out without the database also being in place, since adding a new employee needs to store both employee photos and employee data. So let's go ahead and fix that. In this upcoming exercise, you will create a Dynamodb table called employees. And you will configure this table to store the employee ID, first and last name, location, title, and badges for the employees. You will then open the application from the browser and attempt to add a new employee, edit the employee, and delete the employee. After each step, you will verify that the data is being updated in the Dynamodb table using the AWS console. After you're done creating the table and populating it, you'll have a working app. The Dynamodb table you will use is automatically scalable and highly available. So there really isn't that much to do for this exercise. So have fun.
Hello everyone, welcome back to the final week of the course. You're almost done. Now that we've added a storage and database layer, the employee directory application is fully functional. But we have two more issues. The first issue is that we have no insight into how our application is performing and how it utilizes resources. So to fix this, Morgan will start off this week with a discussion of a monitoring tool called Amazon Cloudwatch. After we understand what the demand for your application looks like, we'll address the second problem, scalability. You may find that your application demand isn't always constant. So in the last section of the course, you'll learn how to automate the process of adding resources as demand increases and reducing capacity as demand declines to reduce cost. You'll also learn how to deliver traffic and balance load across changing amounts of resources. And if you made it this far, you already know we have discussion forums to help keep you on the right track, and readings after every video if you want to learn more. Let's get started with week 4.
When you have a solution built out of many different pieces, like how we build solutions on AWS, it's important to be able to see how different services are operating over time and to react to operational events as they are happening. Let's consider the employee directory application. It's Monday morning, and the users are seeing a latency on page loads. It's probably not good enough to wait until the user sees a slowdown, calls, or enters a ticket saying, "Hello, your application is running slow." If you receive a call or ticket from your users, you can then react and troubleshoot the issue. However, waiting for users to notice and report issues to investigate will generally lead to unhappy end users. Ideally, you'd be able to respond to operational issues before your end users notice. On top of that, the end user can only provide information about their experience, and they cannot give you insight into the inner workings of your solution. So, they can report the issue to you, but where is that issue stemming from? Is it an EC2 problem? Is it a database problem? Is there a code change that was recently made that's causing some issues? Without monitoring, you have to do some digging to figure that out. So, what do we need to do? The first step is to put proper monitoring in place. Monitoring is a verb. It's something that we do. We collect metrics, we collect logs, and we watch network traffic. The data needed to help you pinpoint problems comes from the different services and infrastructure hosting your application. And monitoring tools help you collect the data being generated by these systems. In a cloud environment that is ever-changing and ever-scaling, it's even more important to collect various types of information about the systems as they scale up and down and as they change over time. The different services that make up your solution generate data points that we call metrics. Metrics that are monitored over time are called statistics. A metric is a data point, like the current CPU utilization of an EC2 instance, where other data you could monitor might come in different forms, like log files. For example, Your network will generate data, like flow logs, so you can see how network traffic is coming into and out of your VPC. The servers will be generating metrics, such as how much CPU is currently being used, or how much network traffic the instance is accepting at any given moment. Then finally, one more example is your database layer, which will generate metrics such as the number of simultaneous connections. So you need a way to collect all of this information. Once it's collected, it can then be used to establish a baseline. And this baseline can then be used to determine if things are operating smoothly or not. If the information collected deviates too far from the baseline, you would then trigger automatic alerts to go out to someone or something to try to remediate the issue. A good monitoring solution gathers data in one centralized location, so that you can proactively monitor and operate your system to keep your end users happy, as well as allow for automated tasks to be triggered based on the data coming in. This is where Amazon Cloudwatch comes in. Cloudwatch allows you to monitor your solutions all in one place. Data will be collected from your cloud-based infrastructure, so you can see things like database metrics coming from RDS or Dynamodb, alongside EC2 metrics, as well as metrics coming from other services making up your AWS solution. Coming up next, we'll dive into some Cloudwatch features and use cases. In this video, I'm going to run through some of the features that Amazon Cloudwatch has to offer. We've already deployed resources into our AWS account for the employee directory application. So, to get a handle on what Cloudwatch is and how it works, let's dive into the AWS console and see what we can see. The end goal of this demo is to set up a dashboard that shows us the CPU utilization of the EC2 instance that we launched hosting our employee directory application. And then we also want to set up an alert that will be sent out if the CPU utilization of the instance goes over 60% for a period of time. Something to note about Cloudwatch is that a lot of AWS services begin reporting metrics to Cloudwatch automatically when you create the resources. So let's go ahead and hop in the AWS console now, and let's explore what types of metrics are available from the resources we have already created in previous lessons. You can see that I'm already in the AWS Management Console, and what I want to do now is navigate to Cloudwatch and select this service. And this brings me to the Cloudwatch dashboard. And so now what I want to do to view the metrics that were created by the resources from previous lessons, I'm first going to create a dashboard. So I'm going to go ahead and click Dashboards. A dashboard in Cloudwatch is a customizable page in the console that you can use to monitor different types of resources in a single view. This includes resources that are spread across different regions. I want to create a dashboard that shows me the CPU utilization over time for the EC2 instance. So now what I'm going to do is I'm going to create a dashboard. We're going to click Create Dashboard, and then we'll name it My Dashboard and click Create Dashboard. Next, we then select what we want to add to this dashboard, and we call them widgets. So I want to add a line graph as a widget on this dashboard because I want to compare the CPU utilization over time. So a line is going to be good for this one. Then I'll click Next. And then it asks from which data source would you like to create the widget. You can select metrics or logs. I'm going to go ahead and select metrics in this case. And then we'll click Configure. And now down here, it's listing all of the metrics and it groups by service because, again, AWS resources do often automatically post metrics to Cloudwatch when it's created. So I'm going to go ahead and select EC2 for the service. And then I want to select per instance metrics. And now I'm going to filter the instances in this account by the instance ID for our employee directory application, which I just had copied in my clipboard. And now we can scroll down and see all of the different metrics that are available for this CPU instance. I'm going to go ahead and select CPU utilization here, and then I'm going to select Create Widget. All right. So now we can see that we have this widget, this line graph showing us the CPU utilization, and this gives us visibility into one aspect of the health of our EC2 instance. You can explore in your own account what other metrics are available to you through Cloudwatch by default, but you also can report custom metrics to Cloudwatch programmatically. This is good to know because with EC2 and Cloudwatch, you only get visibility into the health of the instance by default, which doesn't really give you a holistic picture of the health of your application. The application running on the instance might not be operating correctly, but the CPU utilization could be fine. So keep in mind that you may choose to use custom metrics to get a more detailed and accurate view of health in these dashboards. So now, once a dashboard is created, you can then share it with others on your team so that everybody can get a good view of the health of your application. So now that we've created this dashboard, we're going to go ahead and click Save Dashboard, and that saves the widget here. And if you just hover, you can see the different data points and what the CPU utilization was. So you can see we hit a spike where we really maxed out our CPU for a couple of minutes here earlier today, and then it came back down. So this would have been indicative of some sort of operational event going on. So next what we want to do is move on to another feature of Cloudwatch, and that is Amazon Cloudwatch Alarms. So now I'm going to go ahead and click Alarms here. And notice I have no alarms in this account. What I want to do is create a Cloudwatch alarm that will notify me whenever the CPU utilization goes over a certain threshold. So just in general, Cloudwatch alarms allow you to create thresholds for the metrics that you are monitoring. And these thresholds can define normal boundaries for the values of the metrics. If a metric crosses a boundary for a period of time, then the alarm would be triggered. And you can then take a couple of different automated actions after an alarm is triggered. In our case, I just want to notify someone via an email when the CPU utilization spikes over 60% for some period of time, say 5 minutes. So let's create an alarm to do that. So now what we will do is click Create Alarm, and then we will select the metric for this alarm. We'll select EC2, per instance metrics, just as before, paste in that instance ID, and then select the CPU utilization metric and click Select Metric. From here, you can give this a specific name if you would like, and then you also have to select what type of statistic this is. We're going to leave it as average because we want to view the average CPU utilization over a time period. In this case, we are going to leave the time period to be 5 minutes. You want to make sure that you pick a reasonable time period where you don't wait too long to respond, but you also don't respond to every short-lived uptick in CPU utilization. There is a balance to strike here, and it will be highly dependent on your specific situation and your desired outcome. Okay, so now I will scroll down and I'm going to then type in 60 for the defined threshold here. And we are looking for the alarm to trigger when the metric crosses the threshold of 60% for more than 5 minutes. So now I'm going to go ahead and click Next. And this brings us to the Configure Actions page. And so for this one, you can now decide, okay, what are we going to do once this alarm is triggered? For Cloudwatch alarms, there are 3 states an alarm can be in. Either in alarm, okay, or insufficient data. An alarm can trigger an action when it transitions between these 3 states. In our case, I want to have this send out an alert to an email address when it transitions from OK to in alarm. AWS has a service called Amazon Simple Notification Service, or SNS, which allows you to create a topic and then send out messages to subscribers of this topic. You can imagine a scenario where we have system admins or developers on call for our employee directory application. And if something goes wrong, we want to send them an email paging them, letting them know that something is wrong with the app that they need to look into. So, in order to make that happen, what we're going to do is we are going to select Create New Topic, and then we can give the topic a name. All we have to make sure here is make sure that it is unique. So I'm going to go ahead and name this employee app CPU. And then we are going to select the email endpoint that will receive the notification. In this case, I'm going to go ahead and just put my email address, and then we'll click Create Topic. Now that that is created, we will scroll down and then click Next. We'll give this alarm a name. This will be Employee App CPU Util, and then click Next. And now we can preview this alarm. So notice the red line here. We set the alarm at 60%. We would have triggered an alarm earlier, but we didn't have anything in place. So we didn't know that anything was going on. After this, if it spikes again, we should be able to get an email sent out to our admin, which in this case is me. All right, so I'll scroll down and then just click Create Alarm. And there it is. This will remain in the insufficient data state for a little while until it gathers enough information about the CPU utilization to be able to correctly read if this is okay or if it is in alarm. All right, so what we've done now is we've created a dashboard that is monitoring the CPU utilization of our instance, and we've created a Cloudwatch alarm that will send out an email using Amazon SNS whenever the metric crosses the threshold. There are also other actions that you can take when an alarm is triggered, and we will go over that in upcoming lessons. So that's it for now. We will continue to use Cloudwatch in upcoming lessons to make our solution elastic through EC2 autoscaling. For now, you know the basics, and I encourage you to explore Cloudwatch in your own account and create dashboards for your employee directory application.
At this point, you know how to set up alarms to notify you when your infrastructure is having capacity, performance, or availability issues. But we need to go one step further. We don't just want to know about these issues, we want to either prevent them or respond to them automatically. In this section of the course, you'll learn how to do just that. Currently, our infrastructure looks like this. We have one EC2 instance hosting our employee directory application in a single availability zone, with Dynamodb as its database and S3 for storage of static assets. If I wanted to evaluate the availability of our infrastructure, I have to look at each individual component. I know that both Dynamodb and Amazon S3 are highly available by design, so that leaves one issue: this singular instance of our application. If that instance goes down, employees have no way to connect to our application. So how do we fix this? Well, as you already know, to increase availability, we need redundancy. We can achieve this by adding one more server. But the location of that server is important. If instance A goes down, we don't want instance B to go down for the same reasons. So to avoid the unlikely event of, say, an AZ experiencing issues, we should ensure that instance B is put in a different AZ. So now we have two instances that we've manually launched. But let's say our company grows rapidly, and the employee directory application is constantly being accessed by thousands of employees around the world. To meet this demand, we could scale our instances vertically, meaning we could increase the size of the instances we have, or we could scale our instances horizontally, meaning we could add more instances to create a fleet of instances. If we scale vertically, eventually we'll reach the upper limit of scalability for that instance. But if we scale horizontally, we don't have those same limitations. I can add as many instances to my fleet as I'd like. But if I need, say, 15 more instances to meet demand, that means I'd have to manually launch those 15 instances and manually shut them down, right? Well, you could do it that way, or you could automate this process with Amazon EC2 Autoscaling. This service will allow you to add and remove EC2 instances based off of conditions that you define. With this service, you can also maintain the health of your fleet of instances. But with more EC2 instances comes a bigger issue. How do we access those servers? Before, we were simply using the instance public DNS name or public IP address. But when you have multiple instances, you have multiple IPs to route to. Instead of maintaining the logic to send requests to your various servers, you could use a load balancer to distribute those requests across a set of resources for you. And since you can connect from your load balancer to access the application, you no longer need to use the public IPs of your EC2 instances. Before the next video, I'll spin up another instance hosting our employee directory application in a different subnet in a different AZ. See you soon. Now that we have multiple EC2 instances hosting our application in public subnets, it's time to distribute our requests across our servers using the Elastic Load Balancing, or ELB service. Conceptually, how this works is a typical request for the application would start from the browser of the client and is then sent to the load balancer. From there, the load balancer determines which EC2 instances to send the request to. After it sends the request, the return traffic would go back through the load balancer and back to the client browser, meaning your load balancer is directly in the path of traffic. Now, if we're looking at the architecture, the ELB looks like one thing. It looks like a single point of failure. But ELB is actually, by design, a highly available and automatically scalable service, much like S3 is. What that means is that A, the ELB is a regional service, so you don't have to worry about maintaining nodes in each availability zone or having to configure high availability yourself. AWS maintains that for you. And B, the ELB is designed to handle additional throughputs and will automatically scale up to handle the traffic coming in, without you having to configure that feature. Now, there are several types of load balancer that you can choose. There's the application load balancer that load balances HTTP and HTTPS traffic. There's the network load balancer that load balances TCP, UDP, and TLS traffic. And there's the gateway load balancer, which is mostly for routing traffic to third-party applications. For our employee directory application, we'll be load balancing web traffic, so we'll be using the application load balancer, or the ALB. When you create an ALB, you'll need to configure three main components. The first component is a listener. The goal of the listener is to check for requests. To define a listener, a port must be provided as well as the protocol. For example, since we're routing web traffic and we set up our application to use port 80, we'd want our load balancer to listen to port 80 using the HTTP protocol. Additionally, we could set up a listener for port 443 using the HTTPS protocol. The second component is a target group. A target is the type of backend you want to direct traffic to, such as EC2 instances, AWS Lambda functions, or IP addresses. A target group is simply just a grouping of these backend resources. Each target group needs to have a health check, which is how the load balancer can check that the target is healthy so that it can start accepting traffic. The ALB operates on the application layer, which is layer 7 of the OSI model. This gives the load balancer a lot of cool features, and one of those is the third component, which is a rule. A rule defines how your requests are routed to your targets. Each listener has a default rule, and you can optionally define additional rules. So if we had two target groups, A and B, we can set up an additional rule that says if traffic is coming to our /info page, we can deliver that traffic to target group B. So because of the fact ALB operates on layer 7, you can customize paths for your traffic. Okay, now it's time to put this into practice. Let's create an application load balancer in the console. If you want to find the ELB service, you'll need to go to the EC2 console. So we'll type in EC2 in the service search bar. And then on the side panel, we'll go ahead and select load balancers. Once we bring up our load balancers dashboard that shows all of the load balancers for this region, we'll then click Create Load Balancer. Here is where we choose which type of ELB we want, and you can see the three main types. We'll be using the ALB. From here, we'll choose a name and call it app-ELB. The next setting asks if we want an internet-facing or an internal-facing load balancer. An internet-facing load balancer does what you might expect, which is route requests from clients over the internet to your backend servers or your targets. An internal load balancer, on the other hand, will route requests from clients with a private IP to targets with a private IP. For example, if you had a 3-tier application with a web, app, and database tier, you could use an internal-facing load balancer to route traffic from your web tier to your app tier. For this app, we'll be routing internet traffic, so you can leave it as internet-facing. Then we select the listener. Currently, the default setting is to allow HTTP traffic on port 80. If we wanted to allow or limit to HTTPS traffic, we can click Add Listener, choose HTTPS, and we'll be good to go. But for this demo, we'll stick with the defaults. After that, we choose which availability zones we want to route traffic to. First, we'll choose the VPC. Then we'll select both availability zones, and then we'll choose the 2 public subnets. Then we'll go ahead and click Next, and then Next again. Now you choose your security group for your load balancer. This is where you decide which traffic you want to allow in. Here we'll choose a security group that will allow traffic on port 80 from anywhere. Next, we'll go ahead and configure routing. Here is where we create a target group for our backend instances. We'll give it a name such as app-target-group-2, and then we'll go ahead and leave all the defaults and click Next. This is where we'll be choosing which instances we want to live in the target group. So I'll go ahead and choose the 2 instances I have here, click Add to Registered, and then click Next, and then click Create. After the load balancer has been created, we can then select it in the menu, and then find the DNS name in the details page below. We can then pull that DNS name, copy it, and then paste it into a new tab. And from here, you can see our app. If I go to the /info page of our application, you can see which availability zone we're currently in. If I refresh the page a few times, you should see eventually that I'm being directed to both my EC2 instances in both AZs. And there you have it.
As more people visit our application, the demand on our 2 web servers is going to increase. At some point, our 2 instances aren't going to be able to handle that demand, and we're going to need more EC2 instances. Instead of launching these instances manually, we want to do it automatically with EC2 autoscaling. Autoscaling is what allows us to provision more capacity on demand, depending on different thresholds that we set, and we can set those thresholds in Cloudwatch. Okay, so we're going to draw a high-level example of how this works, and then Alana is going to build it out for us. So, looking at our application, traffic coming in from the outside can come down to either EC2 instance. In this video, these EC2 instances will be part of an auto-scaling group. Each of the EC2 instances that we launch will be completely identical. Then, we're going to run code to simulate stress on our employee directory application that will make the instances think that they're overloaded. When this happens, the instances will report to Cloudwatch and say that their CPUs are spiking. Cloudwatch will then go into an alarm state and tell autoscaling, hey, give me more EC2 instances. As each instance comes online, they'll pass ALB health checks, they'll start receiving traffic, and give us the horizontal scalability that we need. As each instance comes online and accepts traffic, we should see the CPU utilization go down across the entire fleet. All right, Alana, did you hear that? Do you mind building this out for us?
Let's make it happen. So to get this built out, the first thing we need to create is a launch template. This is going to define what to launch. So it's all about setting the configurations for the instances we want to launch. Morgan said we want our instances to be identical, and that's what we'll be configuring here. First thing we're going to do in the EC2 dashboard is find launch templates on the side panel. And then click Create Launch Template. You'll first provide a name and description. I'll call this app Launch Template. And then the description will be a web server for the employee directory application. Then you'll notice this handy checkbox here that asks if you're going to use this launch template with EC2 autoscaling. We are, so we'll check it and then scroll down. We'll then choose the AMI. Again, the launch template is all about what we launch. So what we want to do is create mirrors of the web servers hosting our app that we already have running. That way, whenever we scale out, we just have more instances with the exact same configuration. When we launched the instance hosting our app earlier, we used the Amazon Linux 2 AMI and a T2 micro instance type. So we'll select both of those options. We'll also select the same key pair that we used earlier, called the app key pair. Next, we choose the security group for our new instances. We'll use the same security group you created in the course, which in this case is the web security group. And then we can scroll down and expand the advanced details section. In the instance profile dropdown, we'll choose the same role we used previously, which is this one. Once we do that, we'll scroll all the way down and paste in our user data. This is what grabs our source code and unzips it so that our application runs on EC2. Now we're done and we can click Create. Now that we've configured our launch template, which again defines what we launch, we now have to define an autoscaling group, which tells us where, when, and how many instances to launch. To create an autoscaling group, I'll go ahead and back out of this. And then we'll select autoscaling groups on the side panel. And then we'll click Create Autoscaling Group. Then we'll enter a name such as app-asg, and then choose the launch template we just created. And then we can click Next. Then we'll select our network. We'll choose the same VPC that we created earlier in the course, App VPC, and then we'll select both of the public subnets, Public Subnet 1 and Public Subnet 2, and then we'll go ahead and click Next. We then need to select Attached to an existing load balancer to receive traffic from the load balancer we created earlier, and then choose our target group, App Target Group 2. Then we can click Enable ELB Health Checks, so that the load balancer will check if your instances are healthy, and then we can go ahead and click Next. Now we'll choose the minimum, maximum, and desired capacity. The minimum we'll say is 2. That means that our autoscaling group will always have at least 2 instances, 1 in each availability zone. The maximum we'll say is 4, which means that our fleet can scale up to 4 instances. And the desired capacity, which is the number of instances you want running, we'll also say is 2. Next, we can configure the scaling policies. With scaling policies, you define how to scale the capacity of your autoscaling group in response to changing demand. For example, you could set up a scaling policy with Cloudwatch that whenever your instance CPU utilization, or any other metric that you would like, reaches a certain limit, you can deploy more EC2 instances to your autoscaling group. So what we want to do is use autoscaling policies to adjust the capacity of this group. Earlier, Morgan created a Cloudwatch alarm that resulted in the action of sending out an email. Here we're going to create a Cloudwatch alarm, much like Morgan did, but this time it will result in the action of triggering an autoscaling event. So we'll go ahead and enable target tracking. We'll name this CPU utilization. Leave the metric type as CPU utilization. And then we'll say that we want to add a new instance into our fleet whenever the target value is 60%. We'll also say that instances will need 300 seconds to warm up. Then we'll click Next to configure notifications when a scaling event happens. This is optional, so for now we're going to skip past it, but you'll do it in the exercise coming up. You can also configure tags as well, but we'll skip past that too. All right, so we're here and we can review this and then click Create Autoscaling Group. Now all that's left is to stress our application and make sure that it actually scales up to meet the demand. To do that, I'll open up a new tab and paste the endpoint for our Elastic Load Balancer. So here's our application. I'm going to go to the /info page by appending it on the URL. And you'll notice here that we built in a stress CPU feature. This is going to mimic the load coming onto our servers. In the real world, you would probably use a load testing tool, but instead we built a stress CPU button as a quick and easy way to test this out. Then we can watch our servers scale with that autoscaling policy. So as the CPU utilization goes up, our autoscaling policy will be triggered and our server groups will grow in size. So I'm going to go ahead and select 5 minutes for the stress test. All right, some time has passed, we've stressed our application, and if we take a look at Cloudwatch, we can see what happened. So let's find Cloudwatch. And if we click on our OK alarms, and click on the alarm high alarm, we can see our alarm summary. As you can see, we went over our 60% CPU utilization across our instances, and that was our threshold for our autoscaling group to launch new instances. So ideally, what would have happened is autoscaling launched more instances to handle this load. Because we've launched more instances into our autoscaling group, there were more hosts to accept traffic from our Elastic Load Balancer, and the average CPU utilization then went down across our servers. And you can see that here in the alarm summary. All right, so let's go ahead and look at the EC2 instances that were launched into the autoscaling group. I'm going to go to the EC2 dashboard. I'm going to scroll down to target groups, and then select the app target group. Click on targets, and as you can see here, we launched one more instance to help handle the load. So we have 3 healthy targets for our autoscaling group. So now we have an environment with an autoscaling group and our launch template. We've set up an alarm in Cloudwatch that whenever our CPU utilization goes over 60%, we're going to launch more instances into that group. Okay, Morgan, back to you.
Thanks, Alana. Now, if we wait around long enough, what we would see is as the CPU load dropped off, then one by one, each instance would get terminated because we no longer need them, bringing our state all the way back down to the basic 2 servers that we need, which is the minimum number for this particular autoscaling group. All of that done without any human intervention. If for some reason you are doing this in your AWS account, don't forget to delete the autoscaling group instead of just the instances. Otherwise, guess what will happen? Well, the autoscaling group is going to say, hey, we need a minimum of 2 instances. So if you go in and just try to terminate the instances in that autoscaling group, it's going to notice that you are not meeting the minimum. It's going to spin up 2 more in its place. So in order to clean up in your account, make sure that you delete the autoscaling group or you set the minimum to be 0. So that way it doesn't go recreating resources that you're trying to delete.
Welcome to the final exercise of the course. And this exercise will be optimizing our employee directory application by using Amazon Cloudwatch, ELB, and EC2 autoscaling. The first thing you'll do is create an application load balancer. You'll use this load balancer to distribute requests to your EC2 instances that host your application. Next, you'll use autoscaling to launch the instances. To do this, you'll first create a launch template to specify your instance configuration. You'll then use this launch template to create an autoscaling group. You'll specify a minimum of 2, maximum of 4, and a desired capacity of 2 instances. You'll also configure your autoscaling group to use the application load balancer you created. You'll configure your autoscaling group to scale based off of Cloudwatch alarms, and trigger autoscaling to add a new instance when CPU utilization reaches 60%. Finally, you'll be able to go to your application and test this. By going to the /info page of the employee directory app, you can trigger an increase in CPU load and see your application horizontally scale in real time. Enjoy, and feel free to post in the discussion forums if you have any questions. And since this is your final exercise, remember to tear down all the infrastructure you created for this course. That way you can minimize future costs.
Nice work getting through this course. Let's take a look at how the architecture you built turned out. The employee directory application is currently being hosted across multiple EC2 instances inside of a VPC in private subnets. The EC2 instances are part of an EC2 autoscaling group, and traffic is being distributed across them using an application load balancer. The database is being hosted on Amazon Dynamodb, and the images are stored in S3. Beautiful. Looking at this from a maintenance perspective, you would need to ensure that your autoscaling policies are working well with your expectations. And it would likely take some amount of tweaking over time to get it right. You also would need to install any security patches and updates for EC2 as they come out, as well as keep an eye out for new instance sizes and types that might help you further optimize your solution. Now, this is really a great solution, but as with everything built on AWS, there are multiple ways you can architect a solution and have success. It really depends on what you are optimizing for and what you are trying to do that will determine how you architect an application. That being said, what I want to do now is present you with an architecture that could be a wonderful serverless redesign of the employee directory application, taking full advantage of cloud-native services like AWS LAMBDA. I'm going to touch on some services we haven't covered in this course also to give you ideas of alternative architectures. So, this employee directory application is a great example of a standard 3-tier application, where you have the presentation layer, the application layer, and the data layer. The presentation layer is the user interface. The application layer is the business logic, and the data layer is the database. As things are right now, the Amazon EC2 instances are hosting both the presentation layer as well as the application layer. This is true because the EC2 instances have a web server running that is serving the content for the website, like the HTML, CSS, and the JavaScript, which is the presentation layer. Then, the same instances are also handling requests for the backend logic for viewing, adding, updating, and deleting employees, which is the application layer. What I want to do now is separate these two pieces entirely, having the front end of the website hosted separately from the back-end application logic. It's important to separate the presentation layer from the application layer so that the instances are not overloaded by handling different types of requests at the same time. We are going to move the presentation layer to be hosted on Amazon S3. S3 supports static website hosting, and therefore, this is a great place for us to host the HTML, CSS, and JavaScript for our website. When you're hosting a static website with S3, you may think, well, my website isn't static. It's dynamic. It's pulling data from a database. So this isn't a static website, and therefore S3 wouldn't work for this use case. This is where JavaScript comes in. JavaScript files and scripts have the ability to make HTTP requests and load dynamic content, modifying the static page to display results that come back from the requests. So this should work well for us. The presentation layer is taken care of now on Amazon S3. Now what I want to tackle is the application layer. It used to be hosted on Amazon EC2, but let's go ahead and change this to AWS LAMBDA. This means that our employee directory application code would only be run in response to events being triggered by the front-end presentation layer. Now, you don't really want your front-end talking directly to your back-end code. So instead, you would expose your back-end Lambda functions using an API. We would use the service Amazon API Gateway to host this API. Each action that you could take on an employee would have its own method on the API. This API, hosted on API Gateway, would act as the front door to trigger the backend code, which we host on AWS Lambda instead of EC2, as discussed. We could have one Lambda function to handle all of the requests for employee data, or we could have one Lambda function per each action that you can take. We would keep Dynamodb for the database or the data layer, and we would also keep S3 for the employee photo storage. All of the access between these services would be handled via role-based access using IAM roles. One really nice thing about this is notice how because we built this solution in a more modular way, we were able to swap out how we were handling the presentation and application layer while leaving the data layer totally intact with no modifications. That is the type of flexibility that can help you innovate and adapt to change quickly. So now, for completeness and clarity, let's focus on the new architecture and fill it out a bit more. I will add some other AWS services to this diagram that you can explore on your own. I'm going to add Amazon Route 53 for domain name management for our website. And I'm also going to add Amazon Cloudfront here as well, which will allow us to cache the static assets like the HTML, CSS, and JavaScript closer to our end users by taking advantage of the AWS Global Infrastructure's AWS Edge locations. If a user wants to visit the employee directory application website and view all of the employees, here is the flow. The user would first type in the domain for the website, which would get sent to Amazon Route 53. Route 53 would then send back to the client the address of the static website being hosted on S3, and then S3 would send back the content to be rendered in the browser. This website has JavaScript making the API calls to the backend to load the dynamic content. So the API call to load all the employees would be made and it would hit API Gateway first. API Gateway would validate the request and then trigger the backend Lambda function. The Lambda function would then send an API call to Dynamodb to query the employees in the table, and then it would then return that data to API Gateway, which would then be returned to the JavaScript, which finally would be rendered on the page. All right, and that's that. With this architecture we just laid out, we have optimized for scalability, operational overhead, and depending on your usage, it could also already be optimized for cost. The serverless aspects of this make the operations for support much less than compared with Amazon EC2-based solutions. There is no patching or AMI management when you use serverless solutions like AWS Lambda. Also, notice how it was not required that I create a VPC, subnets, security groups, or a network access control list for this solution. The networking aspect of this is managed for you, though you can integrate serverless services with your VPC if you need to for compliance reasons. However, it's not required to get a solution up and running. You have many options to choose from when designing your application. You can imagine a scenario where you redesign the same application to be hosted using AWS Container Services, and then this entire diagram would change. There are a lot of ways you can build on AWS, and that's really the beauty of it. You can swap certain pieces of your solution out as AWS services are released or gain new features, and because everything in AWS is an API call, you can automate the process along the way. That's it for this course. From me, Alana, Meowsy, and Kiwi, thank you so much for learning with us. Please remember to check the course notes after the video for links to other courses where you can learn more about the AWS Cloud. Also, one more reminder to please remember to delete any resources you created in your AWS account for this class to avoid incurring costs. Thanks again, and we'll see you next time.
Welcome astronauts, space seekers, and AWS enthusiasts.
We're here to guide you through security in the AWS Cloud, basic principles of cloud security, AWS services for securing user access, and many more relevant security features in this course.
But before we get started, let's talk about your mission. As you know, bee populations are declining around the world, so we task you, eager explorer, to build a bee colony on Mars, codenamed Bee Mars if you choose to this mission.
We'll therefore be showing you how you can secure your AWS resources in this bee-themed endeavor throughout the course. So look out for more puns as we take you on this journey of not winging security.
Each week, we'll have a theme to it, with this first week being the introduction. Week 2 is securing your infrastructure. Week 3 is data protection. And we ended with week 4, securing your application.
Don't fret with the amount of content, as we've packaged them into little videos, reading content, demos, and even fun little quizzes. However, there is no spelling bee.
So get comfortable, log into your account, check out the AWS console, and prepare for blast off your space cadets. Happy building!
Hello, Dumila, Saubona, hello, Molo, and how's it? I'm Rudy, and I'm a solutions architect with Amazon Web Services, and I work across segments like robotics, fulfillment, and last mile. I'm originally from sunny Cape Town, South Africa, and I'm a big fan of education, and have authored 11 exams for several companies, including AWS. In fact, I think my yearning to teach comes from my grandfather, who was a teacher himself, and my mother, who decided to send me for speech and drama lessons. Thanks, Mom. Actually, my mom is enrolled in this course. Hopefully everyone is as amped for this course as I am, and don't worry, it won't be too hectic, brew. Salagashle, shap shap.
Hi there, I'm Hong, and I'm a solution architect at AWS. I've been here almost 4 years. I was born in Vietnam and moved to America 10 years ago. I went to University of Utah and studied marketing and information systems. I have to build this course because I would love to see more women learning about AWS Cloud. Hope you will learn some useful knowledge and have fun in this class. Mong là các bạn sẽ thích lớp học này.
Welcome to week 1. This week is all about the basics. After a quick review of some goals for the class, we'll dive into fundamentals around defining cloud security in AWS with the shared responsibility security model. And we'll talk some about compliance in AWS. After that, it's all about account management. Creating accounts, managing multiple accounts, and securing account and service API calls will all be covered. As there are no labs or exercises in this class, make sure you're reading through the class notes and suggested readings, and really think about scenarios to implement what is covered. Throughout the class, we will walk through several demos where we encourage you to follow along. And I hope you have some fun. I know Rudy and Hong had a lot of fun making this for you.
So what is cloud security? I mean, what is the cloud apart from a magical place where rain gathers? Well, it's the notion of taking IT services, packaging them up into building blocks, and providing them to you and your business on a pay-as-you-go model. An example would be S3, or Simple Storage Service, where you can store objects. AWS itself provides these services upon creation of your AWS account. But as with any service-based model, we want to give you the mechanisms to further secure your account and infrastructure. This means we readily provide services to secure your accounts, like IAM or Identity and Access Management, and Amazon Cognito, which allows you to provision end-user access to your applications. This all rolls up into the notion of a shared responsibility model. This translates to AWS being responsible for security of the cloud. S3 being the example we mentioned, but all of them, like AWS IoT Core, Amazon SageMaker, Amazon RDS, and so forth. We are also responsible for securing the infrastructure of our regions, availability zones, and edge locations, and only authorized personnel are allowed into these physical locations. You then, as a customer, build your workloads using these services, and therefore you are responsible for security in the cloud, i.e. whatever you build must be secured by yourself. Think of it kind of like a home alarm system. We provide it to you, but you still need to go and physically turn it off and on, as we don't really come into your house at night. Or do we? No, I'm just kidding. But let's think of it like this. When a bee comes into this world, it has a stinger. It's provided to the bee, but it still has to use it in the right way. Then again, a bee will die once it's used it. Okay, you know what? Let's just skip to the next section, shall we?
Hi, Hong again. As you are helping to build infrastructure for bee marts, there are compliant programs and standards that you will need to follow. For example, your bee citizen will need to go online shopping for their hive. You need to make sure your environment is PCI compliant so that you can store and process critical information of your bee citizens. Another example is when you need to build a highly confidential system for the queen bees and her government to store secrets, such as hidden hive locations. Thus, you need an environment that is compliant with FedRAMP. No matter how you deploy your IT infrastructure on your own servers or on AWS Cloud, you as an application owner need to maintain adequate governance over the entire IT-controlled environment. There are a few practices you need to follow. First, understand compliance objectives and requirements. Then, you need to establish controlled environment that meet those objectives and requirements. Also, you need to understand validation required based on your organization's risk tolerance. And you need verification of the operating effectiveness of your controlled environment. Now, when you build and operate your IT environment on AWS, it is a shared responsibility model between you and AWS. AWS part in this shared responsibility include providing its service on a highly secure and controlled platform, and providing a wide array of security features that you can use. Your responsibility includes configuring your IT environment in a secured and controlled manner for your purpose. AWS does communicate its security and control information to customers. You can find more details about this in this week's readings. You can also check if a specific AWS service is compliant with specific programs by visiting AWS Service in Scope portal. Again, you can find this link in the resources section. Thanks for watching. See you soon.
As you start your AWS journey, the first thing you are going to need is an AWS account. This allows you access to the console, and by provisioning other users, you'll open up other channels of interaction, like the command line interface or CLI, programmatic access, API calls, or even be able to use our software development kits or SDKs, like the one for Java, to interact with your AWS account. When you first create the account, you'll notice that you're using the super user or root user. This means that you can do anything and everything in your account, even deleting resources that you didn't mean to. For that fact, the first best practice is to create individual user accounts for each user and provide them with relevant access. For example, if they need admin access, then provision it. But if they only need read access to, say, a Dynamodb table, then make sure you only provision that. It's called the principle of least privilege access, and likewise means to provision the minimum needed access policies so that users can only perform the work they need to. You can create more users via the IAM console by choosing a username, password, whether you want to access it via the console or programmatically, and then you add policies that stipulate the actual resources they have access to. For the purposes of creating an admin user, you attach the administrator access policy, which is a JSON document that describes it. And you can see an example of what this looks like right now on screen. You can see that there are three main areas of interest. Effect, which can be an allow or deny, In this case, it's an allow. Action, which is what API am I going to allow or deny? And in this case, it's all APIs. Resource, which is where I can execute this against. In this case, it's all AWS resources. We're using the star or asterisk because not only are you a star, but so am I. But you know what? Just usernames and passwords are so last year. We want to add an additional layer of protection for privileged users as another best practice. It's called MFA and stands for multi-factor authentication. And it adds another verification check when you try to log in. This can and should be enabled for your root account, along with each account you're trying to protect. Essentially, you'll be prompted for a code once you've entered your username and password, with the code coming from an application like Google Authenticator, a security key like a YubiKey, or even an actual token device such as a Gemalto token. Other best practices include using strong passwords versus something like, say, password123, using roles and groups to assign permissions, and even monitoring them using Cloudwatch and CloudTrail, or maybe some other AWS services. In fact, that's the assigned reading we recommend, and it'll be listed in your resources section for the week. But with that being said, let's get back to all the fun and games, and how about we show you a demo? Hello Space Explorers, and welcome to the demo for multi-factor authentication, or MFA. In this demo, we'll cover creating a user and then assigning an MFA mechanism to this user. The first thing we're going to do is log into our AWS account with an admin user. Remember, you don't want to use your root account as those should be restricted so as to prevent accidental deletions and other funny business. So if we go in here, you can see that I'm logged in already, and I'm going to go to the IAM console, or Identity and Access Management console. We're going to click on the Users section here on the left navigation bar, and then we're going to click Add User. We're going to give it a fancy name. In this case, we're going to call this user Buzz. We're going to select AWS Management Console access by clicking on this doohickey, kind of also known as a checkbox. So once we select it, you'll see that it gives us the option to choose password generation, and we're going to let it auto-generate a password for us. And in this example, we won't ask the user to reset their password. So unselect this last checkbox. We're going to click the Next Permissions button. And because we want to create another admin user, we'll click the Attach Existing Policies Directly section. You can actually search here for admin, and you can see that it auto-completes. Or for those eagle-eye students, you'll notice that particular policy is at the top of our list. So we're going to go ahead and select it, and then click Next Tags. Now we're going to give it some fancy tags. We'll go with the Bee Mars for our mission. Click Next and Review, and now we're going to make sure that everything is A-OK. So, yep, kind of looks good. So let's click on the Create User button. And success! We've created a user. Just make sure that you copy these kind of details that are on this page. This is the sign-in URL that you want, and I'm going to copy that here. And the password, which is pretty important if we're going to log in with our user, aptly called Buzz. So now let's click Close. You can see that our user is there in our user dashboard, and we're going to actually click through on the name itself. We're going to navigate now to security credentials. So that's a tab that we click, and under the Assigned MFA Device section, we're going to click Manage. Now this is where you actually assign your MFA token. In my case, we're going to use a virtual authenticator. I've downloaded Google Authenticator to my phone, and I'm going to click Continue here. Now I'm going to show the QR code, and using my phone, I'm going to scan that barcode. So let's try that out. Scan barcode. Oh, cool. Already came up. And now we're going to enter in 2 consecutive MFA codes. So let me enter in the first one here. And we'll wait for it to tick over to the next one. Oh, there we go. Now we click Assign MFA. Cool, success again. Now we're going to close that, and we're going to try to log in with that user. So let me just log out from my AWS console. I will pull up that URL that was in the Create User screen. Oh, you'll see it's asking me for my username. I know that already. It is Buzz. I'll put in my password, click sign in. Oh, and I'm prompted for my MFA code. So let me check it out on my phone. Click submit, and voila, we're in to the matrix or the AWS account, depending on how you look at it. But anyway, thanks for watching along, and see you soon, Space Cadets. That's it for this section. Hopefully you enjoyed the buzz around securing AWS accounts. Be seeing you soon.
Hello everyone, Hans here. So now we know building BMARS is the right thing to do. We need to hire more people to help out with our missions. We grow in number of teams, organizations, and AWS accounts. Let's say we have 2 AWS accounts, one for storing our data in S3 called Data Account, and one for developer to build applications called Dev Account. You can delegate access across AWS accounts using IAM roles. Let's take a look at how to do it. Hey folks, let's say you have multiple IT engineers that are tasked to manage AWS account and resources. As an IT manager, you will need to grant AWS admin access for your engineers. This tutorial will show you how to create an IAM group for admin users and assign that IAM user to the group. Let's get started. From the AWS Management Console, you can search for IAM service in the search box. Click on IAM, and you will be prompted to IAM console. Let's create an IAM group. On the left side, click on Groups, Create New Group. I will name it as Admin Group. Click on Next Step. Now is the time that we choose an IAM policy to associate to our new group. In this case, because we're creating an IAM group for admin user, I will search for Administrator Access IAM policy. Click on the policy. Next step, we will review the name of the group and the policy. Then we will create the group. Now, this is the new group that you created, admin group. And if you click on it, you will see the name, the ARN of the group. And also, you can see the administrator access policy attached to the group. So now is the fun part. Let's create an IAM user and associate to this group. On the left column, click on Users, Add User, and create a name for your admin user. In this case, I would do admin IT and my name on it. You can choose to allow programmatic access, which means access to API, CLI, or AWS SDK. You can also choose to allow management console access, which means the user can log into AWS Management Console. And you can choose to auto-generated password or to create a custom password for your user. You can also ask your user to reset password when the first time they log in. Next, let's associate the permission. So there's 3 options for you to create permission for a user. The first option is to add user to an IAM group. The second one is to copy permission from existing user. And the last option is to attach existing policy directly to that user. Now, in this demo, I'm going to choose adding a user to a group. And when you do that, you see the list of groups available. Then I'll click on Admin Group, which is the new group that we created earlier. Next, we're going to do tagging for this IAM user. So tagging is one of the best practices to help you managing resource in AWS account. In this case, I'm going to use the key for tag is department, and the value would be IT because this IAM resource belongs to IT department. When we reviewed, we can see that the username, we can see what type of access the user allowed, and we can also see what group the user belonged to. Now let's create the user. So after you created the user successfully, the console will show you the username, the access key ID, the secret access key, and the password. So you have to download the resource because it will not be available later on the console. You can choose to download by clicking on the download.csv button, or you can choose to send an email with log instruction. So if we go to our IAM group, we will see that right now on our admin group, there's a newly created user, admin IT Hong. Awesome, so now we're done with the demo. You can follow these tutorials for step-by-step instructions in the resources sessions for the week. But now we need to create and manage more and more AWS accounts. It comes with a new problem. How do we scale and automate AWS account creations? How do we make sure that each team or organization has the appropriate permissions to use the right AWS services and resources? We certainly don't want developer bees to have permission to see the billing and control budgeting. We also want to make sure our sheriff bees have access to audit AWS activities to detect and isolate if AWS resource and accounts are compromised. Adding to that, we want all the bills in multiple AWS accounts to be rolled up to one central AWS account so that the queen bee can pay for all of AWS cost. Here come AWS organizations. This AWS service can help you centrally govern your environment as we grow and scale. Using AWS organizations, you can automate account creation and management, create group of accounts to reflect business need, govern access to AWS services resource in regions by policy, set up single payment method for all AWS accounts with consolidate billing. You can share resources across accounts. AWS organization make it easy for you to share critical central resources across your accounts. For example, you can share your central AWS directory service running on Managed Active Directory with all accounts in your organization for application to access your central identity store. Additionally, you can ensure application resources across your account are created on your AWS Virtual Private Cloud subnet by centrally defining them once and sharing them across your organization using AWS Resource Access Manager. You can find a list of supported services in the resource section of the course. So how does AWS organization work? First, you will choose an AWS account as the master account. Now, you create an organization in this master account. Note that when you use organization to create a new account, an IAM roles will be created so that master account can switch role to access your member account. Then you can either create organizations unit called OU or accounts called member accounts under organization. Then you can create service control policy to OU or to the member account. There is a few best practices to note as you're creating a new organization. The first one is plan ahead for the structure of your organization. The second best practice is, for the master account, we recommend that you keep the master account free of any operational AWS resource. In addition to making it easier for you to make high-quality control decisions, this practice will make it easier for you to understand the charge on your AWS bill. The next best practice is to use CloudTrail. Using AWS CloudTrail in the master account to centrally track all AWS usage in the member accounts. Next thing is to apply least privilege practice. when setting up policy for your OUs, assign as few privileges as possible. And for organizational unit, assign policy to organizational units rather than to accounts. This will allow you to maintain a better mapping between your organizational structure and the level of AWS access needed. Well, you need to perform testing, right? You test new and modified policies on a single account before scaling up to organization unit. Automations. Use the API and AWS CloudFormation template to ensure that every newly created account is configured to your liking. The template can create IAM user, roles, and policy. It can also set up logging, create and configure VPC, and so forth. So that's it for managing multi-account and provisioning cross-account access. See you in an upcoming video. Hello again. Let's talk about how you can authenticate and authorize users to access AWS resources. There are 3 use cases when you need to provide access. The very first use case is when the user accessing AWS accounts and resources. An example of this use case is when you enable single sign-on your AWS account to let a developer log into AWS account using credentials from your corporate identity to create and run AWS LAMBDA function. Another example is you are building an internal reporting portal hosted on AWS that only allow internal employees of your company to log in and see the reports. Since your companies already have existing corporate identities on an Active Directory, you can federate this Active Directory with Amazon Cognito. The second use case would be allowing resource accessing other resource. To allow your application to access AWS services, you need to be able to validate the identity and permissions of your application resources. For example, your containerized application run on Elastic Kubernetes services need to do an API call to query table in AWS NoSQL database Dynamodb. You will need to securely validate the API call and manage permissions for action that your app is allowed to perform on Dynamodb table using short-term credential called IAM role. Using roles help you follow security best practices for granting least privileged access and enable you to manage fine-grained permission for your AWS services and applications. IAM roles enable you to grant the resources access to data without distributing password or API key or hard-coding credentials in your source code. And the last use case is to allow end users accessing the application. Let's say you're building a great, very fun social media application to help end user create a New Year resolution and have their friends and family celebrate their progress. Your application will need to manage user sign up and sign in, and you also need to enable multi-factor authentication when users sign in. Now that we have discussed 3 use cases, the next videos will dive into 5 available AWS services for identity, directory, and access. See you soon! In the previous video, we talked about 3 use cases for authentication and authorization. Now, let's dive into each of the 5 services related to the use cases. The first one is AWS Organizations. AWS Organizations is a service to help you create and manage multiple AWS accounts. Another helpful feature of AWS Organization is consolidated billing, which helps you to roll up billings from multiple AWS accounts to a central master account. The second service is AWS Identity and Access Management. AWS Identity and Access Management, or IAM in short, enable you to manage access to AWS services and resources securely. Using IAM, you can create and manage AWS users and groups and use permissions to allow and deny their access to AWS resource. AWS IAM allows you to do several things. The first thing is to manage IAM user and their access. The second thing is to manage IAM roles and their permission. And lastly, you can manage federated users and their permissions. In this use case, you can use any identity management solution that supports SAML 2.0 or use one of our federation samples, for example, AWS Console SSO or API Federation, to assign permissions to a user, group, role, or resource. You create an IAM policy by using either the visual editor or just the JSON editor. The visual editor guides you through granting permission by using IAM policy without requiring you to write a policy in JSON. To learn more about policy language, see the AWS IAM policy reference link in the course notes. And a small tip, you can use IAM policy simulator to test your newly created policy. The link to access the IAM policy simulator can be found in the course notes as well. So now you can apply AWS managed policy, a customer managed policy, or an inline policy for an IAM identity, such as user or group. Example can be found in the AWS documentation and the class resources. To quickly summarize, an AWS managed policy is a standalone policy that is created and administered by AWS. AWS managed policies are designed to provide permission for many common use cases. A customer managed policy is a standalone policy that you create and administer in your AWS account. And finally, an inline policy is a policy that is embedded in a principal entity, such as a user, a group, or the role. The different types of policy are for different use cases. In most cases, we recommend that you use managed policy instead of inline policy. The third service that we talk about is AWS Single Sign-On. AWS Single Sign-On, or SSO, is a cloud service that makes it easy to centrally manage SSO access to multiple AWS accounts and business applications. It helps you manage SSO access and user permission across all your AWS accounts in AWS organization. AWS SSO includes a user portal where you can let your end user find and access their assigned AWS account, the cloud application, and custom application in one place. Your user simply sign in to use a user portal with credentials they configure in AWS SSO or using the existing corporate credentials to access all their assigned account and application from one place. And the last service I'm talking about in this video is Amazon Cloud Directory. Amazon Cloud Directory enables you to build flexible cloud-native directory for organizing hierarchies of data along multiple dimensions. With Cloud Directory, you can create directory for a variety of use cases, such as organizational chart, course catalogs, and device registry. While traditional directory solutions, such as LDAP-based directory, limit you to a single hierarchy, Cloud Directory offers you the flexibility to create directories within hierarchies that span multiple dimensions. You can find links to various documentation in the course resource. And that's it for this video. I'll see you soon.
We've talked about authentication and authorization of internal or infrastructure users via IAM, but what about end users? And what if we have an existing identity store that we want to reuse? I mean, is that possible? Well, firstly, a best practice is to logically separate your infrastructure users and end users. This means that you can manage them independently and avoid overlap of process. For example, if you had all your users, irrespective of type, in one identity store, and that store had a disruption, you would not be able to effectively shut off access to specific users to debug without some workarounds. As a way forward with your workloads, and specifically web and mobile apps, AWS provides a service called Amazon Cognito. Now, Amazon Cognito itself provides an identity store called Cognito User Pools. This would store all your users so that registration, authentication, and even password resets are handled by the user pool. Now, say a user had logged into your application and wants to upload to an S3 bucket. They require access to that bucket. This is where Cognito identity pools come in and allow authorized access to AWS resources. But what if you have an existing identity store? Well, no worries, you can federate or link an electronic identity across multiple systems. With Cognito, you can do that with the identity pool, which means linking your Cognito user pool with, say, an OpenID Connect provider, or even log in with Facebook or Google. At Amazon, we provide these mechanisms because our customers consistently ask for platform freedom, and thus we do not lock you into proprietary systems. Speaking of freedom of choice and existing identity stores, what if you need to integrate with a Microsoft Active Directory identity store? As a reminder, Microsoft Active Directory can be used to enforce security policies, such as verifying if a logged-in user is an administrator or an end user on Windows domains. And for this particular case, AWS provides a service called AWS Directory Service for Microsoft Active Directory, or the less tongue twister titled AWS Managed Microsoft Active Directory. The two ways you can use it is to federate, and no, not like the Federation of Planets, but to join your existing directory to the AWS one. Now you can remember. This allows you to use EC2 or Elastic Compute Cloud, RDS for SQL, and other services that utilize Active Directory with your identity store, and therefore not have to recreate all your users from scratch. You can even use single sign-on or SSO to provide a seamless integration between different services. SSO means that a user would log in once and then be able to access, say, 2 different applications without having to log into each one individually. Lovely, right? I don't know about you, but having to remember one less password is definitely a plus for me. Granted, you can still use Managed AD as a standalone service, and this is usually for customers who do not have an existing identity store. Mind you, if you don't need the full feature set or even deployment footprint needed by Managed AD, don't fret. We've got you covered with Simple AD. It's a standalone managed directory that's available in 2 sizes, small and large. Small for up to 500 users and large for up to 5,000 users. This means that again, you do not have to manage user accounts and build a mechanism around it. Some of the benefits of Simple AD are plug and play with apps that use Active Directory, access to AWS applications like Amazon Workspaces, Amazon Workdocs, or even Amazon Workmail, point-in-time recovery along with daily automated snapshots, and so on. By the name, however, you've probably guessed that it's kinda simplified. Therefore, you do not get certain capabilities with Simple AD, such as AWS SSO or support for Amazon RDS for SQL Server. For the full list of supported and unsupported features, please check out our resources section. One other feature to mention is Active Directory Connector. This is useful if you want to reuse an existing on-premises Microsoft Active Directory without caching any information in the cloud. This means that you can use your existing corporate credentials to log into AWS applications like Amazon Workspaces and even manage AWS resources like S3. Similarly, as with Simple AD, it comes in 2 sizes, small and large, and you can spread out application load against multiple AD connectors. And as always, thanks for joining us in this explanation of identity providers and directory services.
Yay, it's week 2. Now that you've been introduced to some of the basic concepts and our mission, let's start going a little deeper. Focusing on infrastructure security this week, our big topics will be things like network isolation, monitoring, and auditing. As our wonderful Space and Bee enthusiasts keep taking you through security in AWS, make sure you keep looking at those suggested readings in the notes. Those will take you even further and really help to fill in those gaps.
Hey, what's up? I'm Hong.
And I'm Rudy, and we're going to talk about network isolation.
AWS has placed a limited number of access points to the cloud to allow for more comprehensive monitoring of inbound and outbound communication and network traffic.
These customer access points are called endpoints, and an endpoint is a URL that is an entry point for a web service.
Some services, such as IAM, do not support regions. Therefore, their endpoints do not include a region.
If a service supports regions, those resources in that region are independent. For example, US West 2 is an entry point for all AWS services in that region.
Endpoints allow secure HTTPS access, or we call HTTPS, which allow you to establish a secure communication session with your resource running in AWS service.
As we build out our infrastructure on the planet, we want to isolate certain pieces so that we minimize the surface area that can be attacked. Whether this is an alien trying to gain access or even asteroids crashing into the surface.
Think about it like a fort. We're building a fort on this barren planet so that we are protecting ourselves and the bees.
But if we go further, we can build hives inside our fort so that we isolate the hives inside the fort itself.
AWS offers the Amazon Virtual Private Cloud, which provides a private network within the AWS Cloud. Amazon VPC provides not only isolation from other customers in the private cloud, it also provides layer 3 isolation from the internet as well.
Your Amazon VPC uses IP address spaces allocated by you. These can be used to build a private infrastructure where networks are isolated from the internet.
You can connect your on-premises environment or other VPN infrastructure to Amazon VPC using IPsec tunnel and AWS Server Connect.
And of course, you can allow resources in your VPC to talk to the internet if you choose to do so.
Let's dive into available features of VPC in the next video. Rudy, do the thing.
Welcome to the video on VPCs or Virtual Private Cloud. And before you ask yourself what it is, rewind this video. It's literally in the name. But I don't expect you to actually rewind. I mean, what are we in, the 80s? Next thing you'll be cleaning your VCR and putting on some swanky leg warmers. But I digress. A VPC or Virtual Private Cloud is a way to logically separate your AWS infrastructure from other customers. Think about our bees. We want to create a fort around them, our AWS account, and then go further and isolate them into hives. So if we go into the VPC itself, we want to minimize the risk to our most critical infrastructure. And we can do this with subnets or a logical subdivision of our IPs. For example, we want our fighter bees or EC2 instances to be able to access the internet and be accessed from, so we put them in a public subnet. This is done via NACLs, not Sonica NACLs, but Network Access Control Lists. These lists contain IPs which are allowed or denied access to the subnet. They are also stateless, so if you allow something in, you must explicitly allow it out via a rule. Taking our illustration into consideration, you can see we are allowing inbound access on all IPs via the TCP protocol on port 80. And as I mentioned, these rules are stateless, so we need to explicitly add an outbound rule if we want our traffic to be able to return. Now with our Queen Bee or RDS cluster, we don't need to allow access via the internet as it's handled in the application sitting on our EC2 instance. So we make this a subnet that is private. This means it's not visible to the internet and our queen is in safer hands behind her private quarters. Now say you want to go further and protect a single fighter bee or EC2 instance. You can provision a security group for it. Security groups act as firewalls for associated Amazon EC2 instances, controlling both inbound and outbound traffic at the instance level. This fine-grained access is defined by allow rules and look as follows. In this example, we see that we are allowing SQL traffic to a database server, similar to a NACL. The difference being that security groups are stateful, so return traffic is automatically allowed, regardless of any rules. And that's it for VPC in this video. Next up, you'll learn about private links. You've learned about what a VPC is and how you can isolate certain parts of your infrastructure. But how do you secure them further when sending traffic between VPCs? Take our bees as an example. If we have two hives, or VPCs, or VBCs, we'd have to send the bees outside and through the internet if we want them to travel between the two. This is not ideal because who knows what lurks out there. Never fear, as you can utilize an AWS feature called VPC endpoints or private links. This allows you to route your bees through a secure endpoint in one VPC and to another. This means they do not leave your AWS infrastructure and do not go through the internet, resulting in a safer path of travel. Translating all of this to AWS speak, we can see that without private link VPCs, we would need to send traffic through the internet in order for VPCs to talk to each other. However, when you configure a private link, you are indeed allowing traffic to flow directly between your VPCs. Fantastic stuff, I must say. I mean, have you ever seen something so beautiful? One more thing to go over is route tables. When you provision a VPC, it comes with an implicit router. Think of your router at home. You connect your PC to it in order to access the internet, but you can connect multiple devices. In order for the receiving traffic to end up to the right device, it is routed accordingly. Devices can communicate to each other, and thus local routes are possible too. If we think about this in VPC terms, this is called a route table, which contains a set of rules or routes that are used to determine where network traffic is directed. A default main route table is set up for a VPC, and you must associate a subnet with an actual route table. It doesn't have to be the main table, and you can create a custom route table to route traffic accordingly. I recommend reading the information about route tables in the notes, especially since I threw in as many routes into that part, and because Hong hates my South African pronunciation of route versus route. I mean, you could route tables, and a tree has routes. You can also root for your favorite sporting team and eat lots of fruit. Okay, the last one doesn't really count, but she's giving me bad looks from behind the camera, so I think I'll close out right there. Thanks for watching, and see you soon.
Hello, it's Hong again. To improve ability to protect your bee fort, bee citizens, and valuable honey deposits, you as a builder will need to improve ability to identify a potential security threat or incident. Detective controls is a term that describes a continued improvement in monitoring of events and processing of logs that allow for auditing, automated analysis, and alarming. Detective control are an essential part of governance frameworks and can be used to support improvement process of your security operation, a legal or compliant obligation, and for threat identification and response efforts. There's a different type of detective control. For example, conducting an inventory of AWS resources and their detailed attributes promote more effective decision-making, and lifecycle controls to help establish operational baselines. You can also use internal auditing, an examination of controls related to information system, to ensure that practice meet policy and requirements, and that you have set the correct automatic alerting notification based on defined conditions. These controls are important reactive factors that can help your organization identify and understand the scope of anomalous activity. So your mission in the next two videos is to understand how to implement detective control by processing logs, events, and monitoring that allow for auditing, automatic analysis, and alarming. That's it for now. This video will self-destruct in 5 seconds. Well, it's not working. Let's just move to the next video then.
You're probably producing lots of honey by this time and want to ensure that everything is operating smoothly in your colony. This means auditing who's doing what is being done, and are there ways to improve security and compliance across the board. Essentially, you're inspecting your infrastructure and service usage to make sure that nobody is winging it in your system. The first AWS service that we will explore is called AWS Cloud Trail. It enables you to see who is doing what in your AWS infrastructure. You can track user usage of the console API calls, AWS SDKs, command line tools, and other AWS services themselves so that you know who is interacting with your infrastructure. The best part is that it's enabled by default. And you can view your account activity for the past 90 days right in the CloudTrail console. How cool is that? This allows you to see who is interacting with specific components in your system and can therefore help you trace an errant change, or maybe find out who's been taking data out of your S3 bucket without permission. You can even go further and direct CloudTrail events to Amazon S3, Amazon Cloudwatch events logs, and events. This allows you to perform analysis, archive events, and even remediate on an unexpected change. As a best practice, we recommend looking into this service early on in your AWS journey, as you can build in safeguards and auditing so that if you ever need to produce the data, you'll have it ready for auditors. Next up is AWS Config, which is an auditor's dream for configuration management. This fully managed service records your AWS configuration, changes to that configuration, or a history if you want to think about it, and even change notifications so you're notified proactively. Say you've configured all your AWS resources, but since you've got a whole team of busy bees, you might not know who's been configuring what across the team. Fire up config and it will discover these existing AWS resources and generate a full inventory along with all the actual configuration details for you. You can then determine how a resource was configured at any point in time. You can even tie this into the aforementioned AWS CloudTrail so that you gain full visibility into who made the actual change at that point in time and what the change was. For example, say we configured a custom rule to check if an S3 bucket should have non-public access. We can then trigger that rule whenever a change is made, i.e. change triggered, or we can run it in a periodic fashion, like say every 1 or 6 hours. If that rule picks up that public access has been enabled, we can execute a LAMBDA function to go in and correct access to non-public. The next service we recommend is called Amazon Inspector. This inspector gadget kind of helps you improve security and compliance of your AWS deployed applications by running an automated security assessment. This way, you can avoid a penny for your thoughts and instead use the brain built into Inspector itself to check on deviations of security best practices, exposure of EC2 instances, even vulnerabilities. The service consists of 3 parts: a network configuration reachability piece, an Amazon agent which can be installed on EC2 instances, and a security assessment service that brings them all together. It works by running an assessment based on your specific configuration choices and then outputting a list of findings for potential security issues. The resulting findings are displayed in the Amazon Inspector console, and they are presented with a detailed description of the security issue and a recommendation on how to fix it. Additionally, you can retrieve findings through an API so as to go towards the best practice of automating your remediation processes. I mean, wowza, that's pretty cool. This means you get all the info in a ready-to-consume fashion in both avenues. Kinda way to go, Inspector Gadget. The last service we'll touch on in this video is called Trusted Advisor. This service assists you in provisioning your AWS resources using best practices. It then produces a report under 5 different categories: cost optimization, performance, security, fault tolerance, and even service limits. Once you run Trusted Advisor, you will be presented with a report that you can then drill down into. Each category will produce traffic light-based recommendations. These go in increasing severity, where green means no action recommended, orange for investigation needed, and red for action recommended. Since we're diving into security in this course, I want to highlight some of the best practices that are scanned and reported on in the security section itself. Some of these include S3 bucket permissions, so whether you can actually access a bucket publicly or privately. Security groups, whether your ports are unrestricted, so you can go in and configure rules to close those actual loops. IAM use, so usage of users, roles, policies, and so forth. This is sometimes a mind bender to figure out kind of the correct way to provision your IAM resources, but stay the course and you'll be guided by this report if you are lost. We've also got MFA on root account, so that's whether you're using a multi-factor authentication tool on your root account itself. Exposed access keys. Make sure your access keys are not hard-coded somewhere. And IAM password policies. Rotation of passwords is pretty important, so make sure that you do not let your credentials become stale. It should also be noted that some of these checks are free and some incur a cost. So, for a complete list of checks, check out our resources section. And again, thank you for watching and see you soon.
Oh, hi. So glad you decided to accept the mission to implement monitoring as a part of detective controls. Hope your detective instinct is still buzzing. So what on earth is monitoring? Oh, wait, we're not on Earth, we're on Mars, remember? Anyhow, monitoring is to collect, track, and display data and statistics related to your IT infrastructure. In AWS Cloud, there are multiple available services and tools to help you monitor AWS resource and application. So let's start with Cloudwatch. Amazon Cloudwatch is basically a metrics repository. An AWS service, such as EC2, puts metric into the repository and you retrieve statistics based on those metrics. If you put your custom metric into repository, you can retrieve the statistics on these metrics as well. Oh, and the best part is, when a certain metric crosses the threshold that you set up, Cloudwatch can generate an alarm. An alarm watches a single metric over a specific time period and performs one or more specific actions based on the value of the metric relative to a threshold over time. The action is a notification sent to an Amazon SNS topic or an auto-scaling policy. For example, you can use CloudTrail to monitor activity related to changing an EC2 security group and trigger Amazon Cloudwatch alarm when configuration changes happen. Also, don't forget that you can use Cloudwatch logs to monitor, store, and access your log files from multiple sources. Let me share with you some use cases for using Cloudwatch logs. The first use case is to collect and store application logs and server operation system logs. Another use case can be to use CloudTrail to capture API activities and send them to Cloudwatch logs. Also, you can log Route 53 DNS query into Cloudwatch logs. And you can use Cloudwatch logs to retain and archive log data in S3. And lastly, you can use Cloudwatch Log Insight to interactively search and analyze your log data. That's it for this video. See you soon. You know, as our BMARs are getting more popular, more and more bad aliens out there are secretly looking for a weak spot in our infrastructure. As we're getting smarter in running and securing BMARs, we want to use automation and machine learning to detect and react to suspicious events happen to our environment, which can be caused by bad aliens. And that's why we need to talk about Amazon Guard Duty. Amazon Guard Duty is a threat detection service that continuously monitors for malicious or unauthorized behavior to help you protect your AWS account and resource. This service uses machine learning, anomaly detection, and integrated threat intelligence to identify and prioritize potential threats. Guard Duty analyzes tens of billions of events across multiple AWS data sources, such as AWS CloudTrail, Amazon VPC flow logs, and DNS logs. You can aggregate Guard Duty findings across multiple accounts. You can also integrate Guard Duty with AWS Cloudwatch events or your current event management system to alert your security team, aka the Sheriff Bees. Amazon Guard Duty provides 3 severity levels, low, medium, and high, to help you prioritize response to potential threats. A low severity level indicates suspicious or malicious activity that was blocked before it compromised your resource. A medium severity level indicates suspicious activity. For example, a large amount of traffic being returned to a remote host that is behind a hidden network. A high severity level indicates that the resource in question is compromised and it is being actively used for unauthorized purpose. An example of this could be that an EC2 instance has been compromised or a set of IAM user credentials has been stolen. Ooh, bad actor. So, now you can use GuardDuty to detect threats. How about responding to these findings? Amazon GuardDuty offers HTTPS APIs, CLI tools, and Amazon Cloudwatch events to support automatic security response to security findings. For example, let's say GuardDuty detects an EC2 security group that accepts traffic from everywhere in the internet. You can automate the response workflow by letting GuardDuty sending the findings to Cloudwatch event as an event source to trigger an AWS LAMBDA function to update the security group. So, are we done yet? Not really. Let's talk about how you can see all the security alerts and compliance status across AWS account in one central place. Entering Security Hub. With Security Hub, you now have a single place that aggregate, organize, and prioritize your security alerts or findings from multiple AWS services, such as Amazon GuardDuty, Amazon Inspector, Amazon Macy, as well as from AWS Partner Solutions. Your findings are visually summarized on integrated dashboard with actionable graphs and tables. You can also continuously monitor your environment using automatic compliance check based on the AWS best practice and industry standard that your organization follows. So that's it for this week, folks. I'll see you again next week.
Hello, Space Explorers. Are you ready to blast off with an AWS Config demo? If you are, good news, we're about to start. But before we dive into the config console, we gotta create an S3 bucket to store our config data. So you can see I've got the S3 console open here, and I'm going to create a bucket. I'll give it a name. So this is Buzz Bucket. If you note, the bucket must be a unique name. So we've got Buzz Bucket here. You can see that it's telling me that I have to be wary of the case too. So let's just change that to all lowercase. Buzz Bucket. We will click next. Oh, the name exists already. See, that's how I'm saying it needs to be unique. So let's do the Buzz Bucket 123. Click next. We're gonna go down here. Everything looks good. We're gonna block public access. And in this case, I wanna say yes. I wanna grant Amazon S3 log delivery to write access for this bucket. So I click next. Again, I'm going to create the bucket now. So you can see we've created our bucket now, and we actually need to go in and create a service role for config to use. So let me click on services. I'll click on IAMs or identity and access management, and I'm going to create a role now. So if I click on roles, I'm going to create a new one. In this case, we're using an AWS service, so AWS config. Kind of look for it here on our console. There it is. We're going to make it customizable. So we'll click next on the permissions. You can see it adds a default policy here. We want to go to tags, put in our bmars tag, click next, give that role a name. So let's call it Buzz Role. And we're going to create the role. Now I'm actually going to go back into that role because I want to add additional permissions so that AWS config can read and write to S3. So I've clicked into that role and I'm going to attach another policy. In this case, it's the S3 one, and you can see I'm searching for it under filter policies. I select Amazon S3 full access and click attach policy. And now we've got the correct policy. We can proceed to the AWS config console. So I've actually got that pulled up here, and I'm going to click on get started. You can see here, it's a few fancy options. We've got the create bucket, but in our case, we're going to choose the bucket that we created. And that was called Buzz Bucket 123. We're also going to go down here and choose that existing role that we created. in this case, Buzzroll. We're going to click Next. And you know what? Let's add one of these default rules here. Let's do auto-scaling ELB health check. We'll click Next, confirm everything is A-OK, and click Confirm. Cool, and you can see that we've created our AWS Config configuration. We can also add rules. So in this case, I'm going to click Add Rule, and for argument's sake, I'll pick this one here for access key rotation. So you can see that takes me to the rule itself with default values populated. In this case, we'll keep it at periodic checks, and let's change the frequency to 3 hours. You can also choose your remediation action here, and you can click Save. I'm showing you kind of default values, but when you go in, you're going to set up LAMBDA triggers and so forth. And you can see that my rule has been created, and right now there are no resources in scope. So it's as simple as that to kind of set up your AWS config configuration. And in our case, maybe the next rule we'll create is to make sure our spaceships are maintaining their orbit around the red planet. So thanks for watching, and hope to see you soon.
Hi y'all, I'm glad you're still buzzing along in week 3. Where last week introduced a lot of services that you can use for your infrastructure security, this week will be more about methodology. Our focus this week is data protection, and we're going to look at this in a number of ways. You'll get information about types of data, encryption in transit, encryption at rest, ways to work with data-centric services more securely, and more. Data is our most valuable resource in the cloud, so make sure you are really diving into ways to implement the things discussed this week. And as always, keep going through those course notes for some great additional information.
Hey there, I'm Rudy, but since I'm in a bee suit, you can call me Buzzy for today. And phew, have I been quite the busy bee the last few days. Our colony is shaping up more and more as we deploy infrastructure to the Martian surface. We are therefore generating lots of data, and we need somewhere to store it. We could just archive it, but that's only if data is not needed immediately. So what are the options of securing our data for the busiest of bees? Well, firstly, we should revisit the notion of least privileged access. What this means is that you should only provide the minimum required permissions for users of your AWS resources. These users could be infrastructure users, end users, busy bees like myself, or even AWS services themselves. For example, if we needed a LAMBDA function to pull out some info from an S3 bucket, it would need read access to that bucket. Similarly, if the data was stored in an Amazon Dynamodb table, we would provision read access to the relevant table. One of the main reasons we do this is to prevent exposure of critical data to unwanted parties. I mean, we could have our honey stored in Dynamodb, but maybe an alien is trying to access it using compromised credentials. We are also trying to prevent accidental creations, reads, updates, or deletes. This is also known as CRUD functions. Another thing to consider is the access frequency of data. Does it need to be accessed quickly or less? Does it need to be stored for days, months, or years? And even what type of data you are storing. Are you storing objects, rows, time series data, or any of the other types? As a starter guide, if you're looking to store objects, you can use Amazon's Simple Storage Service, or S3. S3 allows you to make data accessible over the internet. And as the most cost-effective storage mechanism offered by AWS, you can even store log files or archive data to S3. Speaking of archiving, if you don't need this data in a hurry, then you can archive it to Amazon Glacier, which lowers your cost even more. Better yet, you can set up lifecycle policies to archive data automatically after a certain period. So if you needed the data to be in S3 for 30 days, then you set up the policy to automatically move it or archive it to Glacier after those 30 days. The next thing you'll probably be looking into is storing data for your applications, user-generated data, and have relationships between those data sets. Thus, you're looking for a relational database, and there are various ones offered under the Amazon RDS or Relational Database Service portfolio. Some options include Postgres, MySQL, and even commercial offerings like Oracle and SQL Server. For those of you who want a more performant and cost-effective database, we recommend Amazon Aurora, which comes in two flavors, MySQL and Postgres. The MySQL version is up to 5 times more performant than standard MySQL, and the Postgres version is 3 times more performant than standard Postgres. For a full feature comparison, you can check out our resources section. But you know what? Not all applications require relational databases, and therefore we offer a non-relational or NoSQL alternative called Amazon Dynamodb. This key value database store offers single-digit millisecond access times and can scale up and down automatically. As an added performance gain, you can attach Amazon DynamoDB Accelerator to your DynamoDB tables, which is an in-memory cache which lowers the response time to microseconds. That is lightning fast. Ka-chow! Speaking of speed, pop quiz, hotshot. Welcome back. I hope you got the correct answer. I mean, how could you not get it right? The answer was clearly B. 3 other mentions for databases are our time series optimized database, aptly called Amazon TimeStream, and fully managed ledger database called Amazon Quantum Ledger Database. And last but not least, Amazon Neptune is our graph database service. So instead of leaping between options, you can now go straight for home and use one of these database options in your applications. Apart from databases, you might recall we rolled out some EC2 instances throughout our planetary endeavor. These EC2 instances are generating data and we need a place to store it. The first option we have is Amazon Elastic Block Store, or EBS, which is used for writing block storage. These are automatically replicated within availability zones and offer a non-transient option for EC2 instance storage. With EC2 instances, if you usually stop them, you're going to lose anything that was on the instance store itself. However, if you attach an EBS volume, that data is retained even when shutting down that instance. The second option for storage is Amazon Elastic File System, or EFS. And as the name implies, it's used if you need a file system attached to your EC2 instance. It's fully managed and can automatically grow or shrink depending on whether you add or remove files. For secure data warehousing, we recommend Amazon Redshift, which allows you to store your data in a columnar format. This, along with parallel query execution, means you'll get results up to 10 times faster than other solutions. As an added option, you can even access data stored in S3 via a feature called Redshift Spectrum, thus allowing for even more data to be queried to ensure accurate and up-to-date results. And for those of you wondering if you have to use Redshift for data warehousing, the answer is a most resounding no, you don't. You can use a service called Amazon Athena, which will scan data housed in your Amazon S3 buckets via standard SQL queries. It's a serverless offering, so there's no infrastructure to manage, and the cost is associated with the amount of data you scan, coupled with the query execution duration. But this kind of sounds like we're going into data lake territory here. And you know what? Customers kept telling us they were setting up their own data lakes as a priority, but they weren't sure how to kind of set it up. So we listened and created AWS Lake Formation. And AWS Lake Formation allows you to do that data lake setup in mere days. One of the last few service areas to touch on are our AWS data transfer options. I mean, since we're on Mars, we have no idea what the Wi-Fi is like, and if there's even enough bandwidth to copy terabytes of data to the AWS Cloud. This is where AWS Snowball comes in. It's a portable device and can store petabytes of data. Data is copied over to the device with encryption, and it ships out to us at AWS. Once we've copied it to your account, you'll get notified of its availability. And if petabytes aren't enough, we offer an actual truck to move exabyte scale datasets into and out of AWS called AWS Snowmobile, I mean, this thing is huge. But before I digress into the intricacies of trucking solutions, I'll mention the offerings I described have various encryption options to further secure your data, and that you can control those secure keys as well. We'll touch upon those in subsequent videos. If you want to learn more, check out our resources section for a link to a nice matrix of AWS storage options. I mean, we can lead you to the door of these solutions, but only you can open it. Thanks for learning about available secure storage solutions. And remember, there can be only one. Well, actually, there are several, but till next time, Shlala Gashle, goodbye, cheers.
Hey, bee lovers and space explorers! Just as honey is so important to a bee, customer data is very important to your application. Handling customer data without thinking ahead on how to secure it can impact credibility of your organization and your company. As bee citizens are more connected because we bring the internet to Mars, more applications and systems on Mars are producing data, storing data, and exchanging data. In this video, we are focusing on how you can reduce the risk of unauthorized access or exposure of customer data when it's in transit between system and service. The first thing to do is to define requirements for data protection in transit. Based on legal and compliant requirements, you classify data into multiple categories, which is dependent on sensitivity level of the data. Then you apply encryption standards to the right category. For example, historical weather data is considered public data, so you don't have to require encryption in transit when working with this data. However, customer credit card information is highly confidential data, thus you want to make sure it is encrypted in transit. You also need to authenticate network communications. So that includes verifying the identity of communications by using protocol, such as Transport Layer Security, or TLS in short, or using IPsec. Internet Protocol Security, or IPsec, is a protocol for in-transit data protection between hosts. It is a protocol to protect communication at the network layer, which is layer 3 of the OSI model. IPsec can be implemented when you set up virtual private network, or VPNs, to create a secure connection between your VPC and on-premises network. Transport Layer Security, or TLS, is a set of industry-standard cryptographic protocols used for encrypting information at the transport layer, which is layer 4 of the OSI model. TLS is the successor of Secure Sockets Layer, SSL, but SSL and TLS use X509 certificates to authenticate the server. Both SSL and TLS negotiate a symmetric key between the client and the server that is used to encrypt data flowing between two entities. You should use HTTPS instead of HTTP for data transmission. HTTPS uses the SSL TLS protocol to prevent eavesdropping, unauthorized alterations, and unauthorized copying of your data. All AWS services provide API endpoints that allow you to establish secure HTTPS communication sessions. For your web application, you can choose to terminate the encryption at the application layer or at the load balancer layer. You want to make sure you store the X509 certificates securely and rotate them with strict access control. The good news is you can use AWS Certificate Manager, or ACM, to do this. ACM handles the complexity of creating and managing public SSL and TSL certificate for your website and applications. You can use public certificates provided by ACM, called ACM certificates, or certificate that you import into ACM. That's all I have for this video. Be seeing you soon. Buzz, 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 buzz.
So we've got more hives scattered throughout our colony, and we want to make sure they are all safe. This leads us to the concept of when data is not being accessed, is it secure? One way to secure your Hive data is to lock the Hive away and carry a key with you. This AWS concept is called encryption at rest, and there are two services we're going to touch on here. Think about your key. Do you want to manage it, or do you want AWS to manage it? Do you want it to also be created by AWS so that you can let us do the heavy lifting of generating new keys on a fixed schedule? These kinds of questions lead us to Amazon Key Management Service, or KMS, which will allow you to easily manage the encryption keys used to encrypt your data. The primary resource here is called a customer master key, and you use that to encrypt and decrypt up to 4 kilobytes of data. These CMKs can be managed by you, which will give you full control of them. You manage everything from rotation to deletion, IAM policies, and so forth. The other type is AWS managed, and these are created, managed, and used on your behalf by an AWS service that integrates with KMS. Both of these types live in your AWS account, whereas the third type, called AWS owned, lives outside your AWS account. Think of them as part of a collection of CMKs that AWS owns and manages for use in multiple AWS accounts. AWS services can use AWS-owned CMKs to protect your data. But what if your company wants you to manage these keys using dedicated hardware? Well, that's no problem, as the second service we're going to cover is AWS Cloud HSM, or Hardware Security Module, and it accomplishes just that. Cloud HSM is a cloud-based hardware security module that enables you to easily generate and own encryption keys in your AWS account. This helps you meet corporate, contractual, and regulatory compliance requirements for data security by using that dedicated hardware. Let's conclude this video with a short demo on how to create a KMS key. Hey there students, it's Rudy again, and we're here to talk about KMS. Specifically, we're going to give you a little demo. And in this demo, we're going to show you how to create a KMS, or Key Management Service key. And these, if you remember, are used for encrypting and decrypting your AWS data. So let's get started and navigate to the KMS console. You can see that I'm logged into my AWS Management Console, and conveniently under my recently visited services, I've got KMS. I will click there. You can see I don't have any keys right now, so I'm going to click Create Key. I'm going to give it a snazzy name. Let's call it Gatekeeper. And we'll say it is the compatriot of the key master. So we'll click Next. And we'll add some tags. In this case, our mission is called BMARS, so we're going to add that tag or set of tags. And now we're going to define key administration permissions. So these are users that can perform administrative tasks on your key. In this case, we're going to choose Buzz because it's his key. We'll click Next. Next up, we're going to define key usage permissions. That's very similar to the previous screen, but you will now select the users and roles that can use that CMK you are creating to do the actual encryption and decryption. So I'm going to select Buzz again, and I'm going to click Next. You can see we can review and edit our policy inline if needed, very similar to IAM policies in the case that it's JSON based. So everything looks good, and I'm just going to click Finish right here. Wow, that was quick. I mean, congrats, you just created your first KMS key, and you can now use it in your account. Thanks again for tuning in, and don't touch that dial as we're going to get more fun content dialed up in a jiff. Thanks for watching, and have a good rest while we decrypt the next video. Actually, not just yet, as you have a short quiz to complete, which is key to your success. I mean, so many puns, so little time. See you soon.
Now, let's say you need to retrieve honey from the Bee Galactic Reserve. This bank is the most secretive bank on Mars, where bees store their valuable honey. The Bee Galactic Reserve stores a database of honey transactions in a private subnet of the VPC. To get there, you will need to send your request to the load balancer, which will distribute your request to one of the web servers. The web servers, after validating the request, will send it to an internal load balancer to distribute your request to the application servers. This application server will then talk to the database of honey transactions to get information about you and your honey, such as how much honey are you allowed to withdraw per day. Now, if you look at the process, you see that the load balancer and the web servers are in public subnet that allow requests from the internet. And the internal load balancer and application server will be in private subnet and only allow requests from the web server. Also, the database is placed in private subnets as well, and will only take requests from the application servers. This architecture is to make sure the internet doesn't have access to your database. Depending on the data classification, sometimes running our database in VPC's private subnet isn't sufficient. For example, if you handle data related to customer credit card information, then encrypting data address is essential to prevent data leaks. In this video, we talk about how you can encrypt data stored in AWS database services. For SQL lovers, you may already have heard or know about AWS Relational Database Service, or RDS. It is a managed service that makes it easier to set up, operate, and scale a relational database in the cloud. You can use SSL from your application to encrypt a connection to an RDS DB instance running Amazon Aurora, MySQL, MariaDB, SQL Server, Oracle, or Postgres. Each DB engine has its own process of implementing SSL. In case you are wondering, Amazon Aurora is a relational database service which features a distributed, fault-tolerant, self-healing storage system that can auto-scale up to 64 terabytes per database instance. The best part is, it is compatible with MySQL and Postgres database engines. You can encrypt your Amazon RDS DB instance and snapshot address by enabling the encryption option when you create Amazon RDS DB instance. RDS encrypted DB instance use the industry standards AES 256 encryption algorithm to encrypt your data on the server that hosts your DB instance. So, what will be encrypted, you ask? Data that is encrypted address include the underlying storage for a DB instance, its automated backups, the read replicas, and snapshots. To manage the keys used for encrypting and decrypting your RDS resource, you use AWS Key Management Service, or KMS in short. When you create an encrypted DB instance, you supply the KMS key identifier for your encryption key. If you don't have your own key, KMS will create one for you. What if you choose to use NoSQL database? Then it's time to talk about AWS managed NoSQL database service called Dynamodb. The good news is Amazon Dynamodb encrypts all user data stored in Dynamodb table by default. Server-side encryption address is enabled for all Dynamodb table data and cannot be disabled. You cannot encrypt only a subset of items in a table, though. When a table is encrypted, all the data includes its primary key, index, stream, global table, backups will be encrypted. Encryption address integrate with AWS KMS for managing the encryption key that is used to encrypt your tables, and you can switch between keys. Check out our resource area for further details and documentation. That's it for now. Be seeing you.
So we've swarmed you with mentions of Amazon S3 throughout this course, but how does one secure S3? Well, you'd want to consider things like only allowing bucket access to authorized parties. And if you don't need public access, make sure it's disabled for a bucket. Or maybe you want to add encryption to the equation. But wait, what is S3 again? And what's a bucket? And how do we prevent them from having holes? Simply put, Amazon S3 is cloud storage for the internet. And think of a bucket as a literal bucket where you can add, remove, or update objects. To upload your data, whether they be photos, videos, documents, you first create a bucket in one of the AWS regions, and then you can upload objects to it. But we're talking about securing those objects, and the first thing you can do is set up bucket policies. A bucket policy is a resource-based AWS identity and access management policy, which means that you designate access permissions for the bucket and the objects in it. So if you want a user to be able to read from a bucket, then you provision the relevant policy. Going even more fine-grained, you can dictate permissions for individual objects. But as a best practice for managing a whole bucket, we recommend enabling default encryption on the bucket itself. This means that all objects in that bucket will be encrypted, and that encryption can be centrally managed at the bucket level. Objects will be encrypted using server-side encryption with either Amazon S3 managed keys, that's SSE-S3, or AWS KMS or Key Management Service managed keys, SSE-KMS. Also, it should be noted that you do not incur extra charges for using default encryption for your S3 buckets, but you will be charged for the encryption keys themselves. For more information on the different encryption options and pricing for key storage, please check out our resources section. The last service we'll cover is called Amazon Macie, which is for those of you who like the managed option of securing your S3 bucket. Well, managed in the sense that Macie uses machine learning to automatically discover, classify, and protect sensitive data in AWS. That means Amazon Macie will automatically recognize your sensitive data, such as personally identifiable information or PII, even intellectual property, your IP, maybe even honeycombs. You'll then be provided with alerts on areas of interest, along with a dashboard giving you insights into how your data is being accessed, moved, and modified. Some of the things that Macie checks for are inadvertent exposure of data, insider threats, and targeted attacks. You can then alert on suspicious activity such as compromised user accounts and downloading of large amounts of sensitive content from unusual IP addresses, or maybe the download of a large quantity of source code by a user account that typically does not access this type of sensitive content. I mean, we don't want our secret honey formula stolen. For a list of Macie's features, please check out our resources section. Thanks for following along and learning how to secure your simple storage service, or S3. It's been fun, and I hope you enjoy our upcoming videos.
Welcome back, folks. This video is to discuss about encryption address for Amazon Elastic Block Storage, or EBS in short. EBS provides persistent block storage volume for use with Amazon EC2 instance in the AWS Cloud. Amazon EBS is designed for application workload that benefit from improving performance, cost, and capacity. Typical use cases include big data analytics engine like Hadoop, relational and NoSQL database like Microsoft SQL Server or MongoDB. Another use case can be stream and log processing applications such as Kafka and Splunk. And another use case would be data warehousing application like Vertica and Teradata. When you need to encrypt data in an EBS volume, The solution is straightforward. You can configure your AWS account to enforce the encryption of new EBS volume and snapshots. That means new EBS volume will be automatically encrypted when you create them. EBS provides features to back up data in EBS volume to S3 by taking point-in-time snapshots. When you create encryption by default, these snapshots will be encrypted as well. EBS volume encryption doesn't require you to build, maintain, and secure your own key management infrastructure. Instead, it uses AWS Key Management Service, or KMS, when creating encrypted volumes and snapshots. For existing unencrypted EBS volume, you can create snapshots for the volumes and create new encrypted EBS volume from the snapshot using Create Volume or Copy Snapshot API action. When you create an encrypted EBS volume and attach it to a supported instance type, the following type data are encrypted. The first one is, of course, data address inside the volume. Then, all data moving between the volume and the instance will be encrypted. All the snapshots created from the volume will be encrypted as well. And all the volume created from those snapshots also encrypted. Encryption operations occur on the servers that host EC2 instance, ensuring the security of both data address and data in transit between an instance and its attached EBS storage. Amazon EBS encryption is available only on certain instance types. You can attach both encrypted and unencrypted volumes to a supported instance type. Remember, you can check out the weekly resource section for further details. That's it for now. Space travelers, happy building! Hey, what's up? How are your bees feeling today? Let's say we have 2 AWS accounts, including one production account that has data stored in S3 and one testing account for testing purpose. Now, we are tasked to create cross-account access so that the IAM user on the testing account can access data stored in S3 in the production accounts. You can delegate access across AWS accounts using IAM roles. Let me show you how to do it. So in this demo, I created an S3 bucket called cross-account home in production AWS account. And if I click on the cross-account home bucket, I can see that there's a 2 file that I uploaded earlier, which is a picture of my puppy. So how do you grant access from a different AWS account to this S3 bucket? The very first thing you need to do is to go to permission and update the bucket policy. In this case, I updated the bucket policy earlier. You can see that for the IAM policy, I put in the principal as the ARN of the IAM user test account home from the testing account. So this IAM user is from totally different AWS account. I granted them the access to get object or put object ACL. So now let's look at the IAM user test account home to see how we can grant access to that account. I am in the IAM console of the testing account, and I click on the user test account home to see the policy associated with it. So to grant access for the S3 bucket in a different account, I need to give this IAM user permission to access that S3 bucket. And I create a policy called cross-account access S3. If I click on it, it will show me that this policy have allow effect that will allow me to get object, put object, put object ACL, or list the bucket. and the resource that I am allowed to perform this action is the cross-account Hong S3 bucket. Alright, so now we have the IAM policy in place. Let's do a short demo to see how the IAM user can retrieve the file in the S3 bucket. So I have a terminal open. As for now, let's run an S3 CLI command to retrieve a picture stored on S3 bucket. So now we successfully download picture from my S3 bucket. Let's actually see if the picture is what I want to download. And yep, that is my pup. So thank you for watching. I'll see you again in the next video.
It's finally week 4, and you've really blasted through. Now it's time to talk about securing your application. A lot of this is going to come down to protecting your resources, protecting communication to and between those resources, and protecting your secrets. Everything has been going really well so far, so just keep buzzing through to the end. Good luck on completing your mission.
Hey folks! So glad you can make it to the last week of this class. As we went through multiple cloud security concepts, we haven't dived into how you can protect your compute resource. Let's do it right now. The first service that we want to talk about is Amazon EC2. You control the operating system, and you configure and operate any identity management system that provides access to the EC2 instance. AWS will be responsible for protecting the hypervisor and the EC2 instance isolation. To secure EC2 instance, there are several best practices that we recommend. The first thing to do is to restrict access at the network and the OS layer. You can leverage security groups as the primary mechanism for controlling network access to EC2 network interface. You can also use network ACLs as a secondary control for denying a specific subnet of traffic or providing high-level subnet guardrails. On the instance itself, you should only install necessary packets for your operation system and applications. It is also recommended that the SSH key used to log into the EC2 instance need to be secure, and providing interactive access to EC2 instance should follow the least privilege model. Secondly, controlling the API access coming from EC2 instance is important. When your application runs on EC2 instance need to access other AWS services, you should use IAM roles to grant permission for the instance to make API calls. Using IAM roles eliminates the need to distribute and rotate long-term credentials on EC2 instance. Next, look at applying chain management and configuration management to control and monitor chains for EC2 instance configurations. We recommend to regularly scan and install missing patch for your instance. This is when AWS System Manager can help you to automate process around patching Windows and Linux EC2 instance. And last, apply security monitoring and auditing for EC2 resource and your account. This will include enabling AWS Cloudfront to capture API calls, which will enable AWS Config to audit and track chain made to your EC2 resource. Now, if you choose to run application in Docker containers, there are several container management and orchestration services available. Those services include Amazon Elastic Container Service, or ECS, Elastic Container Service for Kubernetes, also called EKS, and AWS Fargate. You can also run your containerized application on AWS Elastic Beanstalk as well. You'll maintain control over the container environment, the operation system, and the underlying EC2 instance when using Amazon ECS and EKS. For Fargate, you will not have access to the underlying compute resource. However, you will have control over the container environment. ECS, EKS, and Fargate lets you use IAM role to control requests from the application running on container to other AWS services. For example, you store a secret in an S3 bucket. To retrieve the secret, your containerized application run on ECS need permission to read the secret in S3. Thus, you create an IAM role and attach it to the container so that it can read the secret. Another compute service that we should talk about is AWS LAMBDA. AWS LAMBDA automatically runs your code without requiring you to provision or manage servers. You just write the code and upload it to Lambda. AWS will manage the underlying infrastructure and foundation services, the operation system, and the application platform for Lambda. You are responsible for the security of your code, the storage and accessibility of sensitive data, and IAM to the Lambda service and within your function. Each Lambda function runs in one or more dedicated execution environments that are used for the lifetime of the function, and then it will be destroyed. So you can use Cloudwatch and CloudTrail to monitor and audit your Lambda functions, and you can also track configuration changes to the Lambda function using AWS Config. That's it for this video, folks. Hope your inner bees will be inspired to check out this AWS Compute service. As always, don't forget to take a look at the resource section of this video to learn more about how to secure your compute resource. Ciao!
As part of securing your workloads, you need to protect your application endpoints. These endpoints are more than likely the ones that end users go through to interact with your application, and therefore it's critical to protect them. If we look at the traditional server-based infrastructure model with, say, an EC2 fleet, and as a reminder, EC2 is the computational building block at AWS, where you can choose specs such as memory, disk space, and OS, and then spin up an EC2 instance itself. You can start with one, and then you can scale out horizontally, even vertically, to have a whole fleet of servers. When you deploy fleets, you're going to spread the traffic across them like honey, in that you want sticky sessions. And a way to achieve this is with an AWS service called the Elastic Load Balancer. There are a few different types, with the two notable ones being the Application Load Balancer, or ALB, and Network Load Balancer, or NLB. The ALB operates on the individual request level, or layer 7, and the Network Load Balancer operates on the connection level, or layer 4. If you'd like to learn more about these load balancers, please make sure to check out the resources section. In our example, we're using the NLB, and you can see that we're load balancing traffic across our fleet using a round-robin algorithm, which rotates traffic in order between the instances. Our fleet hosts a website, and since we want to secure it by default, we require that the traffic is always transported over HTTPS. HTTPS in this case is a secure extension of Hypertext Transfer Protocol, or HTTP, and means that requests will be encrypted and decrypted. In order to achieve this on our EC2 instances, we route the encrypted traffic through the NLB and then terminate them on the instances themselves. Requests will then be decrypted on the instances, and the application can proceed further. This is a recommended practice for securing traffic to your EC2 instances, but it does incur a small performance impact for the actual decryption and encryption. So can we improve upon it? Of course we can. By using the NLB, we can terminate our HTTPS traffic on the load balancer itself, which will free your EC2 servers from the compute-intensive work of encrypting and decrypting all of your traffic. You also get some added benefits like simplified management, access logs, and improved compliance. For a full list of these benefits, check out our resources section. The next service we'll cover is called API Gateway, where API stands for Application Programming Interface. It's a fully managed service which allows you to create, publish, maintain, monitor, and secure APIs at any scale. By using API Gateway, you can expose certain application logic via REST or even WebSockets. In essence, you're only allowing access to needed parts of your application, and therefore you're not opening, say, your backend for the whole world. This notion of protecting your backend and other critical systems, such as your database, is a best practice for any architecture, and we highly recommend it when designing your next workload. Now say we're exposing a create Bee Hive API call via our API gateway. How do we make sure only authorized users can use it? Well, you can add optional authorization processing, such as AWS Signature version 4 or SIG-v4, even LAMBDA authorizers. SIG-v4 works via AWS credentials, these being your access and secret keys, which authorize access by signing those requests to your service. When you create your API gateway service call structure, you essentially generate a custom SDK for your service. And this custom SDK will handle the signing for your requests. If you don't want to use permanent credentials, you can even use Amazon Cognito to retrieve temporary role-based ones so you can make calls to your API. The other option for securing your API gateway is via custom LAMBDA authorizers, which are actually AWS LAMBDA functions. And as a reminder, LAMBDA functions are the serverless compute offering on AWS and allow you to write your code as reusable functions in a language of your choice. We have several officially supported languages, such as Java, Ruby, Python, even Node.js, but you can include any language via custom runtimes. Now, these functions are executed in response to demand, so they can scale up and scale down as demand varies, with a maximum execution duration of 15 minutes. For a full explanation of AWS Lambda, please check out our resources section. Lambda authorizers determine access to APIs using a bearer token strategy, such as Open Authorization or OAuth, which is an open standard for token-based authentication and authorization. This means that if a Lambda authorizer is configured, API Gateway calls the Lambda function with the incoming authorization token, and depending on the strategy you implemented, it will return IAM policies which are used to authorize the request. If the policy returned by the authorizer is valid, API Gateway will then cache the policy associated with the incoming token for up to 1 hour. And that's how you can secure your API Gateway. But that's enough of this for you busy bees. Thanks for watching, and hopefully you learn more about securing your AWS endpoints. I mean, after all, wasn't that the point of this video? Okay, my producers in the back are cringing, so I'll bid you adieu until next time.
I have a secret to tell you. You can store secret in Secret Manager. In the past, where your application would retrieve information from a database, you typically had to embed the credentials for accessing the database directly in the application. These database credentials can be defined as a type secret. They need to be carefully stored and handled. Other secret types can be password, third-party API key, and even arbitrary text. Handling of these secrets can be an important task in any infrastructure that requires secure handling and protection from unauthorized access. You also want to rotate your secret frequently to avoid things like stale credentials from being used against you. And keep in mind that your secret will need to be encrypted at rest and in transit. A best practice is never to lock the secret in system logs or application logs. Be careful about including debugging or locking statement in your code. You want to ensure that this login or information doesn't include any of the sensitive data that's stored in encrypted secret value. AWS Secret Manager is an AWS service that makes it easier for you to manage secrets. In short, AWS Secret Manager allows you to handle access to secrets without a need to store them locally on any instance or server or in any containers. It gives you the ability to have a centralized storage for the secret and provide direct access to only the necessary components. So the way the secret manager works is, step 1, an admin create or retrieve the secret. In this example, the secret are database credentials. Step 2, the admin then store the credential in secret managers and limit access to only the necessary user. Here, the user is a custom application running locally. Step 3, the application makes a call to secret manager using its credential that it has from the associate IAM role. And because the admin allowed for the application to have access, the application is then allowed to retrieve the credentials as shown with step 4 over here. Once the credentials are retrieved, they are stored in a non-persistent way, and then the credential can be used to access the database, as we see with step number 5. I hope that gives you some clarity, and in a later video, I'll demonstrate how AWS Secret Manager works. See you soon! Hello, Hong here. In this video, I'm going to do a demo to show how you can create and store a secret in AWS Secret Managers. Let's get started. From the AWS Management Console, you can search for Secret Manager to start using the AWS Secret Manager. On the right-hand side, you can store a new secret. Click on this button, and you have multiple options to create the secret, right? You can choose to create a credential or secret for RDS, for Redshift, for other type database. You can also choose to store an API key. In this demo, we're going to start with creating credential for RDS database. So the credential in this case will be the username and the password for the database admin to log into the RDS instance. In this case, I'm gonna create a username admin, and the password, I can just pick a simple password, right? Test account. But you want to make sure that the password for production database need to be following the best practice, right? That's including special character with the appropriate length. So in this case, I can choose to use default encryption key, which is the KMS key that created in your AWS account. I can choose to use my own KMS key that I created in KMS. I'm just going to stick with the default encryption key. And this is where the magic happens. You can see that Secret Manager automatically pull out the database instance name that you want to associate the username and password with. And I have one test, Aurora DB, which is an Aurora instance available in the same region that I'm storing this secret, with a Oregon region. So let's click on next. And in this case, it asks you, what is the secret name? In this case, I'm going to name it DB admin. And for the description, I will say username and password for our beloved database admin. Done. Now for tags. Tagging is one of the best practices we recommend for you to control your AWS resource. So in this case, I'm going to tag department, and the value would be IT because we want to control which resource is created by and maintained by which department. Click on next. And this is the fun part. You can choose to automatic rotate your secret and let Secret Manager do that for you. In this case, I'm going to choose enable automatic rotation. You can choose 90 days rotation, 60 days. I'm going to stick with 90-day rotation. And you can use a LAMBDA function to perform the rotation for you. I don't have a LAMBDA function right now, so I'm going to let Secret Manager create a new LAMBDA function for me. And I'm going to name it database admin secret rotation. Awesome. And this Lambda function will be used to rotate this specific secret. Click on next. And now it's just the review, right? We choose to store credential on Secret Manager for RDS database. We choose the default encryption key. We choose to name it as a database admin. And now it's Secret Manager gives you some sample code that you can integrate with your application. So if you look at the Python code, right, it's just like, hey, there's a function called getSecret, so that you talk to the endpoint of Secret Manager to pull out a secret for you in the application. And finally, we click on Store. And bam, here you go. You have a new secret called dbadmin, stored and rotated by AWS Secret Manager. So that's it for now, folks. Thanks for watching.
Wow, can you believe it's been 4 weeks since we started our mission to build a bee colony on Mars? I'm so happy that you stuck with us on this buzzing journey. And as a final piece to the puzzle, let's talk about the well-architected tool. Before we dive into the tool, we have to mention the actual well-architected framework. It is designed to help architects, developers, and users of AWS to build secure, high-performing, resilient, and efficient infrastructure for their applications. It's composed of 5 pillars to ensure a consistent approach to reviewing of architectures and designing for scaling over time. And since this is part of my day job, I'll tell you the pillars right now. It's cost optimization, operational excellence, reliability, performance efficiency, and security. You're probably wondering why I name them out of order. Well, I like to use this handy acronym to remember them. CORPS or CORPS. Now you can be an architect like me too. In the past, you'd need to evaluate these against your AWS infrastructure with the help of a solutions architect. But we listened to customer feedback and decided to release it as a self-service tool. You can now access it via the AWS console, create a workload, and run it against your AWS account to generate a report showing areas that should be addressed. It's similar to the traffic light system with AWS Inspector, with green being, "Okay, Captain, keep up the good work." Orange being, "You should probably look into this because there's room for improvement." And red being, "Okay, you gotta address this, else you're gonna be sent to the principal's office." And by principal, we mean the principal SA. You see what I did there? No, but seriously, these are the areas where the tool has detected potential issues and provides you with a plan on how to design using established best practices. If we take a look at the tool itself, you'll see something similar to the following screenshot. As I mentioned, we name our workload, and that appears in section 1. Section 2 shows you the pillars and drop-downs into the questions for each. Section 3 shows you the actual questions themselves. 4 is pillar and question stem. 5 is a bit of background and recommendation. 6 is the answer you provide with the toggle to dictate whether the question is applicable or not. This is important as it affects your overall score. And oh, I can't forget about section 7, where you'll be presented with short videos explaining how to answer a particular question. And in the performance efficiency pillar, you'll notice that this handsome gentleman is your guide. Man, that dude is cool. I mean, I wish I could be more like him. Anyway, thanks for going along with us in the secure journey to the Red Planet, and good luck with securing your workloads in the future. Oh, and since we're so nice, we'll leave you with one final quiz.
Congratulations on making it to the end of the course. We are so glad that you joined us for this mission.
We hope this was beneficial to you and that you come away from this class with some helpful information. As we stated multiple times throughout the class, make sure you read through the notes and AWS documentation.
Be sure to try implementing the service and best practice that we discussed to make sure you have a solid understanding of the concept that we covered.
We also want to remind you to look at the website shown on screen and in the notes for more information on AWS training opportunities.
We hope you have a good time.
And hopefully we'll see you in another class.
Buzz, buzz.
That's Bee Speak for see you later. Cheers.
Hello everyone. Welcome to our course covering migration to AWS. Over the next 4 weeks, we'll be looking at topics around defining migration, analyzing your environment and needs, planning your migration, services that are commonly used during migration, and actual migration steps. In addition to the videos, there will be notes for further reading and research, forums for various discussions you may want to present or participate in, and assessments to help reinforce some of the things we're talking about each week. We understand that this is going to be very high level and conceptual, but I hope that over the course of the next several weeks, you are able to better understand some of the things necessary when migrating to the AWS Cloud. And I also hope you have a little fun along the way. That's all I have for now. Until the next video. To start off, this week we'll be discussing general migration concepts. We'll start with contextualizing what we mean when we say migration by providing some definitions to make sure we're all on the same page. After that, we'll look at the steps for migrating and then finish the week by covering what we call the 6 R's, which are various methods for migrating applications to the cloud. Your exercise this week will be to evaluate the steps of migrating an application to figure out what the proper way to approach based on the method chosen. Make sure you're looking at the course notes as you go through the week to gain additional information beyond what the videos are able to cover. That's it for now. You'll see me later.
Welcome to AWS Fundamentals, Migrating to the Cloud. We're your instructors.
Well, technically there's Rick too.
Oh yeah, where is Rick? Anyway, this is Sean. He's been at AWS for almost 4 years. He's a technical architect, and he loves triathlons and his dog Chief.
This is Seth. He's been at AWS for a little over 7 years.
7.5 years.
He's a cloud technologist.
Hey, don't laugh at my title.
Sorry. Anyway, Seth doesn't like any of the things that I do.
That's not true. I like puppies.
We do agree on puppies.
We look forward to spending the next few weeks with you talking about migrations.
We hope you learn lots of new and useful information. Still no Rick.
Oh well.
Where do we begin when starting down the path of migration? What do we mean by migration? In the context of this course, cloud migration is the process of moving data, applications, or other business elements to a cloud computing environment. Whether it is a server you want to retire, some data you want to move, or an entire networked environment that needs a new home, there are various types of cloud migrations an enterprise can perform. Seth and I will be covering the various types of migrations this week. All of these methods involve taking some portion of our environment and moving it to the cloud. Depending on the migration type you choose to perform, your migration will involve more or fewer AWS services. I typically like to start with identifying business drivers, since they tend to inform the technical decisions. Being able to answer the question of why should almost always come before answering the question of how. As we know, the cloud enables levels of agility that typically are not possible on premises. For many companies, the number one reason they choose to move to the cloud is the agility and speed that they can move with. The migration process involves 5 phases. Phase 1, migration preparation and business planning. Phase 2, portfolio discovery and planning. Phases 3 and 4, designing, migrating, and validating applications. And Phase 5, operate. In the next several videos, we'll take a look at each of these phases in more detail. Seth will begin by walking us through phase number 1.
When evaluating migrations to AWS, the patterns seen around migrating to the cloud commonly follow a 5-phase approach. The phases we outline in this regard are Phase 1, migration preparation and business planning. Phase 2, portfolio discovery and planning. Phases 3 and 4 are designing, migrating, and validating your applications. And phase 5, operate. So let's start with phase 1. When looking at migration through this context, planning and preparation will be where most of the time and effort are spent. While individual, non-crucial standalone systems may have the ability to be quickly moved over with little planning, it's because these provide minimal risk for impact should an issue occur. In most cases, the interconnectivity of the various components need more than just several hours of operational work. These types of migrations require very detailed and insightful planning and preparation for both the technical and business sides of the operation, which is why we start with migration preparation and business planning. Here is when the right objectives are determined and getting an idea of the types of benefits you will see begins. It starts with some foundational experience and developing a preliminary business case for a migration, which requires taking objectives into account along with the age and architecture of the existing applications and their constraints.
In phase 2, we need to take a deeper look at our IT portfolio. The goal is to establish where our dependencies are between our applications and begin thinking about what types of migrations might work best for each. Not every application is likely to fall into the same migration strategy. This phase, with a focus on application discovery, is our best opportunity for building a clear use case and business case for each application. Depending on the age of your environment to be migrated, you may even identify applications that fit clearly into the retire strategy. The AWS Application Discovery Service can assist with this process by gathering information about your environment. We'll be taking a closer look at this service in week 2.
Phase 1 involved planning and analysis. Phase 2 involved planning and analysis. Moving on to phases 3 and 4 will still involve planning and analysis, but will also bring you into the times for action. With phases 3 and 4, we are still planning with our designs, but we then migrate and validate. Here, the focus starts to shift from the portfolio level to the individual application level, where you're designing, migrating, and validating each application. Each application is designed, migrated, and validated according to one of the 6 common application strategies, or the 6 R's, which we will discuss later this week. From the previous phases, there are a couple of things I want to specifically point out. Well, one specific thing, and that is the need for each application to be designed, migrated, and validated according to what's necessary for those specific components. Just like with other areas of building and architecting, applications need to be looked at individually. Their needs require assessment, and then they need to be treated in the ways that best fit their use cases. This is not the time to try and force a one-size-fits-all type of mentality. I know this can sound like a lot, but once you have some foundational experience from migrating a few apps and plans in place that the organization can get behind, it becomes easier to accelerate the migration and achieve scale. Some more good news is that partners can help you here, as well as AWS Server Migration Service, AWS Database Migration Service, and Cloud Endure Migration.
So far, in phases 1 through 4, we have discovered our applications, planned their migrations, and implemented those strategies. In phase 5, operate, we look at the ongoing operation of our applications and systems in the cloud and look to continue iterating. We've now created a new foundation that can be built on to further improve our operating environment. During the planning phases, you may have found applications that were good candidates for retirement, but due to dependencies, were unable to be removed from the environment. This is the phase that we begin to look at how to turn off some of these old systems. Phase 5 is an ongoing phase, taking all of the information and lessons learned from our migration and working towards continual improvement. There are many migration partners available to help you better operate in the cloud and become more proficient in your migrations. These companies have expertise in all phases of the migration process and can help with implementation, planning, or even training on migration technologies. In week 4, we'll take a closer look at the partner ecosystem and how they can help in your migration. Now that we've covered the 5 phases of migration, Seph and I will introduce you to the different migration strategies.
There are many tools and references that are available to you when evaluating needs for migration and cloud adoption, both from trusted third parties as well as from AWS directly. These will vary in focus and applicability, but can be very helpful if you find the ones that best fit the tasks you are trying to complete. One of these references that can be very helpful in the early stages of many migrations is the AWS Cloud Adoption Framework. AWS Professional Services created the Cloud Adoption Framework to help organizations design and travel an accelerated path to successful cloud adoption. The guidance and best practices provided by the framework help you build a comprehensive approach to cloud computing across your organization and throughout your IT lifecycle. The Cloud Adoption Framework covers what we see as 6 important perspectives to consider when looking at cloud adoption plans. The business perspectives look at business, people, and governance, while the technical perspectives focus on platform, security, and operations. The business perspective is there to help you move from separate strategies for business and IT to a business model that integrates IT strategy. The people perspective focuses on preparing teams for cloud adoption by updating staff skills and organizational processes to include cloud-based competencies. And governance is about the integration of IT governance and organizational governance. It provides guidance on identifying and implementing best practices for IT governance and on supporting business processes with technology. On the technical side, the platform perspective helps you design, implement, and optimize the architecture of AWS technology based on business goals and objectives by helping to provide strategic guidance for the design, principles, tools, and policies you use to define AWS infrastructure. The security perspective helps you to structure the selection and implementation of controls, and the operations perspective helps you to run, use, operate, and recover IT workloads to levels that meet the requirements of your business. The course notes will contain a link to our page on the Cloud Adoption Framework. I highly recommend that you dive into that page to familiarize yourself with the perspectives in order to make conversations and decisions about cloud adoption and migration as informed as possible.
What are we hoping to get out of the class over the next 4 weeks? Overall, in this class, we'll be taking a multi-tier application and migrating it to the cloud. A repeated focus over the next few weeks will be planning, preparing, and testing. As we make our way through the levels of our application stack, we will dive into how you might plan for the migration of that component, what AWS services could assist in both the preparation and implementation, and then look into how the strategy can be tested. Week 1 is all about laying the groundwork, covering the terms and concepts that we will dive into with the remainder of the class. Our goal in week 1 is for you to quickly get up to speed with familiarity of the migration phases and types. Week 2 is where planning begins. The main theme of any successful migration will have a strong emphasis on planning. This week, we will introduce you to our environment to be migrated and focus on the planning steps for migrating compute assets. This week also begins our introduction to AWS services that could be leveraged during a migration. Week 3 continues our focus on planning, moving to the storage and networking side of the discussion. We'll cover topics like databases and several of the more common AWS storage offerings that you might consider implementing in your migrations. Because many times our systems need to talk to each other as well as to the internet, we'll dive into networking at the end of the week. Week 4, we begin to automate. Where possible, your migration efforts should leverage scripting, tooling, or some form of automation to ensure repeatability, testability, and scalability. We'll introduce you to Cloud Endure, an AWS migration service, and show how it can automate many of the migration functions. By the end of our 4 weeks together, we'll have gone through a migration from start to finish and brought up the questions that you should have answers to before undertaking your own.
When beginning to discuss the how of migrating, it is important that you determine what is in your environment and the migration strategy for each application. Specifically for this purpose, we have 6 approaches that we see as common migration strategies for applications. The 6 strategies are rehost, replatform, repurchase, refactor, retire, and retain. You should gain a thorough understanding of which migration strategy will be best suited for certain portions of your portfolio. It is also important to consider that while one of these 6 strategies may be best for migrating certain applications, another strategy might work better for moving different applications in the same portfolio. Evaluate the needs of the specific applications, then find the approach or combination of approaches that will work best for each use case. Here, we'll start with rehost. We'll cover the other R's in subsequent videos. Rehost, commonly referred to as lift and shift, is a direct migration where you're trying to pick up and move your applications or environments directly into the cloud while trying to make as few changes as possible. This is also known as forklifting. While trying to migrate, it is common to want to optimize as soon as possible, but you may also find that applications are easier to re-architect once they are already running in the cloud. This happens partly because your organization will have developed better skills to do so, and partly because the hard part, migrating the application data and traffic, has already been accomplished. With rehosting, your goal is often just to try and get to the cloud as quickly as possible while maintaining the stability, functionality, and security of your existing system. Where rehosting was all about getting to the cloud quickly, replatforming is about gaining some optimizations while migrating. So instead of a lift and shift restriction, we're looking more at lift, tinker, and shift. Overall, this wouldn't look too different. You're still trying to maintain the stability and functionality, but you may also want to find some ways that will immediately make things easier in the long run. Maybe not major changes like going from a monolithic server environment to a service-oriented architecture, but something simpler to handle. Take, for example, your database. Databases vary in complexity and overhead to run, and this doesn't change when you move from running a DB server in your local environment to a DB engine running on an Amazon EC2 instance. What if you had a database that didn't require a lot of heavy customization? You were essentially just running it on a server containing a mildly optimized engine and your data. In this case, why not run the database in Amazon Relational Database Service, or RDS? This would not only enable you to maintain your database functionality, but you would also eliminate some of the management tasks while gaining features like high availability and automated maintenance actions. Times like this, when you're moving to a similar system that provides some additional benefits, can really help to optimize without a full re-architecting of your applications.
Other than the 2 migration strategies that Seth has already covered, rehost and replatform, we have 4 other migration strategies that you might determine are the best for one or more of your applications. They are repurchase, refactor or re-architect, retire, and retain. In the repurchase strategy, you're making the decision to move to a different product or licensing model. An example of this strategy could be to use the migration as an opportunity to upgrade to a newer version of a product, or maybe to move from a commercial license to an enterprise license, or vice versa. The important distinction is that you aren't fundamentally changing the design of the application or system. For the refactor or re-architect strategy, you are typically driven by a strong business need to add features, scale, or performance that would be difficult to achieve in the existing environment. Even though this strategy can sometimes be the most expensive when calculating hours spent, it can often yield the best results since it allows for taking full advantage of the benefits the cloud offers. If you're working in an environment with a lot of legacy applications or systems that have been around seemingly forever, the retire strategy can be implemented to help clean up and reduce the assets to be migrated. By removing the applications no longer in use, it allows you to direct your attention towards migrating and maintaining the resources that matter. The final strategy is to retain things as is. This decision can be made for a variety of reasons. Sometimes there are applications that you are just not ready to migrate. Or, in some cases, the business feels more comfortable keeping them on premises. If you've recently just gone through an application re-architecture or upgrade process, you might not be ready to prioritize making even more changes. As you make your way through your IT portfolio, each system and application should receive consideration in how its migration is going to be handled. There is no one-size-fits-all approach to migrations, so taking the time up front to plan will lead to the least headaches and most success.
While week 1 was about gaining an understanding of migration and looking at some of the methods, this week is focused on continued planning. For week 2, we're going to look at the importance of knowing our applications and infrastructure. Here, we'll evaluate some of the important areas to analyze within our portfolio, as well as some of the ways to discover the necessary components within our applications. As always, keep looking at those course notes and readings, and keep looking for how the topics covered will best apply to your specific use cases. So long for now.
One of the major motivations and benefits to migrating to the cloud is the scalability. Well, that's what I'll be talking about today.
What we'll be talking about today.
Sorry.
Okay. While scaling is a great and wonderful thing, there are some things that need to be considered. Depending on your application, there are all sorts of things that may change how you're scaling.
Some of the things we're going to look at today are scaling constraints, session data management, and major scaling methodologies.
Starting with constraints. This is important to cover because not everything can scale in the same way. If you have a limited number of licenses and getting more requires a lot of time, approval, or just a lot of processes to work through, dynamically scaling can be very difficult. Or perhaps your application just can't support the downtime it would take to change the underlying architecture so that it can handle more of a workload. In these cases, architecting in such a way so that you don't have to dynamically scale would be the way to go.
Looking at adding other components to help when you can't scale would be a good way to design around this. Resources like managed caches and queues help to not lose requests when scaling is limited. Also, offloading unnecessary work from unscalable servers could help. If you're working with a caching server and increasing its resources is going to be difficult, perhaps it would be easier if stale data was lifecycled off the server to conserve storage and not over-provision and overspend.
Strategies like these are just some of the ways you can work around these constraints.
But what if you have resources that technically can scale, but you don't want to lose session data in the process?
Well, since you so humbly asked, I'll tell you.
No need. I was just using you as a prop to lead me into the next section. So if your application has session data that you're trying to maintain, but also need to scale to adjust the changes in demand, the easiest thing to do is just store your session data off the instance.
Yeah, so as Sean was so helpful to point out, using off-server session storage can really help provide scaling in what could otherwise be a very constrained environment. Using data stores like caches can really help to maintain functionality while not limiting your scaling capabilities.
Thanks, Seth. I could have handled that on my own without issue, but thanks.
You're welcome. So, what was our last topic?
We were going to handle horizontal and vertical scaling.
Oh yeah, so let's do that.
I don't want to just talk about it though. What if we show it instead?
Sounds good to me. What did you have in mind?
Just follow my lead. So there are two different types of scaling, horizontal and vertical. Horizontal
scaling.
I said follow my lead.
Fine.
Horizontal scaling, or scaling out, is when we add more resources and distribute across them. The benefit of this is that it incurs no downtime for your original resource. As the load continues to grow, we can continue to add more and more resources and spread the load across them. Once your load subsides and we need less resources, we can scale back into the original number. This is done with little to no impact to your end user. That's horizontal scaling.
I see what you're doing here. The other type of scaling is vertical scaling. With vertical scaling, you maintain the same logical resource, but you're making that resource more capable. Adding things like memory, storage, or compute power so that that resource can handle more of a workload. With this type of scaling, you don't have to distribute requests across multiple because you do still have that one same logical resource. But there are some limitations. One of those limitations is that there typically is some downtime when you are vertically scaling. The second limitation is that while you're scaling, you typically scale up, but I guess you don't scale back down. Uh-oh.
That covers our quick conversation on the two types of scaling. It's important to analyze your needs and plan your architecture and environment so that you don't incur any negative impact.
Do I really have to stay this big?
Bye.
Here we're going to talk about high availability. It won't take too long, I promise. The big thing I want to say about high availability is, drumroll please, create highly available workloads in AWS. That's it. That's all I had to say. Told you it was going to be short. Sorry, it's not going to be quite that short. I did want to give just a little more of a review. First off, what is high availability? It's building in such a way that allows for increased uptime or availability. Designing for the highest levels of availability is always a good practice, and moving into a cloud environment like AWS makes this easier than trying to achieve the same levels of availability in a traditional environment. From there, you'll just want to keep some things in mind as you move towards building and optimizing your migrated environments in AWS. A primary tenet here is to avoid single points of failure. If the failure of any single component or node would cause a negative impact to the system as a whole, look for ways to minimize the impact. In some cases, this could mean running more than one instance of a component, and in other situations, it could mean having a replacement that can easily be launched should the primary fail. Another way to help build towards higher availability is to utilize ways to distribute traffic and requests across multiple endpoints or nodes. Using load balancers is a major way this can be accomplished. Also, you'll want to have some scalability. In AWS, simply by using managed services, you achieve or can enable some fault tolerance just by how the services themselves scale. These services can provide a much easier path to high availability than if you were trying to just build it out manually. Other services enable individual resources to become scalable by either providing horizontal or vertical scaling. Look into all of these options to see what best fits your use cases. Lastly, something to consider when trying to add higher levels of availability is to monitor your environments. Monitoring can help you identify expected trends, trigger actions for anything outside of normal behavior, and help you to automate recovery of anything that might fail within your environment. This is incredibly important and cannot be stressed enough. Luckily for you, AWS has several services for both the monitoring and logging, any actions you might want to take, and events you may want to be notified of. Well, that wasn't too bad, was it? That's all I have for now. Please continue to look into how you can build and design for higher levels of availability within the systems that you bring to AWS. As has been mentioned several times now, when planning for your migration and evaluating the scope of what may need to be moved, it quickly starts to become clear that there is no single migration method for everything. Depending on the type of application or component, The specific method used for its migration is very important. While we are not going to get into specific migration details here, one thing I wanted to bring up is the importance of decoupling the migration of your databases and data stores from your other applications and components. What makes this such an important topic is the fact that you're dealing with the incredibly important resource of data. The data needs to be secure, reliable, and have varying levels of accessibility. When migrating applications, much of the time and energy goes into ensuring consistent or maybe even improved performance. Planning and preparation is put into being ready when the switch finally happens, and there is rarely any middle phase to worry about between environments. With your data, because this is often one of the most crucial components of your application's environment, there may still be access requirements before, during, and after the migration. This is one of the reasons that database and data store migration is so important to consider and plan when handling the migration. Though we won't discuss the actual migration just yet, what I want to cover are some of the important planning and analysis steps. It is likely that many questions about your database will be well known before your migration is even a discussion. Things like the size, schema, types of tables, and engine-specific limitations are usually topics that are regularly discussed and reviewed. If you haven't done any other database updates or moves in a while, you'll likely need additional research when looking for information about access patterns and frequencies, connectivity methods, security, object sizes, and more. The questions continue to grow when you start considering any changes to the schema, infrastructure, or engine that might occur as part of the migration. This may seem like a lot, but understanding these things will greatly help when handling the migration and can save you a lot of time and headache down the line. Next, you'll want to understand your requirements. The requirements of your database for normal operation while migrating and in your new environment will all need to be analyzed. Are you replacing anything about the platform of your database? Do you know all the key parameters of your new environment? Can your app afford downtime, and how long can this downtime be? How much of the data needs to be migrated now versus later? These are just some of the questions that come to the surface when you start looking into the requirements. Part of this planning is also to understand your network. This is very straightforward. You will need to know the limitations of your network, how much of your bandwidth is available for you to use, how much of your network utilization can your database handle in both your source and destination locations. In some circumstances, this can be adjusted temporarily in order to facilitate a faster migration. But in other cases, you may have to figure out a way to work with what's already in place. Keep in mind that during the migration, you may be placing additional load on the database. How much of an additional load and for how long is going to depend on the migration methods. Another area to look into is planning your talent. Someone needs to know the source and destination database engines, which can be multiple people if any changes are being made. Somebody needs to know about servers, ports, and firewall rules, and how to handle the network requirements from a practical operations perspective as opposed to just theoretical. In many cases, this is too much for a single person to handle, so planning and gathering who is going to be involved becomes very important. The last item I want to cover for now is planning your time. Database migration projects often include refactoring of the application and database code, and also the schema. All of this is a time-consuming and iterative process. The refactoring process alone can take anywhere from a few weeks to several months, depending on the complexity of your application and database. If you have hard dates, be realistic about what you can achieve. Remember that even in the best of circumstances, migration might be slower than anticipated. These are just some of the areas for you to focus on when looking at how database migration differs from direct application migration. In the course notes, you will see more information and more details about how to prepare for your move. Until next time. If, like so many of you, you are already using virtualization in your current environment, and you want to maintain much of what you've already built in order to move it to AWS, this doesn't have to be something that you self-manage or build from scratch. AWS Server Migration Service, or SMS for short, is a tool available in AWS specifically meant to enable an easier transfer of your virtual resources directly into your AWS Cloud environment. SMS is an agentless service which makes it easier and faster for you to migrate up to thousands of on-premise workloads to AWS. The service allows you to automate, schedule, and track incremental replications of live server volumes and makes it easier for you to coordinate small and large-scale server migrations. But before we go any further with the features of SMS, I do want to share some requirements that you need to be aware of when using the service. The main requirement is that AWS SMS is currently only available if you are migrating VMware vSphere, Microsoft Hyper-V, and Azure virtual machines into the AWS Cloud. Keep an eye out for any updates to the supported source environments by checking the AWS Server Migration Service documentation. Another requirement for you to be aware of is that SMS replicates your server VMs as cloud-hosted Amazon machine images that can be deployed on EC2. This does not move VMs into functions or any other area of AWS, but it does allow for you to launch your server VMs as Amazon EC2 instances. The last requirement is that if you want to use SMS to help you transfer server VMs from your origin environment into AWS, you must use a connector. The Server Migration Connector is a FreeBSD VM that you install in your on-premise virtualization environment. The connector aids in the creation of appropriate permissions and network connections that allow SMS to execute tasks in your virtualized environments. Once setup has been completed, you are able to migrate up to 50 concurrent VM migrations per account. The SMS service talks with the Server Migration Connector in order to ease the task of migrating from the supported platforms. Testing is also simple to automate because the migrations create EC2 AMIs, which can easily be launched and tested for verification of successful migrations. Monitoring of your migrations is made possible by Amazon Cloudwatch, and logging and auditing can be done through AWS CloudTrail. These are great to help with providing continuous visibility in your migrations and enabling you to set up events and alarms based on the log entry and metrics that you see, which then help you to automate actions based on the behavior you're seeing during your migrations. I know that was a bit quick of an introduction, but I highly suggest that you go deeper into SMS by diving through the documentation. Depending on your origin environment, there will be some differences with how you work with AWS SMS and how you manage the connector. That's all for now. I'll see you later.
Not all that long ago, planning for a migration also involved renting a moving van or contracting a moving company. There was the time spent unplugging all the cabling, pulling servers from racks, packing them up in boxes, loading up trucks, driving to new location, unloading boxes, putting servers into their new homes, and honestly, my favorite part, recabling everything. Then came everyone's favorite part, turning it all on and hoping everything worked, which rarely happened. Then the world started going virtual. We had fewer physical servers to manage, but a move or migration still looked an awful lot like before. After all, those virtual machines had to live on a physical server somewhere. At AWS, we like to say that we help remove the undifferentiated heavy lifting, allowing you to focus on what matters to your business. Well, in the case of migrations, that can literally mean heavy lifting. Have you ever tried to move a loaded storage area network appliance? Hard drives weigh a lot. Moving your VMs to the cloud will likely require lifting nothing more than a keyboard and mouse, or maybe your laptop. We have several services that can assist with the virtual heavy lifting, like VM Import-Export and the AWS Server Migration Service. VM import-export enables you to easily import virtual machine images from your existing environment to AWS as Amazon EC2 instances, or Amazon Machine Images, AMIs. This enables you to migrate applications and workloads to Amazon EC2, copy your VM image catalog to EC2, or create a repository of VM images for backup and disaster recovery. Once your applications and workloads have been imported, you can run multiple instances from the same image, and you can create snapshots to back up your data. For most VM import needs, we recommend that you use the AWS Server Migration Service, since it automates the import process. The AWS Server Migration Service, or SMS, automates the migration of your on-premises VMware, vSphere, Microsoft Hyper-V, and Azure virtual machines to the AWS Cloud. Leveraging SMS to manage your server migration can add several benefits. It can simplify the process overall, requiring just a few clicks in the AWS Management Console once everything is set up. With VM import-export and AWS Server Migration Service at your side, the migration of your virtual machines to AWS couldn't be easier.
While we have had a good amount of discussion about planning your migrations and different tools that help in the migrating of your resources, one important area to bring up is the need to monitor your migrations. Migrating is not just something you can set and then forget. You need a way to identify what is happening, how well it's going, if everything is running as expected, and various other areas. This can all be especially difficult if you are using multiple tools across multiple AWS and partner solutions. AWS has a service called AWS Migration Hub. Using Migration Hub allows you to choose the AWS and partner migration tools that best fit your needs while providing visibility into the status of migrations across your portfolio of applications. This also provides the ability to see metrics and progress for individual applications regardless of the tools being used. This allows you to quickly get progress from updates across all of your migrations, easily identify and troubleshoot any issues, and reduce the overall time and effort spent on your migration projects while providing a single place to monitor migrations in any AWS region where your migration tools are available. In order to view your assets in Migration Hub, you perform discovery using an AWS Discovery tool or by migrating with an integrated migration tool. Once you've performed discovery or started migrating, you can explore your environment from within Migration Hub. When the migration completes, Migration Hub also shows details about the resources that have been created by the migration. For servers migrated by AWS Server Migration Service, Cloud Indoor Migration, and other migration services and partners, Migration Hub provides links to the AMIs created or running Amazon EC2 instances. For databases migrated by AWS Database Migration Service, Migration Hub provides the target endpoint ID, which can be used as a search filter on the Database Migration Service Management Console. So while Migration Hub does not automate the steps of the migration, it does provide a single place for you to track the progress of the applications you are migrating.
In phase 2 of preparing for your migration, the focus is on discovery and planning. As a consultant, I frequently had the task of combing through a company's environment to try and track down all of the in-use software and to create spreadsheets of which servers ran which services. The AWS Application Discovery Service helps you to plan your migration to the AWS Cloud by collecting usage and configuration data about your on-premises servers. Application Discovery Service offers 2 ways of performing discovery and collecting data about your on-premises servers: agentless and agent-based. Agentless discovery works with VMware vCenter and can be performed by deploying the AWS Agentless Discovery Virtual Appliance. After the Discovery connector is configured, it identifies virtual machines and hosts associated with vCenter. The Discovery connector collects configuration information about your servers, like server host names, IP addresses, MAC addresses, and disk resource allocations. The Discovery connector also collects metrics about the VMs. These data points can be extremely useful in your migration planning activities, especially if you are using the re-platform approach. It can inform decisions like what type and size of EC2 instance to use. Knowing both the average and peak utilization metrics for things like CPU, RAM, and disk I/O, you can make a more informed decision about how to design your environment in AWS. It's important to note, however, Discovery Connector cannot look inside each of the VMs, so it cannot figure out what processes are running on each VM or what network connections exist. If you need insights into that type of information, then using an agent-based approach will be required. Agent-based discovery can be performed by deploying the AWS Application Discovery Agent on each of your VMs and physical servers. The agent will then collect static configuration data similar to the Discovery Connector. In addition to those static config details, the agent will record detailed time series systems performance information, inbound and outbound network connections, and processes that are running. You can export this data to perform an analysis and to identify network connections between servers for grouping servers as applications. The Application Discovery Service is integrated with our AWS Migration Hub, which helps to create a single pane of glass view into migration progress. After the service has performed its discovery, you'll be able to view the discovered servers, group them into applications, and then use the Migration Hub to track the migration status of each application. All of the data that is collected by the Application Discovery Service can be exported for analysis using tools like Amazon Athena and Amazon QuickSight. Overall, the AWS Application Discovery Service helps you to obtain a snapshot of your current state of your data center servers, and the data collected helps to create a cost-optimized migration plan based on your unique business requirements.
While this isn't a security-specific course, security should always be considered. Whether you're building a multi-tier, globally accessed application, or you're discussing migration of your environments like we are here, security needs to always have a place in the conversation. With the migration discussion, our talking points aren't different from many of the topics that would normally be covered. Our focuses will likely be things you've heard before, as we'll be talking about protecting your data in transit, protecting your data at rest, and protecting access to your data for use. And while these may not be new topics, it is important to understand them in the context of a multi-environment communication. When securing data in transit, our goal is to make sure we can communicate easily between environments while protecting the data. This is where you try to reduce the risk of unauthorized exposure by defining and enforcing requirements and implementing controls. You definitely want to make sure you have defined data protection in transit requirements and encryption standards based on data classification to meet your organizational, legal, and compliance requirements. Also, enforce your defined encryption standards to ensure that meeting these requirements is not optional. Additionally, ensuring that there are tools and controls in place to help you with enforcement of your standards will go a long way towards helping you stay secure in transit. The first and one of the easiest things you can do is just to use authenticated network communication protocols. Using IPsec tunnels and transport layer security, or TLS, to encrypt in transit will go a long way to reduce the risk of data tampering or loss. Additionally, setting up automated tools to help identify when other issues or risks become apparent can also be very helpful. Using a tool or detection mechanism to automatically detect attempts to move data outside of defined environment boundaries can be very helpful in identifying any threats to your security and help prevent data exposure. With data at rest, encryption is really the biggest point here. You will really want to make sure you have established and enforced encryption methods in place for everywhere data is held in your environments. In addition to this, your key management solutions will play a big part in your encryption for your data. Depending on the services within AWS and your current environment's resources that you're using, there are several options that you can look into for helping you to maintain data security at rest. For instance, many of the data store services with AWS have options that are simple to implement where you essentially turn on encryption for that service. For your current environment, if you are not already using an encryption key management solution, it will be important to evaluate and find a solution as soon as possible. And I know it can reduce the level of desired performance depending on the resources or AWS services you're using when you start to implement encryption mechanisms. But that is why it's important to have these conversations early on so that any additional performance overhead encountered by your security measures can be considered for your migration expectations. When it comes to securing your data use while migrating, we're focusing on general data access and permissions. As with other areas of access control and permissions that we usually talk about with AWS, using a least privilege access model is going to be a great mindset to keep. Users and applications should only have access to the specific data they need, should be given access for only when they need it, and should only be able to access how you want them to access it. Depending on the data store options you have available to you, the level of granularity you're able to provide in terms of what each user can access will vary. It's just important to take the extra work to make sure that no one has access to more than they should, or at least that they only have access to the appropriately classified data. For limiting when they should have access, using AWS services and automated mechanisms that allow you to limit time users have to access data will become very helpful. Sometimes this can be done in a policy. Other times, you need to look at automation jobs or workers that can open and close connectivity methods to ensure that data is only accessed when necessary. And for limiting how you want users to access, that's where we go back to enforcement of the methods that you established when looking at protecting your data in transit. Making sure only secured connections and protocols are used helps to avoid the accidents that can occur when those become optional instead of required. Well, that's all that I have for you in terms of multi-environment security. I know this was all very broad and theoretical, but a lot of the specifics will depend on what resources, tools, and services you have available to you and what features they provide in terms of security. Make sure you check the course notes for links to provide additional information around securing your environments, and keep thinking about how those concepts can be implemented in your multi-environment setup as you're migrating. I'll see you later.
The tools for migrating data to the AWS Cloud are either unmanaged or AWS managed. This illustration displays some options for data migration, depending on the volume of data and the velocity of migration. Unmanaged migration tools are the easy, one-and-done methods to move data at small scales from your site into Amazon Cloud Storage. These include options like rsync or the Amazon S3 and Amazon S3 Glacier command line interfaces. AWS managed migration tools help you manage the data migration tasks more efficiently and can be further classified into two broad categories: tools that optimize or replace the internet, like Direct Connect, and tools that provide a friendly interface to Amazon S3. If you have large archives of data or data lakes, or in a situation where bandwidth and data volumes are simply too large, you might want to lift and shift the data from its current location straight into AWS. You can do this either by using dedicated network connections to accelerate network transfers, or by physically transferring the data using AWS Snowball. If your data stores can gradually migrate over time, or when new data is coming from many non-cloud sources, consider methods that provide a friendly interface to Amazon S3. These migration services can leverage or complement existing installations, like backup and recovery software or a SAN. Several AWS technology partners and third-party solution providers also offer tools for migrating data to AWS. For a list of vendors who partner with AWS to provide data migration solutions, check out the course notes.
Welcome to week 3. This week we're going to be focusing on services within AWS that can help us with our migration. We'll be looking at topics around data transfer, storage, databases, and some other things that will hopefully help you to make the most out of moving to AWS. Keep diving through those readings and notes and keep learning. I'll be back on your screen before you know it. When moving from an environment where you have limited storage solutions, it's nice to know that you have flexibility to find the best solutions to use when concerning your storage choices in AWS. For this session, we'll quickly review 3 of the most commonly used storage solutions available for you. Starting with the most commonly used and default block storage mechanism in AWS, Amazon Elastic Block Store, or EBS. This provides block-level storage volumes for use specifically with EC2 instances. EBS volumes behave like raw, unformatted block devices that you can mount as devices to your instances. And while you can mount multiple volumes on the same instance, each volume can only be attached to one instance at a time. You can create a file system on top of these volumes or use them in any way you would use a block device, such as a hard drive. Additionally, you can dynamically change the configuration of a volume attached to an instance. Within EBS, there are several configurations open to you, and the volume types that you can choose include both SSD and traditional HDD options. The general purpose volume is the most common type and the default volume used by Amazon EC2. General purpose SSD volumes provide strong levels of performance for a wide variety of workloads. The Provision IOPS SSD, or PIOPS volumes, offer you some of the highest performance SSD volumes for mission-critical low latency or high throughput workloads. You also have the ability to adjust the level of performance you may require. These are best utilized when you need consistent and high levels of performance. For our HDD volumes, we have another 2 options for you to consider. For the throughput optimized volumes, these are for frequently accessed throughput-intensive workloads. While it's not the fastest type of storage in EBS, it is a great balance of cost and functionality. The other type of HDD EBS volume is the cold HDD volume. These are going to be best suited for scenarios where the lowest cost block storage is of utmost importance. The major difference between throughput optimized and cold HDD is, unsurprisingly enough, the throughput. Both are designed to be cost-effective options. If you're planning a higher throughput need, but still with lower overall I/O per volume, then the throughput optimized would be the way to go. If, on the other hand, you need a higher I/O on the volumes, the SSD options are still going to be better choices. So that's about EBS. But the title of this video also mentions that we'll be talking about Amazon Elastic File System. So where is it? Well, lucky for you, that's my next topic on this video. Elastic File System, also known as EFS, allows you to create a file system, mount the file system on EC2 instances, and then read and write data to and from your file system. And while that may sound strikingly familiar to what we just covered, it does. There are some major differences though. First off, EFS can be mounted to multiple EC2 instances at the same time. This enables you to have a shared file system for multiple servers. Secondly, EFS is just that, a shared file system. EFS is a file storage system that uses NSF v4 and currently supports versions 4.0 and 4.1, though we do recommend that you use the most recent version. EFS does provide another difference that you can utilize, and this becomes incredibly important while running multi-environment workloads, like when migrating. That other difference is that your AWS-housed EFS can be mounted to by on-premise servers. So now that we've looked at EBS and EFS, let's take a look at our last topic for this section, Amazon Simple Storage Service, also known as S3. S3 is an object storage system that was intentionally built with a minimal feature set that focuses on simplicity and robustness. To use S3, all you do is create a bucket, which is a container for your objects, and then start loading in the objects. The objects are fundamental entities stored in S3, which consist of the object data and metadata. While the object's data is opaque to S3, the metadata is a set of name-value pairs that describe the object. In S3, once you've created the bucket, you can work with objects either through API or directly through the console. Though S3 is a natively internet-based service, meaning that access is provided through internet-accessible endpoints, it does not mean that there is any loss or compromise on how secure your data is. Through access control lists, bucket policies, encryption options, and additional security features, you have full and granular control on how you grant access to objects in your buckets. In terms of migration, S3 is unique in that it can be used not only to store objects for your applications to utilize after migration, but can also be a great location to store images, backups, database dumps, and other components that are used while migrating. So while you're planning out your migration, be thinking about what the best storage option for your various workloads might be. Test and experiment with them and find out what provides the most optimal performance to meet your needs.
Migrating your workloads doesn't just involve moving around virtual machines. It likely also involves moving large amounts of data. Sure, copying a couple gigabytes of data to the cloud wouldn't take that long, but what if you've got several hundred terabytes of data? Even if you're lucky enough to have a high-speed internet connection, it will still take days, if not weeks, to upload. Let's do some quick math. Let's say you've got 80 terabytes of data that needs to be moved, and you've got a 1 gigabit connection to the internet. The business has decided that we're allowed to use the entirety of the connection for the duration of our transfer. So, how long are we looking at? Well, a terabyte is about 1,000 gigabytes, so we've got 80,000 gigs to copy. A 1 gigabit connection is being measured in bits, not bytes, so we've got to divide by 8, leaving us with 0.125 gigabytes per second of upload. So 80,000 divided by 0.125, divided by 60 seconds in a minute, divided by 60 minutes in an hour, divided by 24 hours in a day, carry the 1, it looks like we'll be done in just over a week. Your business can go a week without internet, right? Assuming a week of downtime isn't going to fly with management, we can look into other options for migrating the data. AWS Snowball is a physical device that can be connected directly to your network in the data center and leverage the local network to copy the data. The AWS Snowball device can currently hold up to 80 terabytes and is protected by AWS Key Management Service to encrypt the data. Using Snowball, you can import and export data between your on-premises data storage locations and Amazon S3. The Snowball is its own shipping container, and its e-ink display changes to show your shipping label when Snowball's ready to ship. But what if you have a lot of data to move? Not gigabytes or terabytes or even petabytes, but exabytes of data. Well, we've got a moving truck for that. Literally. A semi-truck. Well, technically it's the shipping container on the back of the truck, but it's called AWS Snowmobile. And this storage on wheels service holds up to 100 petabytes of data. Check out the notes on this video for a link to the launch announcement and more information. Moving data is the real bulk of the work for a migration. It's important to make sure it's done efficiently and securely. Depending on how much data you need to move, AWS Snowball could be the right choice.
There are times when, whether during a migration or just wanting to have AWS Cloud-backed storage for your on-premises resources, you need to be able to connect across environments. AWS Storage Gateway utilizes a VM image in your on-prem environment that securely connects to the gateway endpoint within AWS. This allows you to connect your local storage resources to the AWS Cloud and enables you to add availability, fault tolerance, and scalability to your storage mechanisms. For solutions, Storage Gateway offers file-based, volume-based, and tape-based options. File Gateway, the file-based solution, supports a file interface into Amazon Simple Storage Service, or S3, and it enables you to store and retrieve objects in S3 using industry standard file protocols such as Network File System, NFS, and Server Message Block, or SMB. A volume gateway provides cloud-backed storage volumes that you can mount as iSCSI devices from your on-premises application servers. With this volume-based solution, you do have two configuration options. There are cached volumes and stored volumes. Cached volumes allows you to store your data in S3 and retain a copy of frequently accessed data subsets locally. Stored volumes can be a solution for when you need low latency access to the entire data set. All of the data is stored locally, and snapshots can be made from the on-prem storage and used to either recover local volumes or create volumes inside of your AWS accounts. Moving on, the last type of gateway I want to mention is the tape gateway. With a tape gateway, you can durably archive backup data into AWS. A tape gateway provides a virtual tape infrastructure that scales seamlessly with your business needs and eliminates the operational burden of provisioning, scaling, and maintaining a physical tape infrastructure. Another tool that can assist when you're working between environments, like when migrating or transitioning to a hybrid environment, is AWS Data Sync. Data Sync is a data transfer service that simplifies, automates, and accelerates moving and replicating data between on-prem storage systems and AWS storage services over the internet or AWS Direct Connect. Currently, Data Sync supports transfers between NFS to Amazon Elastic File System or Amazon Simple Storage Service. This may sound somewhat similar to Storage Gateway, but the major differences are that Data Sync primarily is utilized to transfer from an NFS source, and the destination can be EFS. Similar to Storage Gateway, Data Sync uses an agent, which is a virtual machine that is used to read or write data from on-prem storage systems. The agent is currently deployed on a VMware ESXi hypervisor, and you use Data Sync Management Console or the API to set up and activate your agent. With these tools, hopefully you have some additional ideas of how you can manage data transfer and access across environments. The course notes will have more on Storage Gateway, Data Sync, and their options. I encourage you to take a look. As we mentioned earlier in the course, migrating your databases can be a very difficult task. Outside of all of the planning and analysis, you have to set up the necessary network connections, find a time that works for adding the additional load to your active DB, take a backup of all of the necessary data in your database, and enable for updates to the database to be replicated to the new environment. And you have to do this without negatively affecting your running application and ensuring the security and integrity of the data. When working with AWS, there is a service that, while it won't completely remove the work needed to migrate between database environments, it will help to lighten the load. AWS Database Migration Service, or DMS, is a tool that makes it easier to migrate relational databases, data warehouses, NoSQL databases, and other types of data stores. You can use it to migrate your data into the AWS Cloud, between on-prem instances, or between a combination of cloud and on-premises setups. Whether performing one-time migrations or ongoing replications to keep environments in sync, DMS can help you with the managing of the tasks. Also, if you need to perform a schema change while migrating, there is an accompanying tool with DMS called AWS Schema Conversion Tool, which supports converting your existing database schema from one database engine to another. To perform a migration, DMS connects to the source data store, reads the source data, and formats the data for consumption by the target data store, where it can then load the data into the target. DMS also provides the ability to monitor the migration so that you can keep an eye on everything happening. We'll be going into more detail with DMS and the schema conversion tool later, but that should provide you a good starting point. Until next time.
So far, we've covered how to migrate servers and data to the cloud, and now I'd like to talk about database migrations. it should come as no surprise that AWS has a service aimed squarely at helping you to perform this task. It's called the AWS Database Migration Service, or DMS. You can use DMS to migrate your data to and from most widely used commercial and open source databases. The service supports migrations to and from the same database engine, like Oracle to Oracle, and also migrations between different database platforms, such as Oracle to MySQL, or MySQL to Amazon Aurora. You can also use DMS to migrate your on-premises database to a database running on Amazon EC2 instances. DMS can be configured to perform an ongoing replication, which can allow you to migrate databases with zero downtime. AWS Database Migration Service also provides a schema conversion tool, which we'll cover more in depth later, to help convert stored procedures in Oracle and SQL Server to equivalent code in the Amazon Aurora MySQL dialect of SQL. When a piece of code cannot automatically be converted to the target language, DMS will clearly document all locations that require manual input from the application developer. You can use AWS Database Migration Service for both one-time data migration into RDS and EC2-based databases, and also for continuous data replication. DMS will capture changes on the source database and apply them in a transactional, consistent way to the target. Continuous replication can be done from your data center to the databases in AWS, or in the reverse, replicating to a database in your data center from a database in AWS. Just a quick note, to use AWS DMS, one endpoint must always be located in an AWS service. Migration from an on-premises database to another on-premises database is not supported. During the video on the Database Migration Service, I mentioned a very powerful tool called the Schema Conversion tool. This tool allows you to take an existing database and convert its schema to a different engine. I thought it would be helpful to show you a quick example use case of the tool in action, and show you the report it can generate. For this example, I've set up an EC2 instance running SQL Server. This will also be the server that I run the tool and do the demo from. What we're looking at is that server. We're going to pretend that this is our on-premises SQL Server for the demo. Since we're on the machine, let's take a look at what we'll be converting. I've loaded up a sample database called Bike Stores. We can take a look at the database, and we see that there are multiple tables that we'll need to convert. If we do a quick query on one of the tables, we can see that there are several columns and rows of data that will need to be converted. Looks like we have about 1,400 customers listed in the table. Before we're able to start converting, we'll need to set up our destination database. Since we want to make full use of AWS, I'll be converting to an Amazon Aurora MySQL compatible database. In the AWS Management Console, we'll jump over to the Relational Database Service, RDS. We'll click Create Database, and since Aurora is the default option, we just need to change a few items. We'll name the database SCT Target, and the rest can be left at defaults. Now we can create the database. We can see in the console that our database is currently creating. After a few minutes, it will show as available, and we can continue. Now we'll move over to the Schema Conversion tool, which I've already installed. We'll need to create a new migration project. I'll leave the default name and location. Under the engine type, we'll select SQL Server, and after clicking Next, the tool will analyze the database to find available schemas. We'll select our Bike Stores database, click Next, and the tool will begin to analyze the database. Once the analysis is complete, a summary report is generated, which tells us how much of the data that SCT will be able to convert. We'll come back to this data in a few moments. To configure our target, we need some information from our newly created database instance, specifically the endpoint address, which we'll enter in the server name field. Once we fill in the rest of the fields, we can test the connection, then proceed once successful. After clicking Finish, we're shown the Schema Conversion Tool project page. To get a nice assessment report, we can go to the View, Assessment Report view. On this page, we see that SCT will be able to convert 100% of our database objects. I've also created a database, AdventureWorks, that SCT has identified some issues with. Let's take a look at the assessment report to see what actions it recommends. We can see under the Action Items tab that there are several issues listed. If we drill down into one of the specific examples, we can see the code that currently exists in the SQL database and the tool's recommendation to perform a manual conversion. Depending on your database, you may or may not run into conversion issues like this. That's a quick look at the assessment capabilities of the Schema Conversion tool. The tool can be used in conjunction with the Database Migration service to convert your database schemas and to migrate objects to a new target. I've added links in the course notes for additional reading.
While we're talking about data store options, it's important to bring up Amazon Aurora. Aurora is a MySQL and PostgreSQL compatible database engine offering within Amazon Relational Database Service, known as RDS. Aurora is designed to provide multiple times the throughput of traditionally available database engines, but without having to make drastic changes in how your applications access your data. It is a fully managed and distributed system that is able to meet the higher levels of performance by utilizing an SSD-backed virtualized storage layer specifically built for database workloads. Additionally, Aurora's storage is fault-tolerant and self-healing. Disk failures are repaired in the background without loss of database availability. Amazon Aurora Serverless, which is a configuration that can be used for Aurora, is an auto-scaling solution where the database will automatically start up, shut down, and scale capacity up or down based on your application's needs. It enables you to run your database without the difficult task of database capacity management. In the context of migration, especially when you start looking for how you can optimize your application's performance in the cloud, solutions like Aurora and Aurora Serverless can be very helpful. Aurora allows you to manage using the DB class sizes, and reads can be scaled out by distributing requests across the read replicas. If the workload changes, the DB class size and number of replicas can be adjusted to meet the changes in demand. While this is a functionality that exists, it's best suited towards predictable workloads. With Aurora Serverless, you can create a database endpoint without specifying the DB instance class size. Instead, you set the minimum and maximum capacity. The database endpoint connects to a proxy fleet that routes the workload to the fleet of resources that are automatically scaled. Database client applications don't need to change to use the proxy fleet. Aurora Serverless manages the connections automatically. The reason that the scaling is so rapid is because it uses a pool of warm resources that are always ready to service requests. I highly recommend that you look further into Aurora and Aurora Serverless to see if they possibly fit your optimization needs when migrating. The course notes will guide you to the documentation for these options, and I'll talk to you later.
During a migration, there will come a time when you need to connect your network to AWS. Depending on your migration, you might even be running in a hybrid scenario, systems both on premises and in AWS. Beginning with the discovery phase, we'll have a need for agents to report their findings back to AWS. During the migration, we'll need to be able to transfer data like our virtual machines, storage volumes, and databases. After the migration, we'll need to be able to perform tasks like monitoring, ongoing replication, and potentially additional data transfers. AWS services are delivered over the internet. For many actions and activities, we can simply use the AWS Management Console or AWS Service APIs, which only require an internet connection to access. Many administrative tasks can be accomplished in the Management Console. When we start getting into automation and tools, which Seth will talk more about, we begin to get away from the Management Console and begin interacting with AWS APIs. However, when we want to talk with our own resources running inside of AWS, there are very few occasions when we would want to make those connections or perform those tasks over the open internet. I wanted to quickly cover two options that we have to securely make the connection from your on-premises network to your virtual private cloud and AWS services. The first option is one that many people will be familiar with, VPN over the internet. There are several options for creating and configuring a VPN connection, and we're not going to dive into that in this course. The important part for our migration is to understand that this connection establishes a secure tunnel or link from your network to AWS. With the right configuration, the resources that you have running in AWS can be seen as an extension of your on-premise network. In this example, we're still using our internet connection to talk with AWS and our resources in AWS, but the VPN tunnel allows for that communication to happen securely. If your migration or operational requirements need dedicated bandwidth to talk to AWS, or you have a requirement to not use the open internet for communication, there's AWS Direct Connect. Direct Connect links your internal network to a Direct Connect location over a standard 1 gigabit or 10 gigabit Ethernet fiber optic cable. With this connection in place, you can create virtual interfaces directly to the AWS Cloud, for example, to Amazon EC2 and Amazon S3, and to Amazon VPC, bypassing the need for public internet in your network path. You can also establish a VPN tunnel over the Direct Connect link, allowing for a secure tunnel of communication from your on-premises resources to the resources in AWS. These connection options can allow for AWS to act as an extension of your network, which enables smoother data transfers, migration cutovers, and ongoing replications. Network design is an important part of your AWS infrastructure. During the migration planning phase, you'll want to ensure you plan for how your systems will talk to each other.
All right, so let's say theoretically you're up and running in AWS. You've taken the time to plan, evaluate, and move the necessary components over. You've tested the applications and are pretty sure they're going to be okay. Now that it's all running, how are you going to do the actual cutover? Can you afford any downtime? Is there a risk of data loss? What do you do if you experience any errors that you weren't expecting? As with all of the other questions we've presented in this course, these are important to ask early and to have a plan in place long before it's needed. So let's talk about two main deployment or cutover methods. The first one is called red-black. In the red-black method, you have your original environment, you have the new environment, and they're both running. You've set up the records and DNS for both endpoints, and data is being replicated across the environments. Once everything is ready to go, you simply switch the DNS over to the new environment. There, you're done. Well, sort of. In this method, you still keep the original environment running, and if you experience any issues with the migrated application, you can cut back to the original. The next method, commonly referred to as blue-green, is very similar. Setup is the exact same, with both environments being up, tested, and running, and DNS setup is still there. The big difference here is that your cutover needs to be more gradual. With this setup, instead of an instant cutover, you're only shifting a small percentage of traffic at a time. maybe 5%, maybe 10%. It's up to you how you want to manage it. The major reason for this is to avoid downtime. In red-black, if you have an issue once traffic has been shifted, the application could be down until you're able to move traffic back to the original environment, which could negatively impact any users of the application. With blue-green, issues are less widespread, and the number of affected users due to an issue is easier to manage. Though that doesn't mean blue-green is without its limitations. One of those limitations is that in order to do a blue-green deployment, you have to be using a DNS service that gives you the ability to control the amount of traffic going to each endpoint. While Amazon Route 53 does have this capability, not all DNS services do. Another limitation of blue-green is that this method requires a lot more management. Shifting the traffic over little by little can require some manual effort, which may not be wanted. Outside of that, there is a major consideration to keep in mind for both of these methods, and that is you need to have monitoring in place to evaluate if any issues are encountered. If you aren't able to identify that errors are occurring, then it's difficult to know whether you need to move back to the original environment or not. Well, that's it for now. Keep these deployment methods in mind and make sure you're evaluating which is best for the specific application you'll be migrating. Week 1 was about understanding migration. Week 2 was about planning and knowing your current environment. And in week 3, we looked at some services that can help you with your migration. Now that we're in week 4, we're going to specifically cover topics around the act of migrating your applications. This week, make sure you're continually going through the notes and readings, and good luck completing the course. Cheers. AWS is API-centric. Hopefully you find that news relieving. Over the past few weeks, we've been looking at a lot of the tools that AWS has that help with merging environments when migrating. But if you had to work with those tools manually, one by one, only through a management console, it would likely drive you crazy. So, to make life easier, AWS is API-centric. What I mean by this is that a large majority of AWS services and tools have directly accessible APIs that you can use for creating, configuring, and managing the services you employ. The reason I bring this up is because especially when you're trying to handle the very difficult and sensitive task of migrating data and applications across environments, handling everything manually is going to cause a lot of headache, a lot of troubleshooting, and timing is going to be very difficult to predict and test on a large scale. If, on the other hand, you're able to automate many of the tasks, the scale of what you can do grows exponentially. Essentially, it goes from a mad scientist running around flipping all of the levers and switches to a better equipped mad scientist monitoring what's going on while their assistants are able to handle all of the tasks. To access the APIs within AWS, there are a couple of options. One, you can use the various SDKs that provide access to the interfaces. And two, you can use the AWS Command Line Interface, or CLI. Both of these give you direct access that allows you to fine-tune and test what you need to do and takes away a lot of the manual effort that you would otherwise have to deal with. The power of these are that they allow you to create scripts and applications to handle a lot of the work, not only during migration, but also when managing, optimizing, and configuring your environment post-migration. It is very important that using the APIs becomes habit as soon as possible. If you're not already familiar, I highly suggest you start with the AWS CLI. This is a toolset that is easy to install locally and gives you the ability to do anything you would be able to do in the management console and more. Try out different tasks, test your various scripts, and see how it can help you. Continuing on with the discussion about automation, there are some additional tools that should be reviewed. Here, we're going to look at AWS Systems Manager and AWS CloudFormation. CloudFormation, which many of you are already familiar with, is an infrastructure and configuration automation tool that enables codified infrastructure. CloudFormation gives you the ability to have one or more templates that can be used to create, configure, and update your infrastructure through the CloudFormation engine. This becomes very helpful in migrating because it gives you the ability to quickly spin up test environments that will look exactly like your production environment. You can test configurations, spin up the full environment with a few clicks or a single command, and then tear it down once you've gotten the data you're looking for. The biggest learning curve with CloudFormation comes in creating templates, but luckily for you, there's a lot of documentation and reference material on this, as well as various tools that can help you put a template together from either sample templates or from scratch. Moving on, with AWS Systems Manager, you have a way to do exactly as the name suggests. You are managing your systems. Systems Manager gives you a path into the servers you are running that enables you to run commands, schedule updates, and manage various other tasks from a single point. When managing a fleet of servers, the ability to run a command on the entire fleet without having to directly connect to any of the servers individually saves time and effort. Another major benefit of this is that it allows you to manage systems not just in AWS, but also with your on-premises servers. It has this ability because it uses an agent, the Systems Manager agent or SSM agent, that can be installed on both Amazon EC2 instances as well as your servers running locally. As long as they have some connectivity to AWS, you can have a single access point to manage cross-environment fleets. These tools are just some of the additional options you have when it comes to automating tasks that can aid in migration. The notes have some links that will further share some of the features that they provide, as well as ways to get started. I highly suggest you take a look. Over these few weeks, we have looked at how important planning is when it comes to migrating, brought up important questions when evaluating both where you are and where you're wanting to go, and looked at a lot of tools that can help with your migration. Now, I want to talk about one of the solutions that helps you with everything as opposed to just one aspect of the migration. TSO Logic is a solution that exists within AWS to provide insight into what you currently have and give you options into what you may want to utilize in AWS. This can be done as a pre-migration step or as an ongoing analysis to ensure that you are always running each application in the best place with the right software, even as your environment and prices change. TSO Logic provides discovery of your existing resources to help identify what you are running in your compute, storage, database, and other areas to help evaluate what your total cost of ownership, or TCO, is for various applications. We then are able to use predictive analytics to help determine the best fit for your workloads in the cloud. Using data-driven methodology and continuous visibility will help to provide ongoing insights and predictive analytics for all of your workloads. TSO Logic, as well as many other tools, can help you with both specific parts of your environment as well as full migration assistance. I highly recommend looking at what options you have and finding what will help to make your migration as easy as possible. Another tool in the toolbox to help you with migrating is called CloudEndure. It's actually a little misleading to call CloudEndure a tool. It's more of a fine-tuned machine that enables a much easier end-to-end migration into AWS. CloudEndure Migration simplifies, expedites, and automates large-scale migrations from physical, virtual, and cloud-based infrastructure to AWS. It automatically converts any application running on supported operating systems, enabling full functionality on AWS without compatibility issues. Continuous data replication takes place in the background without application disruption or performance impact, which ensures that data is synced in real time and minimizes cutover windows. When migration cutover is initiated, CloudEndure executes a highly automated machine conversion and orchestration process, allowing even the most complex applications and databases to run natively in AWS. The continuous data protection engine works in memory, neither taking snapshots nor writing any data to disk, which means near zero impact on performance. Furthermore, Cloud Endure is designed for large-scale migrations and enables the replication of data from thousands of machines simultaneously without performance impact. After initial replication, you can spin up all of your machines in parallel as well as execute any post-migration scripts at scale as necessary. You can also manage the entire migration lifecycle and verify your readiness for cutover directly from the Cloud Endure console. Lastly, Cloud Endure gives you the control to test your target machines as often as you like in preparation for cutover by just clicking a button. It also provides you with the ability to quickly and easily shift your environment to AWS from existing physical or virtual data centers, private clouds, or other public clouds. As you can see, while you can work on migrating your environments yourself, using the tools and creating your own applications and automation scripts to handle your environment transfer, tools like Cloud Endure can help to make the whole ordeal much easier. The notes will have further information on Cloud Endure. Make sure you review them to see if this might be a good solution for you.
As we've seen over the last few weeks, there are a number of tasks that you'll need to perform in order to plan, prepare, and perform your migration. The good news is you don't have to do it alone. The AWS Migration Acceleration Program, MAP, is designed to help enterprises that are committed to a migration journey. MAP was created to provide consulting, support, training, and service credits. The goal is to reduce any associated risks with migrating to the cloud, to build a strong foundation for the operation, and to help offset the initial costs. The program includes guidance and methodologies for migrating legacy systems, as well as a suite of automation tools to help speed up more common migration scenarios. AWS also maintains a partner competency program, which allows companies in our partner network to demonstrate and prove their expertise in areas like migrations. Successful completion of a migration can be aided by leveraging the knowledge and/or tools of migration partner solutions. There are several different types of partners that can assist with your migration. Migration delivery partners are able to help with every stage of a migration, including getting hands-on. Migration consulting partners provide expertise and training to help enterprises quickly develop specific capabilities or achieve specific outcomes. Migration technology partners provide the tooling and automation to help with all phases of a migration, from discovery to workload migration to data migration. A migration isn't likely to be something that you tackle completely on your own. When it comes to migrations, the best approach is to leverage all the tools and experience at your disposal.
As we're drawing to a close for our course on migration, I wanted to take a moment to quickly review the application migration types. What we covered in this course were, as we frequently call them, the 6 R's. They consist of rehost, replatform, repurchase, refactor, retire, and retain. Starting with retain, this focuses on identifying components that are either not ready or not necessary to migrate. Oftentimes, when retaining will be used, it is important to consider if and how your migrated infrastructure and your retained infrastructures will need to communicate, and set up the appropriate and secure channels to do so. With retire, you still need to identify what components may not need to be migrated, but for the purpose of evaluating what will not be needed by both the migrated environments as well as any retained components. Once the evaluation is completed, the unnecessary pieces are eliminated and the applicable components are migrated. With refactoring, also seen as re-architecting, you look not only at what needs to be migrated, but also at how that particular application might be re-architected to better utilize the advantages provided by the AWS Cloud. Shifting from a traditional architecture to a service-oriented architecture, for example, could be one way that you refactor your application to move into the cloud. Now, repurchase, replatform, and rehost are all very similar, but of course have their minor differences. With rehost, you are looking at as close as a one-to-one migration as possible. In this case, you are looking to move quickly with minimal changes. With replatform, you're still looking at a similar move, but also considering what might provide a small and easy optimization to your performance or usability. For example, replacing a server running a database engine with an Amazon Relational Database Service instance. This could make your database usage a bit easier while maintaining or improving performance. And with repurchase, you are looking at places like the AWS Marketplace for ready-to-run services configured for the cloud that will get you features that you're looking for without requiring you to custom build a solution. Something that might fit into this category would be purchasing a firewall from the AWS Marketplace instead of trying to import or configure your own on an Amazon EC2 instance. Over the course of the class, we focused on rehost and replatform, but it is important that you look into all of these options for your possible utilization. The last thing I want to say about these is that it is very important that you look at your application's specific needs to find the method that will work for the various use cases you will encounter. Trying to force a single method for all of your migrations will bring about a lot more problems than solutions. Individually evaluate, make your plans, test your plans, and then reformat the plan if necessary. As we stated earlier, the more effort you put forth on the front end of your migration with evaluation and planning, the easier the actual work will be. We've spent the past several weeks talking about the importance of planning and analyzing your migration, looking at services that can help during different phases of your migration, and even briefly discuss some of the AWS tools and partners that can help with the full migration. That final topic is where I want to focus in this video. When migrating large enterprise applications, in all reality, it's going to be better to utilize a third party for your migration. One of the reasons for this is simply the level of knowledge needed. It's a lot to ask of people internally tasked with migration to become experts in all of the services they're going to be using. The steep learning curve to go from novice to expert can be overwhelming and mistakes are easily made. With AWS partners, they have built the knowledge up over years of experience working with and helping other customers migrate to AWS. And that brings us to another reason: experience. AWS partners aren't working on their first migration, but have been doing migrations and consulting for a while. They have been hands-on, have seen a wide variety of scenarios and use cases, and can offer solid advice with other questions you may have around migrating your applications. And lastly, AWS partners often help to provide faster migration timelines than would be possible if you had to learn, evaluate, and test the services while also trying to analyze your infrastructure and plan your migration needs and steps. When it comes to crucial or large applications and environments, we highly recommend looking to an AWS partner to help. It is still important for you to learn about what they are doing and the services involved in order to be able to ask the right questions and easily get going once migrated. But the partners themselves can help greatly with the actual migrations you need to do. The course notes will have a link to our partner page. I highly recommend you look through these to help you identify when you might need a partner, the options you have, and which partners might work best for your needs. Hello everyone. I hope you enjoyed our course about migrating to AWS. Over the past 4 weeks, we looked at topics around defining migration, reviewed migration methods such as the 6 R's, stressed analyzing your environment and needs, urged you to plan your migration, covered some services that are commonly utilized during migration, and looked at actual migration steps. While it was all very conceptual, I hope you were able to take away some concrete actions and ideas for you to use as you plan and evaluate your needs around migration. Keep track of your notes and the links that we provided in order to help you with your continued learning. And good luck with any future migrations you find yourself working with. I'll see you in another class.
Welcome to AWS Fundamentals, Building Serverless Applications. By now, you've probably heard of the buzzword, serverless. Ever wanted to know what that actually means? Ever wanted to know how to build data-driven applications in the cloud as fully serverless? Well, you're at the right place. Hi, my name is Rick, and I'm the technical architect for this course. As the name implies, we're going to focus on building a serverless application. This course won't be just videos. You'll be able to do exercises at your own pace, so you'll get some hands-on experience with our serverless products and services. Although there are tons of serverless offerings from AWS, we only have a few sessions together, and so we have to be a little bit savvy with which services we choose to include. We decided on these: Amazon Lex, Amazon API Gateway, Amazon Cloudfront, AWS LAMBDA, Amazon S3, Amazon Cloudwatch, AWS IAM, and Amazon Dynamodb. Now that's an awful lot of content to get through, but don't worry, even if these things are brand new to you, we'll take it real slow. Besides, we have some stellar instructors on hand to help you through each week, along with some fun exercises along the way so you can get some hands-on experience actually using them. So here's how the exercises are designed. Each exercise is going to build a serverless component, and as we progress through the course, each one will tie into the other. This way, the end result will give you a website that touches on everything you've learned. I'm going to ask you to refer to the course notes about how to set up your environment for these exercises. Anyway, I bet you're keen to get started and build a serverless application, right? Or at least find out what serverless means. So before we jump into the lessons, I'd really like you to meet the instructors. This won't take long. Then Wes, and you'll meet him in a second, will introduce what we're going to cover in this first week. Then I'll come back and talk to you about your first exercise of the week. Okay, let's get to know the trainers.
If I wasn't a trainer, what would I be doing? I'd probably be a full-time scuba instructor, living on a sandy beach or a boat somewhere, teaching people how to dive.
I would prefer to spend time at home with my 3 German Shepherds, my husband, and working on renovating my 200-year-old house.
Still be in education in some capacity, whether teaching at a high school or at the college level.
I'd probably still be a trainer like those other guys, because that's an awesome job as well. Not as good as my job.
I love maple syrup. As a French Canadian, I have my own maple farm.
My favorite AWS service is Simple Storage Service, or S3.
It's probably SageMaker.
Route 53.
S3.
Certificate Manager.
I really love DNS. I don't know what happened to me when I was young, but I probably fell in the soup of DNS somewhere.
I love being an AWS trainer because I get to meet new people, teach folks how to embrace the power of the AWS Cloud.
I think the ability just to travel around and meet our customers face to face and hear about their technology challenges and help them solve real-world problems.
I get to meet new people every week and help them with their technology dreams and their goals.
It's being able to see that light bulb go off and on in the head of our students while you're teaching, and then you know that from this point on they're going to do something amazing.
I get to work in different teams and different projects, so nothing ever gets stale. And it's always really interesting because there's a million different projects going on in parallel. It's a colossal firefight, but it's great fun.
My favorite monkey has got to be the macaw. They're just so clever and good to eat.
So, you just met our instructors. Well, remember Wes? I mean, who can forget Wes, right? Well, he's going to talk to you in a sec about what we're going to cover in week 1. And he'll talk to you about what is serverless and what that even means. But before I hand you over to him, I just want to explain what we're going to cover in terms of these weekly compounding exercises. Now, in my intro earlier, I shared with you which services we're going to cover throughout the whole course. But what I haven't shared with you yet is what we're actually going to build. So, what is the most important, pressing question in our lives today? I know what mine is. It's not what's the meaning of life. It's not how come pizza tastes so great in New York. No, the most pressing question in my life is it too cold for my cat to go out? You all have cats, right? Yeah, you all have cats. Well, if you don't, you can at least pretend you do so you can play along. So this website is just a bit of fun. It's actually a really great way. Even though it is fun, it's a great way to expose multiple services to you that are all serverless. And they're going to build upon each other. And it doesn't take much mental gymnastics to map out some or all of these concepts into actually useful applications. So what I will do is before each exercise, I'm going to have one of the team introduce you to a new core serverless concept, and maybe a demo or two just to touch on some relevant high-level paradigms. Because this will help you hit the ground running when you actually do the exercises. Naturally, I've included copious notes in the exercise guides to help you along. And don't worry if you're not a programmer. This course is introductory level. It's not designed for hardcore developers, although you might get something out of it if you are. But you won't be writing any code. At most, it will be a copy and a paste here and there. By the end, you should have a working cat weather voice-enabled data-driven serverless website. Now, obviously the website itself is just a bit of fun, but our aim is that during this iterative process, you'll actually learn a lot of really cool stuff relating to serverless that you can take out there into the real world. All right, take it away, Wes.
Hi, I'm Wes, and today we're going to answer the question, what is serverless? A serverless architecture is a way to build and run applications and services without having to manage the infrastructure behind it. Your application still runs on servers, of course, but the server management is done by AWS. You no longer have to provision, scale, and maintain services to run your applications, databases, or storage systems. With a serverless architecture, you can execute your code only when needed and scale automatically, from a few requests per day to thousands of requests per second. And you only pay for the compute time you consume. There is no charge when your code's not running. You can run code for virtually any type of application or back-end service, all with zero administration. So why use serverless? Well, serverless enables you to build modern applications with increased agility and lower total cost of ownership. Building serverless applications means that your developers can focus on their core product instead of worrying about managing and operating servers or runtimes, either in the cloud or on premises. This reduced overhead lets developers reclaim time and energy that can be spent on developing great products, which scale and that are reliable. So what are the benefits of serverless? Serverless has four main benefits. 1, no server management. There's no need to provision or maintain any servers. There's no software or runtimes to install, maintain, or administer. All of that is taken care of for you. 2, flexible scaling. Your application can be scaled automatically by adjusting its capacity through toggling the units of consumption, for example, throughput or memory, rather than units of individual servers. 3, you pay for value. You pay for a consistent throughput or execution duration rather than by the server unit. And last but not least, automated high availability. Serverless provides built-in availability and fault tolerance. You don't need to architect for these capabilities since the servers running the application provide them by default. A serverless model, therefore, is inherently highly available. So let's get started building your first serverless app.
Hi, John here. I would like to introduce you to chatbots. You may have heard the term before, as they are quite popular these days, and we will see why today. The term itself is derived from chat robot. Why would we need a chat robot? If you think about a chat interaction you may have had with a support team, think how long you waited in line. I don't know about you, but I've had bad experience where I waited for up to 15 minutes until an agent was available. In many cases, what I was asking was fairly simple and could have been executed by asking me a few questions ahead of time. This means that when it was my turn with the agent, I was bogging them down for a few minutes while they couldn't attend to anyone else. The majority of those minutes were spent on the agent asking me questions or redirecting me to another agent for my particular problem. What if instead I could have asked my questions or told what I wanted to do already in the chat ahead of time? Then if I was missing information to complete what I was trying to do, I could have asked I could have been asked a few more questions. So what I'm looking for here is a robot. However, this machine needs to be highly engaging and provide conversational experiences through text or even voice. Okay, so what are our requirements here? I need a bot that can take both text and may send over a chat in Facebook, Messenger, Slack, or via SMS or an audio input. If the input method is text, the machine can start parsing what I have typed. However, if it's voice, the bot needs to take that input and recognize what was said to transfer the audio to text. That's what we call automatic speech recognition, or for short, ASR. Let's take an example here. I would like to book a hotel in Boston for 5 nights. I'm either sending this text as this data as text, or I could also use my voice. So let's add this voice in here. If I was to use my voice, then it needs to be converted into this text that you see at the bottom. I would like to book a hotel in Boston for 5 nights. And that's what automatic speech recognition will do for us. So the voice data plus automatic speech recognition equals to I would like to book a hotel in Boston for 5 nights. As humans, it's very easy for us to understand what the user wants, that the user wants to book a hotel. We also understand that it's in Boston and then that there is 5 nights. For a machine though, it's a bit more complex. It needs to act as a human to parse that text, to recognize the intent of the text. It needs to deduce what the speaker actually means, and then not just the words that they say here. That is what we call natural language understanding, or NLU. In this case, the bot will need to figure out that it's a hotel that the customer needs. So, in this case, it's a hotel. And figure out that they have already provided information about the city where they're trying to go to. So this is Boston in this case. And it's for 5 nights. If we were to start a hotel search for this data here, we will need some more information. For example, for which date? This is where the agent has an interaction, a back and forth with the customer. For a human, replying with their voice or text isn't an issue. So if the user used the text to interact with that human, they will be able to reply back with that text. If it was with voice though, it's a little bit different. The human can reply back with their voice. However, for a chatbot, replying with text isn't much of an issue. But if the customer used their voice to do the interaction, the chatbot also needs to reply back with the same modality that was used by the customer in the first place. So the customer, instead of using the chat, will use audio again. The process of translating this text that you see on the left-hand side that the robot wants to send into a voice data, that is what, so this process right here is what we will call text-to-speech. Now, think about our agent example from earlier. That agent will need to ask those questions to the customer and wait for their answer to start that processing. In fact, that agent also needs to ensure that the city, the date, the type of bed are all viable answers. What if the user provides a date that was in the past because the question was misunderstood? Well, that's time that the agent isn't spending with another customer. If we were to replace the introduction of this interaction with a chatbot, it could ask all of those questions to the customer in a conversation and send the data back to the agent that is already validated. It could validate all of the entries from the user and even provide some information back to know if there are availabilities for the dates requested before forwarding it to the agent. This was an example of a call center application. There are many other use cases, like a personal assistant to order groceries or booking medical appointments. It could be used for enterprise productivity where the chatbots can be integrated with enterprise backend systems such as an inventory management program or HR system. They can be built to check sales numbers, marketing performance, inventory status, or perform employee onboarding. In the end, it's a modality of interaction with a machine via text or voice. The three components required for that are automatic speech recognition, natural language understanding, and text-to-speech. This sounds like a lot of work. You'll need to hire some machine learning experts that aren't scared of mathematics like I am to start building all of those three functionalities. Once they will be done with building those functionalities, which will take time, you will finally be able to build your backend processing. Think about the amount of time that this will take. Meanwhile, your customers are waiting for you to provide more options. How can we accelerate this time to build those functionalities? Well, AWS already built those. Have you heard of Alexa? Most know her as the answering voice from the Echo device suite, as you can see here. But she can be heard from many other devices as well. This sounds all great for physical devices, but what we are looking for here is a way to add a chatbot on our website, or maybe in our Slack channel, or even our Facebook page. Well, let me introduce you to a service named Amazon Lex. It provides the advanced deep learning functionalities of automatic speech recognition and natural language understanding that powers Amazon Alexa. So let's add Lex into here. But what about the third functionality here, for text-to-speech? Well, this is solved by using the Amazon Polly service. Amazon Polly is a text-to-speech service that uses advanced deep learning technologies to synthesize speech that sounds like a human voice. As of today, it includes over 50 lifelike voices spread across 28 languages. Now, those are two different services. While Lex integrates with Polly automatically when the user interacts with Lex via speech. It sends this text to synthesize to speech to Polly, which in turn returns an audio file that is then sent back to the user. This means that the barrier of entry for those three functionalities is minimal, as you don't need a machine learning background to develop any of those. You simply use the service with a pay-as-you-go model. In the previous lecture, we discussed what a chatbot is and then learned that Amazon Lex is the service to use to build one. In this lecture, I will demonstrate how to use Lex using the AWS console. Instead of building an entire bot from scratch, I will use a sample. This way, if you want to follow what I do during the demonstration, you can. Let's start at the Lex console. Lex is available in 4 different regions as of today. You can see all of those regions up here. Let's start with creating the bot by clicking Get Started. You can see 2 main options here, where I can decide to create my own custom bot or use a sample. Let's look at the sample for a few minutes. Here you can see the definition of the bot. I have Book Trip as my bot name. This bot contains something that we call an intent. An intent is a particular goal that the user wants to achieve. So the user sends a few utterances. The utterances are things like, I'd like to book a hotel. So that utterance is sent into the bot. The bot will now look at part of all of its utterances and will try to match it to one of those intents. This time, it's pretty easy. It's the book a hotel intent. Next, we don't have all of the information to be able to book a hotel. So we need to start asking a few more questions towards the user. Well, those questions are sent via something we call a prompt. This prompt, as you can see as sure, in which city, will ask the user for that question. The user will now answer that question by saying, hey, New York City. And then that will fill something that we call a slot. A slot is data that the user must provide to fulfill the intent. There are required slots. And then the bot will need to have the answer to every one of the slots to be able to fulfill this entire intent. Once all of the required slot has been filled, it is now time to ask the user, hey, are you sure you want to book the hotel in New York City? Make sure that we confirm all of those slots that has been filled. If the user answers yes, it is now time to fulfill this bot or fulfill this intent. The fulfillment is the business logic required to fulfill your entire goal, your intent here. So if you have to make a call towards your backend to say, hey, I'm ready, I'm done with the input of the user, I want to send that towards my backend to book my entire hotel. There are two ways to interact with Lex. If you remember our previous lecture, you either send the data as text or you send it as a spoken statement. When you interact with Lex using speech, it makes use of Amazon Polly to convert prompt and confirmation text to speech. This is why Lex requires a role to allow the service to call Polly. Here's our role. We will discuss roles on week 3, so I'm not going to go through it now. The last step to create this bot is to specify if this bot is subject to the Children's Online Privacy Protection Act. In this case, I'm not subject to COPPA. So I'm going to answer no. Let me show you the create your own options here, the custom bot. You can see here a few more options that aren't asked when I use a sample. Don't worry though, all of those options are configurable in the settings of the sample bot. Here we can see the language is set to English. That is currently the only language supported by Lex. Next, we have the output voice option to pick the different English lifelike voice that Polly is going to use. There is another option here called session timeout. This is used to specify how long the information of the user that was passed as session attributes should be kept. I'll go in more details about this concept in a later lecture. Let's go back to booking our trip with the sample book trip bot. I will answer no to COPPA here, and then I'll hit create. Let me explain the editor here. On the left menu, you can see a list of intents. So I have book car and I have book hotel. Below, you can find the slot types. That is a list of custom slot types, which I will discuss later in this lecture. You can also find the error handling section below. Let's take a look at it. In the case where the bot can't match the ask of a user to an utterance in an intent, it will retry twice, as you see it right here, by sending the clarification prompt that you can see at the top here. Sorry, what can I help you with? You can add more prompts and it will randomly select one of them, which makes the bot seem a lot more human. In the case where it can't understand what the user wants to either do by not being able to match it with a utterance in an intent, or when a user doesn't provide a valid answer to a prompt, one of the hang-up phrase will be used. In this case, it's sorry, I'm not able to assist at this time. Let's go back to the book car intent. I will close this prompt here saying that the bot was successfully built, and I'll remove the screen on the right-hand side just so that we have more space here. We have 3 utterances here. You can see make a car reservation, reserve a car, and book a car. You don't need to specify each one of the possibilities, as Lex utilizes natural language understanding, deep learning algorithm to expand those sample utterances. Sometimes, though, you may need to add a few more utterances that the model doesn't associate properly. I'll skip the LAMBDA piece initialization here because I will talk about it in week 4. Next, we have slots. Let's take a look at the second slot here, pickup date. We see that it's required because there is a check mark next to it, which means that we won't be able to fulfill this intent until this slot is filled. Next, the slot is of type built-in Amazon.date. There are many built-in slot types, and all will start with the Amazon prompt, as you see there. This particular one will take a date entered by a user and transform it to a date that machines can understand. For example, using tomorrow and transforming that to 2019-02-21. A machine can understand that. Then we have the prompt. You can configure what question is asked of the user to fill this slot. Again, you enter a few of them. What day do you want to start your rental? Lex will randomly select one. You can specify the maximum amount of retries as well here, in case where the user enters a wrong entry until Lex returns the hang up phrase we saw earlier in the error handling. Also, you can specify different utterances here that the user may use to answer the question. Typically, those aren't required for simple answers like the date, but sometimes the user may bury the answer into a very long sentence and Lex can't find it. That's where you will add the utterances here. Let's take a look at another slot here. Car type. It is the last slot. Does that matter? Well, the order is what Lex uses to order the different prompts it will ask to the user. So yes, it does matter. The slot type this time is car type values. That doesn't start with Amazon. So it is a custom slot type. Let's take a look at it. Car type values. The slot resolution option is important here. You can specify to restrict values to only the ones you add below. Restricts to slot values and synonyms. You can then add synonyms which will match back to the original value on the left-hand side. If a user specifies a synonym, the actual value on the left-hand side is what will be sent back as the result or as the fulfillment of this slot. So that makes it easier on your business logic. Alternatively, you can configure the slot type to expand on the values. Slot values will be used as training data, and the slot is resolved to the value provided by the user if it's similar to the slot values. There are many slots here. As you can see, there are 5. It seems like there will be a lot of back and forth between the bot and the user to fulfill every single one of those slots one at a time. What if the user was to provide a few or all of the slots via the returns? Well, let's check it out via the book hotel intent to see that example. You can see that the first utterance references some slots this time, nights and location. To do so, you use the curly bracket and the name of the slot in between. Now that means 2 less slots to fill, one with prompts for the user. Isn't that great? When all of the slots are filled, it will be good to confirm with the user that everything that was understood by the model is right. The confirmation prompts provides that. You can see that here again, we are using curly brackets. If the user finds an issue with the answers, they can answer or cancel by saying no, which means we will reply, okay, I have canceled your reservation in progress. At that point, the user will have to start again by invoking the intent via its utterance. If everything is fine, the user confirms that everything is right by saying yes, and then the fulfillment can start. This can either be done via LAMBDA, which we will discuss later in the course, or by sending back the parameters to the client. Once the client has all of that data, it can be sent to any backend of their choice. Think using JavaScript here to make an AJAX call with everything that the bot has understood to your business logic. The response section can be used to pass final messages back to the user or even give them the option to move to another intent at the end of our conversation. We've now created our simple bot. In the next lecture, I will modify the bot and introduce you to versioning and publishing. See you there. In the previous lecture, we built a bot from the samples. Now let's do some changes to our bot. But first, you need to understand the concept of versions. Bots, intents, and custom slot types all have versions. So version for the bot, a version for the book hotel intent, and even my slot type has a version here. Why are those versions required? It's to create immutable versions of your bot. You may have a bot version you use for dev, beta, and prod. They may each use a different version of intent, and those intents may use a different version of a slot type. The idea is to make sure that nothing changes once you publish a version of your bot. You can only edit the latest version of each of those constructs. Let's do a change by adding another utterance and save my intent. I'll add book a room. You can see that the version of my intent is still set to latest. The reason for that is that the new version of intents only gets created once the bot is built. First, I'll save my intent at the bottom of this page, and then I will build this intent. Amazon Lex is now building a machine learning model for our bot. This sounds way simpler than doing all of the work myself. No maths required here. This should take less than 1 minute. So with the power of recording, we'll fast forward that a bit. My bot is now successfully built. You can see now that I have 2 versions of my book hotel. Before we move on with the bot versions, let's make sure that this bot is actually working. I can do that using the test bot interface on the right, and I can now interact with my bot either via text or voice. Let's first try by text. Book and hotel in Boston. Whoa, this wasn't part of our utterance. Look at our utterance on the left-hand side. Yes, remember what I said about utterances? They are just samples, and the machine learning model that was built is doing the job of doing natural language understanding. You don't need to think of every use cases. That's why the model is there. You can also see that it detected that I sent Boston as the location below in the summary here. Location, Boston. It's now asking me to fill another slots in here. What day do you want to check in? I will enter tomorrow. Wait, tomorrow? That's not a date. Well, it kind of is. The bot took care of translating tomorrow into a date, as you can see it in the summary where it was translated to 2019-02-21. We now need an amount of night. How many nights will you be staying? 3. The bot again translated the word 3 into the number 3. So it's easier for a backend. Finally, I need to enter my room type. What type of room would you like? Queen, king, deluxe? Let me enter king here, as I love having all of the space in the world in my bed, even if it's just for one in there. You can see that all of the slots have been filled at the bottom of the screen. There's none of them that are null now. The next step is for a confirmation prompt. Okay, I have you down for an amount of night. Perfect, that's what the bot is returning me. I can revise the answers that were sent. Everything looks good to me. Let me answer, go for it. The intent fulfillment has now been executed. And if you remember our choice from earlier, I said to return the data back to the client with what the model has interpreted. You can see all of the data that Lex found. Let's try using my voice this time. I'm going to look at the book car. I don't need to, but it's just for you to follow me. The way that this web interface works is that once you click on the microphone icon, it will start recording. You need to click it again to submit the audio clip to Lex. So let's try it. I want to book a car.
In what city do you need to rent a car?
Wait, it just talked to me. How can that be? Lex only does speech recognition and natural language understanding. It doesn't do text-to-speech. Oh yeah, I remember now. Lex uses Amazon Polly, the service that does text-to-speech. Great. Now that I understand what's happening, let's converse with our bot. Seattle.
What day do you want to start your rental?
The day after tomorrow.
What day do you want to return the car?
On Saturday.
How old is the driver for this rental?
Oh, my age. Well, this is something very strange that happened to me when I hit 25. I just stopped aging. My official documents are just getting more wrong every year. So, 25.
What type of car would you like to rent? Our most popular options are economy, mid-size, and luxury.
Mid-size.
Okay, I have you down for a mid-size rental in Seattle from February 22nd, 2019 to February 23rd, 2019. Should I book the reservation?
Sure. Great. It sounds like this worked. I'll encourage you to play with Lex a bit more and try a few other utterances. If you see that one doesn't work the way you are expecting it, apply what we have learned in this lecture to add an utterance to get the bot to understand you, and don't forget to build the intent again. Now that we built our bot and tested it to make sure it does what it's supposed to do, it's time to deploy this bot. However, as you can see, it's still pointing to our latest version. I could point my application to this latest version and be done with it. But if I make any modifications, what do you think happens? I'm impacting my users, which isn't great for customer satisfaction. So I want my application to point to a version 1, 2, 3. Wait. That will mean that each time I modify my bot, I need to redeploy my application? That sounds pretty bad. Yeah, that will be. That's why you shouldn't do that. Instead, you should use an alias. Let's see that in action. I'll click on Publish. It asks me to create an alias version or update an alias version. An alias points to a version so that you can still only have one deployment of your code. Let me create a new alias. I'll call that prod. And hit the Publish button. This will take a minute or so to publish. So what did I just do? Well, by clicking Publish, it creates a new version, version 1. And then an alias named prod is created pointing to version 1 of our bot. Now that version 1 of our bot points to 2 intents, book car still at version 1, and book hotel, that's now at version 2. Now, I can go in my application and make it point to the prod alias without having to worry about making changes to the bot, as the only way to impact the application will be to publish the bot again and then change the prod alias to point to that new version. That's a lot of mistakes in a row if you were to have that problem. As you can see, book trip has been published. You can see version 1 of our bot right here. It uses version 1 of book car and version 2 of book hotel intent. I'm ready to use this bot in production now. Before we leave, I want to show you the monitoring tab here. It shows metrics over time to understand how your bot is being used and things like latency for the execution of your bot. The other important piece I wanted to show you is the uterance sections here. It is currently empty, which is normal. You can use it to view uterances that your bot did not recognize. Uterance statistics are generated once a day. You can see uterance that was not recognized, how many times it was heard, and the last date and time that uterance was heard. It can take up to 24 hours for missed uterance to appear in the console, and data is typically generated overnight, so don't wait for it yet. From this interface, you can select an uterance that was missed and then add it to your intent. So it is a good practice to review this list when you deploy new intents in your bot. In the next module, you will put to use what you have learned about Lex to do an exercise. Rick is waiting for you. Thanks for watching.
Hi there. Now that John has explained and demoed a simple chatbot, it's your turn. The end goal is to create a chatbot that tells you if it's too cold outside for your cat. Obviously a really important app. Initially though, to get things started, we'll create the world's simplest chatbot that elicits which city your cat's in, and then repeats back to you something like, you want to know if your cat can go outside in Seattle today. But we'll actually stop there and make it answer you a bit later on. But this is a great start as it gets all the plumbing in place for our serverless application. And by the way, working through the console is pretty straightforward. However, I will warn you, the console UI changes all the time. And probably by the time you're watching this, we may have moved things around a little bit, at least visually. So your console might not look exactly like the one you saw on John's screen, but rest assured the concepts still stand and you shouldn't run into any major problems to get it all working. And also, I've added plenty of notes in the lab guide, so I hope that helps. But if you do get stuck, please don't worry. You can always head over to the course forums. So in summary, here's what you're going to do. We're going to create a chatbot that elicits information from you about where your cat is. This, air quotes, conversation may go back and forth for a while, but once Lex has prompted you for all the information that it needs, or what Lex calls eliciting, it will simply confirm with you your request. And once you confirm to Lex that it got the question right, it's going to return to you what we call a fulfillment, basically echoing back what you asked it. And later on, we'll make this chatbot really smart and link it to some other great services like Amazon API Gateway and Amazon Dynamodb. But for now, let's keep things really simple. We'll get the most basic chatbot we can up and running. Okay, you ready? Great. Head over to the lab and enjoy. This is a fun lab.
Greetings, I'm Bobby, and in this course, we are going to learn how to use Amazon's Simple Storage Service, or S3, to host a static website. This is an example of serverless because you don't have to worry about managing the servers or patching them. Amazon's Simple Storage Service is an object storage service that offers industry-leading scalability, data availability, security, and performance. Amazon S3 is designed for 11 nines of durability and stores data for millions of applications for companies all around the world. This means customers of all sizes and industries can use it to store and protect any amount of data for a range of use cases, like websites, mobile applications, backup and restore, archive, enterprise apps, IoT devices, and big data analytics. Amazon S3 provides easy-to-use management features so you can organize your data and configure finely tuned access controls to meet your specific business, organizational, and compliance requirements. When we think about the three number ones with AWS, they are cost-effectiveness, security, and resilience. S3 helps you to meet all of these. I wasn't exactly thinking about alien, more like an earthbound threat, like a DDoS attack. One of the biggest advantages for using S3 is that you can host your website from an S3 bucket and reduce stress on origin or on your actual data center or AWS Cloud. This also minimizes your attack surface for your site, adding in an additional layer of security. It's cost effective because it's a frugal method for storage and website hosting, and you're also reducing traffic to your origin site, so you don't have to pay for more web servers by scaling vertically or horizontally. It works to help with your security by reducing your attack surface by not sending traffic to your infrastructure or origin. It's resilient. S3, using the standard S3 storage class, your data is being replicated in the background. We will discuss more about the different storage classes and other options available when you create your S3 bucket for your static website during the demo. Hi, and now I'm going to show you how to use S3 buckets to create a static, serverless website. We've already discussed why S3 is a great option. Now let's do it. I want to clarify that when I say static, I don't mean it can't be interactive. It can. You just can't use server-side processing code like .NET or PHP. You can use a client-side script like JavaScript. In my demo, I'm going to create a website that actually uses JavaScript to show you how easy it is. You can still set up your website to interact with other AWS services like Dynamodb or API Gateway and pull dynamic information by passing variables using query strings. I just bring that up so you are aware that your site can be dynamic, but your processing happens on the client side or using a service like API Gateway. You will learn more about those services later on in this course. To host a static website, you configure an Amazon S3 bucket for website hosting, and then upload your website content to the bucket. This bucket must have public read access. It is intentional that everyone in the world will have read access to this bucket. The website is then available at the AWS region-specific website endpoint. Instead of using the website endpoint for S3, you can also bring your own domain name, such as example.com, to serve your content. Amazon S3, along with Amazon Route 53, supports hosting a website at the root domain. For example, if you have the root domain, example.com, and you host your website on an Amazon S3 bucket, your website visitors can access the site from their browsers by typing in either example.com or www.example.com. For this demo, I'm going to use the AWS console, but you can also access S3 via the command line interface and software development kits. Here we are inside of the AWS Management Console. I can select S3 from here under my recently visited services or type it in using S3. Inside, this is actually going to show all of my buckets. And you'll notice at the top right-hand corner it says Global, which lets me know that these are all of the buckets in all the different regions. You can see I have some in Northern Virginia, Oregon, and Ohio. I'm going to click on Create Bucket. I have to come up with a unique bucket name. So I'm actually going to use my last name and put a 200 behind it. I'm going to go ahead and keep it in the Northern Virginia region. If I had other websites, I could actually just copy those policies here instead of going through everything fresh. But for the sake of this demonstration, we're going to go through each screen. So I'm going to click on Next. Now you'll notice that any time I can actually click Create here at the bottom. We create the bucket, but we're going to go through and set everything up the way we want it from here. I can choose to have versioning. If you check to turn on versioning, that means if I upload a new index page, for instance, but maybe I overwrote something important, I would always have another version of that that I could have access to. So this helps to prevent against accidental deletes. Not a requirement, something you can or cannot choose to turn on. I can also turn on logging for server access logging. If this were going to be my production website, I may want to set the environment with a tag and say environment equals prod. You can add up to 50 different tags. I could also do object level logging and choose encryption. And for the advanced settings, we have something called object lock, and you can choose to do that for auditing purposes or for legal purposes. I'm actually going to leave everything at the default settings. Again, here's our Cloudwatch metrics if we wanted to turn that on. This is important. This is talking about the public access for this bucket. And because this is going to be a website, I'm actually going to uncheck all of these. And I'm also, this is talking about the managing the system permissions. This is talking about allowing S3 log delivery. I'm going to turn that on. It's always a good thing to do logging. I'm going to click Next. And this is basically giving me an overview of my permissions and the different objects, object permissions that I chose. So I'm going to click on Create Bucket. And you can see my bucket here. Otterstein 200 is there. I'm going to click on that. First thing I need to do is go to Properties. Even though I made it open to the public, I want to say that this is going to be a static website because if I do not, no one's going to be able to get to it still. So I'm going to say use this bucket. I have to identify my index document, which I'm going to stick with index.html. I do have an error.html. If I wanted to have redirects, I could do that. And at any time, if I want to take this site offline, I can always disable that website hosting. So I'm going to click Save on that. Go back to Overview, and now we're actually going to upload our website. So I already have a site that I put together. It's on my desktop. I'm going to just grab those files and choose all of these. And I have JavaScript in there, CSS, my HTML, and I'm going to click Next. And this is important because if I do not change the public permissions to give everyone read access, no one's going to be able to see my website. So I said, yes, I want public read access to these objects. I'm going to click Next. This is talking about the different type of storage classes. So standard is where I know that I'm going to have replication happening in the background within my region in Northern Virginia. For a website, you probably want to stick to standard. If this were being used for other types of storage, something like intelligent tiering or standard and frequent access, those are the options you might choose to be more frugal, but for a website, we're going to stay with standard. I click Next and say Upload. And so I can see the progress happening at the bottom. It's going to upload in a few seconds. It's uploading all those individual images and HTML files. And once it's done, I'm going to click on index.html. I'm going to see that URL, and you will see that my website is going to be live. And it is done. So I'm going to go to index.html. I see here is my s3.amazonaws.com with my bucket name Otterstein 200. I'm going to actually do this in a new window. And this is the website that we just created. So we have my three dogs, the three amigos, Geist, Shot, and Echo. And scroll down, of course, I use this to talk about some of the important factors with Amazon S3. It's got some JavaScript things happening here with the menus. I put it, things my dogs would like. So more steak, please, play ball. But this is how easy it is. And because this website is hosted on S3, I don't have to worry about, is it going to be resilient? Because it is resilient because it's a managed service from AWS. It's going to be cost effective, again, because it is a managed service from AWS. And it's secure because it's a managed service from AWS. So this is a great way that I can have a public-facing website and not have to worry about servers in the back end scaling up or down. In the following lab, you're going to have the chance to do this all by yourself.
Hi. As you saw in Bobby's section on S3, setting up a static website is really easy. Well, in this next exercise, you're going to do just that. And the good news is we've prepared a simple website for you already. So all you have to do is upload it to S3 and configure it to act as a static website. And once you do all that correctly, you should be able to interact with the website on the internet because you will have adjusted the bucket policy to allow anyone to view it. Because remember, it's really important, everything is private by default in S3. And you are going in there proactively to make it available for people to look at with that bucket policy. So once you test it online, we're going to have you make a change to one of the files. And don't worry, it's a very minor text change. We're not going to have you write any JavaScript. But once you've made that change, we're going to update S3 and view those changes. That way, you have experience in uploading and modifying a real live website. And this website, of course, is static, meaning it doesn't hit a back-end server or use a database behind the scenes. But again, this is a really great starting point for a serverless application. Later on, of course, we'll link it to the back end. But for now, let's see how you get on with this exercise. And remember, if you hit a brick wall and something's not playing right with Lab, just jump over to the forums and get some guidance. Best of luck. Welcome to week 2. So what did we learn in week 1? Well, you got to meet all the instructors. So you got to hear John talk about the core concepts behind Amazon Lex, where he built a basic chatbot in the console. And if you did the exercise, you did too. Bobby did an intro into S3 and how to host a static website. I trust that helped you when you came to do yours in the exercise, right? So at this point, what have you actually built? Well, you should have a static website in one hand and a simple chatbot engine in the other. 2 standalone serverless services. Pretty cool for your first week, right? Now, as we progress through the coming week, we're going to introduce to you some more Amazon core serverless services, namely Amazon Cloudfront and Amazon API Gateway. We can then, during the next few exercises, start to integrate these services into our website, making it incrementally better and better as we go. I'm not going to talk about Cloudfront and API Gateway. I'm going to let Adam and Wes do that. I'll first hand you over to Adam, where he's going to talk to you about our content delivery network service that we call Amazon Cloudfront.
Hi there. To start this video, I thought we would do a quick history lesson. Content delivery networks, or CDNs, have been around for quite some time now. Since the late 90s, when the first generation CDNs were introduced to help reduce latency associated with media transfer. Traditionally, static material was retrieved directly from origin each time a user requested it. That took way too long. The CDN reduced that round-trip request time by caching frequently used items at an internet exchange location. Now to the current state of CDN. Amazon Cloudfront speeds up content delivery by leveraging its global network of data centers known as edge locations. Cloudfront has edge servers in locations all around the world. Let's take a look. Cloudfront fetches your content from an origin, such as an Amazon S3 bucket, an Amazon EC2 instance, an Amazon Elastic Load Balancer, or your own web server, and stores it in the edge location. Cloudfront can be used to help optimize your application's performance and security while effectively managing costs. We recommend that you also set up Amazon Cloudfront to work with your Amazon S3 bucket to serve and protect the content. By design, delivering data out of Cloudfront can be more cost-effective than delivering it from S3 directly to your users. When a user requests content that you serve with Cloudfront, their request is routed to a nearby edge location. If Cloudfront has a cached copy of the requested file, Cloudfront delivers it to the user, providing a fast, low-latency response. If the file they've requested isn't yet cached, Cloudfront retrieves it from origin, and as an added benefit, data transfer from S3 to Cloudfront is often more cost-effective than serving files directly from S3. So it's a win-win. Cloudfront also leverages AWS Global Private Network, a separate backbone across the internet that helps bypass worldwide networking issues to provide better performance for both static and dynamic content. To help clarify how this works, let's take a look at the scenario shown in this illustration. We've stored our content in an S3 bucket located in a European region, and we have users located around the world who have access to that content. As the arrows show, whenever a user requests content, the request must go over public internet to the source location, in this case, the S3 bucket in Europe. Depending on the user's location, this can take a long time. Now imagine we set up Cloudfront in front of that S3 bucket. Much better. You can see now that there are no longer requests traversing the globe to get our content. Instead, requests are routed to the least latent edge location, that is, the closest in terms of delivery speed. Cloudfront then serves cached content quickly and directly to the user nearby, as shown by the green arrows. If content is not yet cached with an edge server, Cloudfront retrieves it from the S3 bucket origin. And because the content traverses the AWS private network instead of public internet, and Cloudfront optimizes the TCP handshake, the request and content return is still so much faster than crossing the public internet. Let's talk about securing your content. Often companies who distribute content over the internet want to restrict access to documents, business data, media streams, or other content so that only selected users, like paying customers for example, can request that content. By using Cloudfront, we can set up additional access restrictions like geo restrictions, signed URLs, and signed cookies to further constrain access to the content following different criteria. Another security feature of Cloudfront is Origin Access Identity, or OAI. Let's take a look. OAI restricts access to an S3 bucket and its content to only Cloudfront and operations that Cloudfront performs. Cloudfront includes additional protection against malicious exploits. To provide these safeguards, Cloudfront integrates with both AWS WAF, a web application firewall that helps protect web applications from common web exploits, and AWS Shield, a managed DDoS protection service for web applications running on AWS. The goal here is to place layers of protection between your user requests and the data origin, but to do it in such a way that it does not impact performance. AWS WAF lets you control access to your content based on conditions that you specify. For example, IP addresses or the query string on a content request. Cloudfront then responds with either the requested content, if the conditions are met, or with an HTTP 403 forbidden error. All Cloudfront customers benefit from the automatic protection of AWS Shield standard at no additional charge. I hope that now you're as excited about Cloudfront as I am. And as you can see, CDNs are incredibly important to our internet infrastructure and service. In fact, you're probably viewing this course through a CDN distribution now. Now that we've got a good footing on Cloudfront, I'd like to show you how to enable this very powerful service in our next video. See you then. Let's get started with the Cloudfront demo. First step is I'm going to prepare my content. In this step, I'm going to upload my static content to an S3 bucket. In later steps, we will use this bucket as a Cloudfront origin. Amazon S3 is a good choice for Amazon Cloudfront origin. That includes static content such as images, videos, HTML pages, .css files, and .js files. The sample image we will use in this tutorial is an image called jingles.jpg. The AWS Management Console is where we will begin in a new browser window. Type S3 in the search box and double-click to open the dashboard. Now that I am in the S3 dashboard, I'll click Create Bucket button. I'll enter a name for my bucket. It must be unique and all lowercase. I'll have the option to choose a region to minimize latency, minimize costs, or to address regulatory requirements based on my data. I'll select Next. On the Properties panel, there are a number of useful options for my S3 bucket, including versioning, server access logging, tags, object level logging, and default encryption. I won't enable these features in this tutorial, so I'll click Next. On the Set Permissions panel, I can set access control permissions for our bucket, but I won't enable these features for this tutorial, so I'll click Next. On the Review panel, I'll select Create Bucket. I'll double-click on my bucket and select Upload. Then Add Files, and select the picture of my cat Jingles, and click Next. On the Set Permissions tab, I will need to make my image publicly readable. By default, S3 objects are set to private. I'll change my Manage Public Permissions to grant access to this object. Select Next. On the Properties tab, I can set a storage class option. On the Set Properties tab, I can set storage class, encryption, and metadata. I won't enable these features for this tutorial, so I'll click Next. And select Upload. Step 2 will be entering the Cloudfront console. Once my content is uploaded to Amazon S3, I can use Amazon Cloudfront console to deliver that content to end users all around the world. Let's get to it. Go back to the management console, and then I will type in Cloudfront, select, and I'll select Create Distribution. Step 3 is going to be configuring a web distribution. A web distribution specifies configuration settings so that Cloudfront knows which origin to get my content from when a user requests it. I've got a couple options here. I can use an Amazon S3 bucket. I can use HTTP servers, web servers, as an origin as well. I will first choose my delivery option, my delivery method. A web distribution is used for static and dynamic content. Because jingles.jpg is a static image, I'll select Get Started under the web option. I will now configure my settings. In origin domain name, I'll select the name of the S3 bucket I stored jingles.jpg in. I can leave the rest of the configuration settings with the default values for this tutorial. You can learn more about each configuration setting by clicking and hovering over the eye next to each field, just as I've done here. Step 4 will be creating a distribution. Once I've configured my distribution, Cloudfront will now create the distribution and propagate it throughout the Cloudfront network for me. I'm going to scroll down and select Create Distribution. After this process is complete, the status column will change from In Progress to Deployed. By the way, if you do this at home, it might be a good idea to go ahead and grab a cup of coffee. Luckily, I have my friends in the studio who are quite adept at time travel. So on this video, step 4 goes very quickly for me, but for you, it can take up to 15 minutes. The domain name that Cloudfront assigns to my distribution appears in my lists of distribution. I will need to make note of this for the next step. Clicking on the Distribution ID field takes me to a page where I can see the full Cloudfront domain under domain name. The next step is to test my link. After I create my web distribution, I can test it out by confirming that Cloudfront gets my object from origin and returns it into my web browser. For this test, I will need the Cloudfront domain name from step 4 and the image name I uploaded to the S3 bucket previously in step 1. I'll open a text editor on my computer, copy and paste the following HTML code. I'll replace the domain name with the domain name that Cloudfront assigned my distribution. I'll replace object name with the name of my image file in the Amazon S3 bucket. In my case, it's jingles.jpg. I'll save the text file as mycloudfronttest.html. I'll open my web page in a browser to ensure that we can see my content. And there you have it, a cute cat. Step 6 is to disable my distribution. I can easily disable the distribution from the Cloudfront console. In fact, it's a best practice to disable distributions that you are no longer using, so you don't keep getting charged for them. However, note that when a distribution is disabled, any website supported by that distribution will be down and the content will no longer be accessible to the end users. I'll select the checkbox next to the distribution I created and click Disable. I'll be asked to confirm and then I'll click Yes, Disable. That's it. How easy was that? Now you can go and create your own low latency static site to serve up as many cute cat pictures as you can possibly handle. That's all for now. I'll see you in other topics.
Hiya. You heard Adam's explanation of our content delivery network, Amazon Cloudfront. Well, he touched on the idea that in order to provide low latency for people viewing your website, we need to bring the content closer to your users and alleviate that direct load on those origin servers. Well, we want to take advantage of this cool concept with our website. Now, in our case, we're using S3 to host our website, right? Well, we don't want to have some users visit our website directly at S3 and other users visit it indirectly via a Cloudfront distribution, because that's going to get really messy and your server logs, well, they'll just be confusing. So we're going to use a Cloudfront distribution in front of our website. What are the steps? Well, step 1, we're going to make your S3 website private again. Yes, that's right, all that bucket policy stuff you did to make it available to everyone, that's going away. We're going to replace it with something that's much better. We're going to adjust that bucket policy so that our website is basically saying, I'm only going to be communicated with by a very specific Cloudfront distribution. In this case, the one we're going to have you create. That way, what we're doing is we're forcing all the traffic to be served through Cloudfront, and that's exactly what we want. You know, I think you'll be pleasantly surprised with how easy all this is to set up. Cloudfront is a very powerful service, and we have customers using it to serve millions of requests. And as Adam alluded to earlier, there are tons and tons of advanced features available for you to use. And the good news is, you're only going to have to set up a very, very basic distribution for this exercise. It's all we need. Okay, off you go. Set up your global website. Good luck.
Welcome back. I'm Wes, and in this section we will introduce Amazon API Gateway. We're going to do a quick overview of what the service is all about. We'll talk about why you would want to use it, and then we'll run through a quick demo to show you how to create and configure your very own API Gateway in the AWS console. Let's get started. So API Gateway is a fully managed service that's designed to make it easy for developers to create, publish, maintain, and monitor secure application programming interfaces, or APIs, at any scale. With a few clicks in the AWS Management Console, you can create REST and WebSocket APIs that act as a front door for your applications to access data, business logic, or other functionality from your backend services, like workloads running on EC2 and web applications. API Gateway also provides an easy interface for code running on AWS LAMBDA and other AWS services, which we'll discuss in detail later in this course. First off, why would you want to use API Gateway? Well, it turns out that software development organizations are moving more towards microservice architectures. Microservices are an approach to software development where software is composed of small, independent services that communicate over well-defined APIs. These services are in turn owned by small, self-contained teams. Microservices architectures make applications easier to scale and faster to develop. And that really enables innovation and accelerates the time to market for new features. API Gateway fits right into this scheme, so why would you want to use it? Well, developers can add headers, map input variables from post events to something your target application needs. You're going to see this in the demo in a minute, as well as later in this course. Here are several more reasons you might want to use API Gateway. Efficient API development. You can run multiple versions of the same API simultaneously with API Gateway. This allows you to quickly iterate, test, and release new versions. We're talking about the difference between days and weeks. Easy monitoring. You can monitor performance of metrics and information on API calls, data latency, error rates from the API Gateway dashboard, which allows you to see millions of requests in a single pane of glass. Performance. You can provide end users with the lowest possible latency for API requests and responses by taking advantage of our global network of edge locations using Amazon Cloudfront. You can also throttle traffic and cache the output of API calls to ensure that the backend operations withstand traffic spikes and backend systems are not unnecessarily called. Cost savings. API Gateway provides a tiered pricing model for API requests. You can decrease your costs based on the number of API requests you make per region across your AWS accounts. Flexible security controls. You can authorize access to your APIs with the AWS Identity and Access Management, or IAM, as well as Amazon Cognito. If you use OAuth tokens or other authorization mechanisms, API Gateway can help you verify incoming requests as well. By providing an extra layer in front of your backend service, you can add extra layers of protections and security as well. So enough marketing speak. Let's crack open the AWS console and show you how this thing works. So in this demo, we're going to log into the AWS console, go to API Gateway Service and get started. There's a little note there about an example API that's already set up for you. However, we're going to create a new API by selecting New API. We're going to get it a name. In this case, we're just going to use Demo. The description itself is optional. And we hit the Create API button. In our actions, we're going to create first a new method. And for this particular demo, we're going to make it real simple, and we're just going to use a GET request. As part of this GET request, since this is just a demo, we're not actually going to do anything. We're going to use, for the integration method, we're going to use mocking. And what mocking really is, it's just a fake way to send some information and bounce it back without actually making anything happen. So we haven't written any code, we don't really have a service, but we want to test that the API Gateway works. So in this particular case, we have created our method request. We've decided that our integration request type is going to be mock, and again, that's just for fake. So the next thing we have to do is the integration response. And the way we do that is selecting integration response. We're going to scroll down and expand this, and we're going to simply use a mapping template that's already been created for us. It's application JSON, and the little drop down here, we've got our method pass-through. This code's not super important, but all it really does is bounces back any request that's sent to it with all the information that's coming through in the header within the request. Check it out. We save our particular request, and now we are going to deploy it. Go back to Actions and hit Deploy API. We're going to give the stage a name. In this case, we're just going to call it Test. Call it a new stage, we're going to call it Test. And we don't have to give it a description. As you'll see, since I've created this, we now have a URL. I can click on this URL to test my API. All we've done is gone out, we've taken all the information that came from that particular request, the header itself, and you can see all kinds of information in the query string that was returned, all the variables, my IP address, and all the browser information that was returned. It's really just that simple.
Hi. So Wes has talked to you about API Gateway, and specifically how to set up a mock API. Want to guess what you're going to do in this lab? That's right. You're going to mock an endpoint using, surprise, surprise, API Gateway. This concept is often used by developers as they are building out their web apps, because they might have to develop on the front end first, but might not be ready to wire up, say, a database at the back end. A mock is great for this kind of thing, as we can wire up all the plumbing for the website to communicate to a real back end, but actually just receive dummy data back. Once your mock's in place, you can have a working front end and kick that back end intelligence down the line, worry about that later on. So are you ready to mock out an API? Well, thanks to Wes and his demo, this exercise should be a breeze for you, because you're following exactly the same steps. You'll log into the API console, so at this time you'll create a post method, as our front end will send a payload of city, and hardcode the mock to send a fixed temperature back, rather than echo the whole request back, like you saw in Wes's example. That's it. We can worry about replacing the mock with real functionality a little bit later on. There's one other thing. Cross-origin resource sharing, aka CORS. This one's a pain. You see, when a website makes a request via JavaScript to a back-end API, such as the one we're having you create, the browser will complain and not allow the data back into the browser if it thinks it's not coming from your server, i.e. cross-domain. But why would it think it's cross-domain? Well, it turns out that because your website is hosted, or at least served from, Cloudfront, and thus using a Cloudfront domain name, the browser thinks, we're at one domain for this site, yet JavaScript from this site is trying to call a different API gateway domain name. That doesn't smell right. You know what? Let's just block it and play it safe. Ta-da, broken website. So how do you get around this? How can we inform the browser that we actually manage that API endpoint as well? In other words, we need to say to the browser, it's still ours, please let this request through. Luckily, there's an easy fix. We leverage a feature of API Gateway Console that hides the complexity of manually setting up and configuring CORS. It's literally a button that says Enable CORS. Just press it. Let API Gateway add all the technical stuff behind the scenes in your API, and that way, from your perspective, it just works. Problem solved. So, in this exercise, you're going to do two things. One, you're going to create an API gateway using POST with hard-coded mock data. And two, you're going to press that Enable CORS button. You'll know when you've got CORS enabled correctly because your website will work. Remember, forums are your friend. Go there if you get stuck. Welcome to week 3. So what did we learn last week? Adam talked about our content delivery network, Amazon Cloudfront. And the first exercise of last week was to put one of those Cloudfront distributions in front of our S3 website, so that we have a website that is globally available with low latency for our users. Awesome. What did you do then? Well, thanks to Wes explaining API Gateway mocks, you should have been able to mock out a backend for the website and test it, right? So all in all, what do we have so far? We have a low latency website that actually hits our own backend, albeit a mock, and returns a temperature. Pretty good progress, especially as we're only in week 2 and we're already implementing multiple serverless services. So what's next? What does evil Ricky have in store for you this week? Lots. Amazon Dynamodb, our serverless NoSQL database. Amazon IAM, Identity and Access Management, the overarching system that determines who can do what when. And most people's favorite service, AWS LAMBDA, serverless functions in the cloud. Now that's a lot of stuff to cover in 1 week. Please don't worry, you're in great hands. Bobby's going to discuss IAM, Adam will talk about Dynamo, and I'm afraid, sadly, you're stuck with John for the LAMBDA sections. Just kidding, we all love John, he's great. But as far as this week's exercises go, I want us to swap out our API Gateway mock for a function mock, so you get some hands-on experience actually using LAMBDA. In fact, we're going to use LAMBDA a lot throughout the rest of this course. So I think I'm going to have John and Adam start off this week discussing the pros and cons of LAMBDA and serverless in general. And I'll see you again just before the first lab.
Hi again. I want to talk to you now about Identity and Access Management, or IAM. Later this week, you will see how roles are used to allow services like LAMBDA to work. So let's talk about roles. In AWS best practices, roles are generally the right solution. They allow us to give access to third parties without creating a new IAM user. This is great for service accounts or application IDs. Let me give you an example. In the Unix world, if someone told me their user ID didn't have permissions to perform a specific task, I would use the su command or switch user to log in from my root account to their user ID to see if their user really didn't have access to perform a command, or perhaps it was just a syntax error on their part. Although I had root or super admin rights on a system, when I use the su or switch user function, I assume the privileges of that ID. Let me give you another example. When I assume my role as a fireman and I have on my turnout gear in the fire truck speeding to a house fire and pass a police officer, he isn't going to stop me and give me a ticket. In my role as a fireman, I'm allowed to speed to the house fire. However, when I get back to the station, off duty, take off my turnout gear, and get into my personal car, if I speed past that same police officer, he's going to give me a ticket. In my role as Bobby, private citizen, I'm not allowed to speed. I'm the same person with or without my turnout gear, but in my role as a fireman, I'm allowed privileges that I'm not afforded as a private citizen. An IAM role is an IAM entity that defines a set of permissions for making AWS service requests. IAM roles are not associated with a specific user or group. Instead, trusted entities assume roles, such as an IAM user, an application, or an AWS service like EC2. IAM roles allow you to delegate access with defined permissions to trusted entities without having to share long-term access keys. You can use an IAM role to delegate access to IAM users managed within your account, to IAM users under a different AWS account, or to an AWS service like EC2. To get started with any IAM role, you just need to create the role similarly to the way that you create a user. Name the role and attach a policy or permissions to it. You assume an IAM role by calling the AWS Security Token Service, or STS. You can also use the Assume Role APIs, Assume Role with Web Identity, or Assume Role with SAML. These APIs return a set of temporary security credentials that applications can then use to sign in requests for different AWS services or APIs. There is no limit to the number of IAM roles you can assume, but you can only act as one IAM role at a time. When should I use a user versus group or role? An IAM user has permanent long-term credentials and is used to directly interact with AWS services. A group is primarily a management convenience to manage the same set of permissions for a set of IAM users. So for instance, I would want all of my DBAs or database administrators in the same DBA group, so that if I have a new DBA come on board, I can simply add him or her to that group and know that they have all the privileges they need to perform their job as a DBA. An IAM role is an entity with permissions to make AWS service requests. IAM roles cannot make direct requests to AWS services. They're meant to be assumed by authorized entities such as an IAM user, an application, or AWS services like EC2. Using IAM roles to delegate access within or between AWS accounts. There's a soft limit of 1,000 roles per account, but because this is a soft limit, you can request an increase in the number of roles for your account. For troubleshooting purposes, keep in mind that there is an implicit denial for all actions. IAM policies are evaluated along with the service's resource-based policies. When a policy of any type grants access without explicitly denying it, the action is allowed. Meaning, if I have anywhere in the policy an explicit deny statement, that will override any allow statement. For more information on IAM, go to the documentation located at www.aws.amazon.com/IAM.
John and I have this awesome web application we're looking forward to deploying soon. But we've been debating back and forth about which deployment approach is best because we're not really sure if it's going to go viral or not. But we'd like to be prepared for it.
You may have heard about the Hello World application. In fact, mostly everyone in IT has heard about it. The issue with that application is that it's boring and it's static. Instead, we want to create the Hello World version 2 application. This application shall take a name as an input, John, and then she'll reply back with hello, whatever that name was, in this case, hello, John. Since everyone in IT knows about Hello World, I'm pretty sure it's going to go viral.
Let's certainly hope so. Okay. I think the traditional deployment method is probably our best bet. 1, I know it. 2, it's tried and true. 3, I could show it to you in just a few minutes.
Well, I'm pretty sure serverless is the right approach, but if you want to show me architecture, go for it.
Okay, well, let's get to work. Okay, John, let's check out my architecture. All right, so I've got a VPC, and that provides me logical isolation at the network level. I have an internet gateway, which allows inbound and outbound traffic. I have an ELB, which distributes the traffic across 2 availability zones. I've chosen 2 for high availability and fault tolerance. And then I have 2 EC2 instances. The ELB will distribute the load to those, and I'll show you the flow of traffic now. So traffic comes inbound through the internet gateway to the ELB. And then is distributed to the EC2 instances. So what do you think?
Wow, that was a lot for a simple Hello World application. Let me show you a different way of doing this that is a bit simpler. API gateway is going to receive traffic from the user. It will send that traffic into LAMBDA, and LAMBDA will be replying back with that traffic all the way down to the user. And that's it. Wasn't that much simpler? Adam? Adam, you there? Clearly, Adam is in agreement that this is the way to go. So let me discuss LAMBDA since you already know API gateway. At this point, you have learned about different serverless services. However, the category of serverless I want to discuss with you today is compute. AWS LAMBDA is a serverless compute service. It lets you run your code without provisioning or managing servers. You pay only for the compute time you consume. That means no charge when your code is not running. In our example here, if there are no users that sends requests, there are no charge for LAMBDA, and there's no charge for API gateway either. It also means that you don't need to wake up in the middle of the night to respond to a server that crashed or do patching outside of business hours. With LAMBDA, you can run code for virtually any type of application or backend service, all with zero administration. Just upload your code and LAMBDA takes care of everything required to run and scale your code with high availability. With AWS LAMBDA, you pay only for the requests served and the compute time required to run your code for each of those requests. Billing is metered in increments of 100 milliseconds, making it cost-effective and easy to scale automatically from a few requests to thousands per second. Building serverless applications using LAMBDA means that developers can focus on their core products instead of worrying about managing and operating servers or runtime. This reduced overhead lets developers reclaim time and energy and can be spent on developing great products. Customers do care about the availability of an application, but what they really want to see are new features. So with LAMBDA, you can focus on those new features. In the next lecture, I'll go in more details about how LAMBDA works. Thank you for watching. In the previous lecture, you learned about the benefits of LAMBDA. Let's dive into the details. Before you can start creating the code of your LAMBDA function, you will need to pick a programming language. As of today, LAMBDA natively supports 6 programming languages: Node.js, Python, Java, C#, Ruby, and Go. Sometimes those native runtimes aren't enough because you may have a tool that you don't want to rewrite that's in C++, or maybe because your expertise is in PHP. That's why it's possible to use your own runtime, but you will need to develop that piece as well. Now that we figured out the runtime, the next step required to create a LAMBDA function is to upload our code. That can be done in 3 different ways. You can use the inline code editor, upload your own zip file containing your code, or decide to store that zip file in S3 and point LAMBDA to that file. Depending on what your code does, you may require LAMBDA to access other AWS services. For that, you will need to specify an identity and access management role that Bobby will explain to you in the next lecture. That role is required to do logging, as an example. That's right, you aren't getting away with no logging here, as you may need to troubleshoot the execution of your LAMBDA function. To do so, you can just output to the console in Node.js and Python. Anything that is sent there will automatically be sent to the Cloudwatch log service, which is just a service to collect logs. That's why the permission of your LAMBDA function are so important. At that point, the LAMBDA function will be created. However, a LAMBDA function on its own doesn't do much. It needs to be executed. We call that triggers. There are many AWS services that can trigger a LAMBDA function. Some that we have already seen this week that can trigger a LAMBDA function, like Simple Storage Service, Cloudfront, API Gateway, but there are many more. For example, a LAMBDA function can be triggered by S3 when a new object gets uploaded. So if you wanted to transform a picture that is uploaded to an S3 bucket, and flip it upside down towards another S3 bucket. Let's take this example on a diagram. On the left side of this diagram, you can see an S3 input bucket with a triangle. And then on the right-hand side, I have my S3 output bucket with that same triangle flipped. In the server world, you will have to pull the S3 bucket to know if a new image has been uploaded every once in a while. So adding my server here, I'll need to pull that S3 bucket constantly until that image is there. And then once I'm ready, I can then send that towards the other S3 bucket. While with LAMBDA, you can configure S3 to trigger the LAMBDA function as soon as that image is uploaded. S3 needs to be allowed to trigger your LAMBDA function, as by default, nothing can trigger it. To do so, you use a function policy referencing the S3 bucket, in this case, our input bucket. Luckily for us, if we use the AWS Management Console, that policy can be automatically created, as you will see in the next demonstration. When your LAMBDA function gets executed, LAMBDA, the service, needs to know what piece of your code it needs to execute. That is the entry point for your code. In the LAMBDA world, that's called a handler. This tells LAMBDA in which file or class the function to execute is, as well as its name. LAMBDA will use that handler to execute your LAMBDA from the trigger it received. But your code probably needs to receive some more information about what just triggered it. That information is passed to the handler via what we call an event payload. If we go back to our example of a picture uploaded to S3 to be transformed, that event payload will contain the bucket name and the object key of the blue triangle, which LAMBDA can now use to know which one of the objects from that input S3 bucket to transform. When a service like S3 invokes the LAMBDA function, there is no need for S3 to get return data from the function. It really doesn't care about what LAMBDA does. That is what we call an asynchronous invocation. If we take another example where we will have API gateway that sends a request to LAMBDA for a REST API call. API gateway is really interested in the response from LAMBDA to be able to send it back towards the user. That is what we call a synchronous invocation. Those are the two types of invocation of LAMBDA. While the function is running and transforming that image from S3, RAM and CPU are used. How are those allocated in LAMBDA? Well, you don't allocate CPU power, you only allocate RAM. However, the more RAM you provide, the more CPU power your LAMBDA function will also have. As of today, that RAM allocation can go from 128 megs to 3 gigabytes. Why will you not always allocate the highest amount of RAM? Well, the reason is that you pay more money per 100 milliseconds when you allocate more RAM. So that's obviously more expensive. Let's not do that. But wait. If the LAMBDA function finishes in less time because it has more RAM and CPU power, then it means that it uses less 100 milliseconds, thus reducing the price of the length of our LAMBDA function. Let's take a look at a graphic here. What you can see here is LAMBDA compute cost by function execution time for 100,000 invocations. On the y-axis, you can see the cost of compute from $0 to $12 USD. That is not that expensive, but yeah, this is LAMBDA. On the x-axis, I can see the function execution time in milliseconds. So in orange, for example, at the 3-second mark, what I can see is that for a function that will have 2 gigs of RAM, it will cost close to $10 for running that for 3 seconds for 100,000 invocations. For a 512 megs of RAM, it will cost a lot less, so about $2.50 or $3 here. Well, then you will always be using the lower amount of RAM. No, but let's think about this for a second. if it takes 3 seconds to execute our Lambda function with 512 megs of RAM, how much time will it take to execute that with way more horsepower here? Well, I don't know. It's not always a function of this. It's not division in here. So maybe it will arrive towards 400 milliseconds. So if you look at the price difference, now we're at about, I don't know, about $1 here versus executing that at the $2 to $3 mark that is here. So since this all depends on the complexity of your Lambda function code, you will need to execute some tests to figure out which amount of RAM is better here, which is the lower cost. Now, a limitation of Lambda is that a single execution can only run for a maximum of 15 minutes. After 15 minutes, we will yank the carpet under your code and it will now have no choice but to stop abruptly. If you do need to run for more than that, you are probably looking for another type of compute. Staying in the serverless world, you could take a look at AWS Fargate, or you could go to an architecture like the one Adam talked about with those servers. Since you pay per 100 milliseconds of your code running and Lambda has a maximum timeout of 15 minutes, what happens if your code was to go in an infinite loop? Will you be charged for all the way to those 15 minutes? The answer here is yes, you will. However, there is a timeout that is configurable for your Lambda function to prevent this kind of behavior. In the next lecture, I will do a demonstration of all of the topics we just covered using the Hello Name application we discussed with Adam earlier. Thanks for watching. So now that you have learned a lot about Lambda, but all in theory, let's put it to practice. In an earlier lecture, I told you about that brilliant application of Hello Name. So I want to use this time and do a demonstration about that Hello Name application. If you don't remember it, don't worry. Let me re-explain it to you. The idea from it is I want to go to www.example.com/?name equal John. And then that is supposed to reply with hello John. So the architecture that you've seen from our previous lecture was that API gateway was the endpoint of this www.example.com, sending that into Lambda, and then Lambda, when it needed to, was sending its logs into Cloudwatch logs. That was the whole architecture. So for this to work right now, the first piece that we need to do is to create an identity and access management role. Why do we need that? Well, this role is going to be applied to our Lambda function because Lambda needs to be able to send its logs into Cloudwatch logs. So that's the first step that I need to go and do. So join me into the console. First, I am into the Identity and Access Management console under the roles, and I'm going to create a brand new role. This role is going to be for Lambda, and then the permissions that I need, I'm going to use an already built policy that comes with your account that is called the AWS Lambda Basic Execution Role, which gives us write access into Cloudwatch logs. Don't forget to click that little check mark button that is right there. And I'll click Next on tags, which are optional, so I'm not going to go through them. And then in the review, I need to specify a name. We're going to call that the Lambda Basic Execution Role and create this role. Now that my role is created, I can go and create my Lambda function. So let's go into the Lambda console, click the Create a Function button. I'll author it from scratch. I won't be using any blueprints or serverless application repository here. So I will give it a name called the Hello Name Lambda function. And then now I need to select a runtime, the language I will want to use. Obviously, I will be using Node.js because that's my favorite language. And then I need to specify a certain role. Well, the Lambda Basic Execution role that we have just created into the IAM console a few seconds ago. I'll hit Create this function. Let me explain to you this console that is right here. First part is the designer that you see at the very top. This designer makes everything work inside of the Lambda console. if I click on different buttons that is inside of this designer, the bottom of the page changes as we move along. So if I click on this view permission, at the bottom of the page, I now see the function policy and in my execution role that I have just created. If I go back and I click on this hello name piece that is there, which is my Lambda function, now I can see my code of my Lambda function. Yes, this is how the designer is actually working. On the left-hand side, I can define triggers for my Lambda function, what will call the Lambda function itself. And then from the Lambda function, what it has access to are what you see on the right-hand side. Cloudwatch logs is the only thing that my Lambda function has access to right now. Now, let me scroll down into that function code. I have the code entry, 3 methods, upload a zip file via S3, or edit the code in line. Today I'm going to use the edit the code in line. Then my runtime, Node.js, and then I have a handler. This handler is what tells Lambda, the service, what to call inside of your code. It says call the index file, index.js file. So if I look on the lower left, I have the index.js file, and then call the handler function. I have an export of a handler function. That's how Lambda will call my Lambda function. Now, inside of this code, I have a status code of 200, which means an OK status, that everything has worked. And I have the body, which says hello from Lambda, and that response is being returned by this handler. So that's what we return back, depending on the event data is being sent into my Lambda function. So what I really want here is to change this hello to be a hello John. That's what I want to send. So I'll save this function and I'll test it. When I click the test button, I need to configure an event data that will be sent into Lambda. So I'll give it a certain name, hello name test. I'll pass in a certain parameter, name, and then the value is going to be Jonathan. And I'll create this test. Then execute it. Now, my execution, if I scroll back to the top of the page, I can see the execution succeeded. It's in green. If it was in red, then I will have had a problem with my test itself. Let's take a look at the details. It says status code 200, and the body says hello, John. Isn't that supposed to say Jonathan? Let's go and take a look at the code. Oh yeah, I've hard-coded the value of the name inside of my code. I'm not supposed to have done that. I need to take the data coming from the event payload. So let me remove that piece in there, and I'll add event.name. From the event variable, I am going to have a name parameter sent into it. I'll save it and test it again. And this time, I can see hello, Jonathan. Other P's that I can see from within this console is I can see the duration of this Lambda function. It only took 28 milliseconds for it to execute. And I got billed 100 milliseconds. I used 71 megs of memory out of 128 megs of memory that has been assigned to this Lambda function. Scrolling down in the page, in the basic settings, I can see that this is where I can specify my amount of memory for this specific Lambda function, which also controls the CPU, the amount of CPU power that I get, and as well as the timeout, the maximum amount of time that I want my Lambda function to run. So the next step into here that I wanted to show you is logs, right? So Lambda is supposed to be able to execute and call and output logs. So let's go in our code and add certain logs into here. I'll go into this and remove that to implement, and I'll output a certain log statement. One of the good things to output in your logs is the event payload, to be able to troubleshoot that a little bit later. So I'll pass in event, and then I'll use the JSON.stringify function to take the event payload that is passed as a JSON input and then stringify it. Right? I create a string from it. And then that will be what will be logged in there. I'll hit save on this and test it one more time. Now, I want to go and look at those logs. Let's go and take a look. I have the configuration tab right here. This is what we've been playing with all along. But if I go into the monitoring tab, there's a whole new dashboard that gets executed here. In here, you're going to find that I have invocation count, how many times I've invoked this. You'll find the duration of my Lambda function, and you also find the errors. It seems like there is 0 errors for this Lambda function that I have executed. So my Lambda function is working. At the top, I also find the View Logs in Cloudwatch button. So if I click that, the Cloudwatch Logs console opens. I can see now that I have a certain log stream that got created for me. So there are 3 log streams. Why is that? Well, every time that I change my Lambda function, a brand new container gets deployed, brand new Lambda function gets invoked in there, which means there will be a brand new log stream that gets created. I changed my code 3 times, hence why I see 3 log stream in there. The last log stream is the 1030 log stream right here. So if I click on it, what I am going to find in there is the start of my Lambda function, and then I have the event, my payload. So the name, Jonathan, that was sent as part of my test. So this is how you can do troubleshooting with Lambda. Lambda is using console.log or any print output in Python, for example, will be sent into Cloudwatch logs, and you can go and review them inside of Cloudwatch logs. Let's go back into our diagram. So at this point, we've created everything on the right-hand side, from Lambda to Cloudwatch logs. In the next video, I'm going to integrate API Gateway into this architecture where this www.example.com/name=John is going to be sent into. If you have the time, you can follow me over there. In our previous lecture, I've introduced to you Lambda, or the demonstration with you of Lambda with Cloudwatch logs of this example.com application. The next piece that we need to integrate in here is API Gateway. So API Gateway is going to receive a request. This request is going to be on the /resource, and it will be a GET request with a query string parameter of name being passed in. So let's go into console and go and take a look. In the API Gateway, I will click the Get Started button, which will say, hey, do you want to create an example API? Not really. I want to create a brand new API. I'll give it a name called the Hello Name API of type endpoint regional. I'll create that API. Now, in my resources, on the /, I'll create a new method that will be of type get. And I want this get request to send the data into a Lambda function that is called the Hello Name Lambda function. I am also going to make use of the Lambda proxy integration. The Lambda proxy integration automatically takes the input request, packages that into a JSON payload, and send that into Lambda. We may have to do a few tweaks into a Lambda function to adapt for this type of payload being sent in there. But first, let me save this setup right here. When I hit the save button, it says add permission to Lambda function. Yes, API Gateway needs to have access to call that Lambda function, but only your API Gateway needs to have access to it. So before I click the OK button, I want to go back into my Lambda console and then show you the current permission of this Lambda function. So I'll click on that View Permission button right here, and then I can see under the function policy that this Lambda functions policy is empty, which means no one is allowed to invoke this Lambda function unless they have IAM permissions. Well, let me go back into the API Gateway console and click the OK button. I'll go back again into the Lambda console, hit the refresh button, click on that View Permissions, and I can now see that API Gateway has access to call my Lambda function, my resource is right here on the right, hello name, if the source ARN is QAE, ends with QAE, and GET request. Let's go in API Gateway. I can see QAE and then the GET request. So only my API gateway that I have just created is allowed to invoke this Lambda function. That's why this ARN is very important to have inside of your function policy. So you can always let API gateway do that for you automatically, or you can do that manually yourself. So the next step here is the method request. The method request, I need to specify that there is a name parameter being inputted. So in the URL query string parameter, I'm going to add a query string called name, and I'll say this one is required. Now, I am ready to test this API gateway. However, I don't know if you remember what I said about that Lambda proxy integration, but because API gateway sends its data into Lambda via automatically packaging everything up into a JSON payload, the name parameter may not be passed the same way as how I've done my tests in the first place. In fact, we're going to need to go and modify our code. We shall create a brand new test for this though. It needs to be sent from API gateway. So I'll configure a brand new test event here, and I am going to create this new test event and use an event template of API gateway AWS proxy. I will need to specify a name here, hello name API test. And you can see that the data there's a lot more data that is being passed. One of the important pieces here is the query string parameters. The query string parameter is an element, right, that API gateway is creating for us, and this is where it will add the name query string parameter that gets added with the value that I want it to have. So in our code, we cannot just say event.name anymore. I'm going to need to say event.query string parameters .name, because this is where now that query string is located. So I'll save this test or create this test, and I'll go into my Lambda function, hello name, go into my Lambda function, and I'll modify it with my event.queryStringParameters.name. I'll save it and hit the test button. Go back to the top, and it now says, hello, John. So we're good. It should work with API Gateway. We've created our test. Well, the best way to know that is to go test it from the API Gateway console. Let's go there. In API Gateway, there is a test button right here. I'll use and input my name parameter, name equal Jonathan. I'll click the test button at the bottom of the page. I get the data back. Latency was 21 milliseconds. And in the response body says, hello, Jonathan. So API Gateway is able to invoke Lambda, and Lambda was able to get the data, the query string parameter name, from the event payload. The last step here is to deploy this API Gateway, because I'm not going to give access to the console for my users and them coming into here and doing this test themselves. I want them to be able to use a URL in there. So I'll click Action, deploy the API. I need to create a new deployment stage. You've learned these with Wes in our previous lecture. So today, I feel a little bit cowboy, so we're going to deploy right away in prod. Don't do that at home though. And hit the deploy button. I now have my invoke URL that I can copy and input my name parameter with hope this works. And what I get back is, hello, hope this works. So API Gateway I was able to deploy my API Gateway in prod. And then now any users that has this URL that want to pass this query string can now use my brilliant hello name application that will now be used from the entire world. No need to scale Lambda, no need to worry about API Gateway scaling. All of that is managed for me. That's the beauty of serverless here. So in our next lecture, Rick is going to introduce you to the exercise, which will take a lot of everything that you have learned in the last few modules and integrate them and do an exercise around Lambda.
Thanks to John, you should now understand the value proposition of Lambda and the idea of running functions in response to events. LAMBDA is pretty awesome, and we're going to use it in multiple ways throughout the rest of these exercises. As usual, we'll start simple and enhance our LAMBDA function as we progress through the exercises. Whenever you use LAMBDA, you always need to think about what it's going to do and what it's going to interact with. In this one, we're going to replace API Gateway, you know, the mock you built earlier, with a function that returns a temperature. Now, this doesn't make any real difference to our website, but what it will do is create a base from which we can add advanced functionality a bit later on. Once we have this mock LAMBDA in place, swapping out the code for more elaborate functionality, it's easy. We know we want to return a temperature, but what about the other thing we need to consider? What will LAMBDA interact with? Well, often when you write code, you might need to debug and push information to a logging system. As John talked about, we have Cloudwatch for this. So naturally, that is one service that our LAMBDA function is going to need to interact with. We call that an execution permission. But there's even something else that we have to consider. API Gateway needs to wake up LAMBDA, but LAMBDA is not executing API Gateway, right? So we need something ever so slightly different here to wire this up correctly. We need an invocation permission on LAMBDA to say that it can be triggered by API Gateway. Now, of course, we could put the permissions on the API Gateway end and say that it is allowed to wake up LAMBDA, but for this lab, we're just going to create an invocation permission on the LAMBDA function because it's super easy to do in the console. So, once you have your LAMBDA function that returns a temperature, regardless of city, mimicking what you had with the API Gateway, and it has permissions to write logs and be awoken by API Gateway, we can test it in our front-end website. I hope you're starting to see the big picture here, piecing together serverless components on top of each other to create an end-to-end solution. Naturally, we need to make this work with real data instead of dummy data, but all in good time. Let's get this LAMBDA thing working first. Good luck with this, lab. You know, I think you'll like LAMBDA. It's really cool once you start working with it.
Hi, welcome back. In this portion of the class, we're discussing the serverless NoSQL solution on AWS called Amazon Dynamodb. Together we will discover how Dynamodb service stores data, sorts, and completes scans and queries. Amazon Dynamodb makes your life easier by offering a simple and cost-effective way to store and retrieve any amount of data and serve any level of request to traffic. Listen, we are talking about millions and millions of requests here. It's important to understand the foundational concepts of Dynamodb, such as partition keys and sort keys, as well as local and global secondary indexes. That was a mouthful. Okay, let's start with the basic concept of a table. Remember, we're not building a database here in the traditional sense. Instead, in Dynamodb, we call that set of information tables. A table is a collection of items, and each item is a collection of attributes. I'll tell you what, let's draw this out so that it's easier to understand as I explain the remaining things that make up a table. First is the partition key, which is a simple primary key composed of one attribute. In the case of our table, we are storing music data. Our primary key should be artist. You see that next to the partition key is a sort key. That should be a song title. When a partition and a sort key exist in a table, it is referred to as a composite primary key and is composed of two attributes. The first attribute, again, is artist. The next attribute is song title. Okay, so while this table isn't super useful yet, it will become useful when we add attributes. Let's think of some attributes to add that are music related. Well, chart number, let's see, that's pretty important. Genre, year, beats per minute. For creating playlists to match your speed, that's kind of important too. So all this data seems like it would be very helpful to know. So now let's add those attributes to the table that we've drawn previously. Wow, this table is actually starting to become useful. But now we need to figure out how this data will be queried to derive meaningful insights. Let's talk indexes. A secondary index is a data structure that contains a subset of attributes from a table. along with an alternate key to support query operations. A table can have multiple secondary indexes, which give your application access to many different query patterns. First up is a local secondary index. That's an index that has the same partition key as the base table, but a different sort key. So an example of a query that we could use on a local secondary index would be to say, let's find all of the songs, the #1 songs from a particular artist, one artist. A local secondary index is an index that has the same partition key as the base table, but a different sort key. A good example of a local secondary index query would be all the songs from a particular decade per artist. So if I have a favorite artist, all the songs from the 80s, all the songs from the 90s. That would be an example of a query for a local secondary index. A global secondary index is an index that has a partition key and a sort key that can be different from those based on the base table. So an example of a global secondary index query could be all the #1 songs from a particular artist, or all of the songs of a particular genre. Doesn't matter what artist produced them. I want you to pause and consider for a moment how you will use DynamoDB. The secret to a successful deployment is to develop your application first and determine what your queries will look like. Then design your tables to best serve that data. Next, let's review a bit about performance. Provision throughput is represented in units of read and write capacity. There are several options to manage this. First is the ability for you to provision throughput, again based on read and write capacity units. There are a number of ways for you to configure this setting. Be sure to use our good friend Amazon Cloudwatch to help guide you with your decision to increase or decrease. Next, you can use the on-demand mode for DynamoDB. This will help you get up and running quickly without much concern to performance configurations. And then auto-scaling. Auto-scaling is a way for you to run a more forgiving type of DynamoDB environment. Auto-scaling allows DynamoDB to scale based on demand, much like you could with EC2 for compute. As far as performance goes, these tools are largely automated since it's a managed service, which is really nice for you. In our next video, I will show you how to create a DynamoDB table and enter items into it to make it more useful. Thanks for watching. In this demonstration, we're going to build out an Amazon DynamoDB table, and then we're going to run a query against it. So let's get started. At the AWS Management Console, we'll go ahead and look for DynamoDB in the search bar. It pops right up. Click. And then I'm presented with the service front page. Now there are some learning opportunities here, but again, we're focusing on creating a table. So I'm going to click Create Table. For our table name, we'll put music. The partition key will be artist. And in this case, I'd like to add a sort key because artists could have more than one song. Typically they do. So let's go ahead and make the sort key song title. Great. Now let's scroll down. We could select the default settings. And as you can see on the screen, it sets it up with really no fuss about performance or any of the other parameters that you would typically have to set. It just gets you up and running. In this case, I'm going to deselect the default settings, and that's so I can show you the different areas that you could configure for DynamoDB. Scrolling down, you'll see that you can add secondary indexes. By the way, if it's a local secondary index, which this would be, this is your one and only opportunity to add it. Read and write capacity mode. We can choose whether we want this provisioned or if we want it placed into that on-demand, which remember is a very forgiving environment for us to run our DynamoDB in. In this case, we're going to stick on the free tier and use provisioned at 5 read and 5 write capacity units. Autoscaling is next. You'll notice that you can autoscale your read and your write, one or the other, or both. And you set this by the total utilization of the read or the write units. Scrolling down further, I have the ability to use a IAM role that already exists, or I can have the Dynamodb service create that for me. Scroll down further and then enable encryption at rest. You can select encryption settings for your Dynamodb, default or KMS. I'm going to just review my settings here. And I'm going to click Create. The table is being created, and it takes anywhere from 1 to 3 minutes on average. Now that the table's been created, I'm going to want to add some items. So let's take a look at the Items tab. I'll click on the Create Item button, and a window appears. This allows me to enter the values for artist and song title. So for artist, I have a favorite artist of mine, and that is John. My favorite song of John's is the Maple Syrup Blues. Okay, I've added my artist and my song, and now you'll see that the item appears. I'm going to add a few other items to the table, and then we'll come back. All right, now that we have all of our items populated in the table, I'm going to run a query. So I'm going to click the pull down. It says scan currently, but don't worry, there's a query under that. We click query, and we're going to set our values to run this on. You notice that the partition key is artist, the sort key is song title. So in this case, I'd like to say that I want to see all the songs written or sung by Evan. I place him in the key for the artist, and I click search because I don't need to enter a specific song title value because he has many songs that he's written or sung. In this case, all my AMIs live in Texas, and S3 Rhapsody are Evan's 2 hits that I have populated in the table. All right, so that was how you build out a Dynamodb table, enter items, and run your first query. Well, that's it for the Dynamodb demonstration. You're going to be able to apply what you've just learned in the exercise that Ricky's put together for you. I'll see you in future topics.
Hi there. I just want to introduce you to the Dynamodb that you're about to do. Now, if I can, I'd like to set your mind at ease first, because many of you may be database wizards, but I would imagine that a lot of you aren't, and might feel a bit daunted when Adam was talking about provision capacity, local secondary indices, sort keys, and compound keys. Please don't worry. You really don't need to know all of that to complete this lab and actually take advantage of serverless Dynamodb. In fact, if you're new to Dynamo, and for purposes of this lab, you could choose to think about Dynamodb more like a tiny little spreadsheet. Bear with me. Try and visualize how simple it could be to look up a temperature by city. One column of unique city names, one column of temperatures. The first column, city, is what you'll query on to get the temperature back. See? The world's simplest Dynamodb data structure. No index in sight. Sorry, Adam. We don't need them. Not for our cat weather app. Seriously though, Dynamo is really powerful. It's used by some of our largest customers and can handle billions of interactions. It can do transactions, auto-scaling, and you can even design really complex schemas and build incredible real-time serverless applications with it. So just because we're using the world's simplest schema for our tiny little cat app, don't think for a second Dynamo isn't legit. It's a professional, enterprise-grade, battle-hardened serverless NoSQL database. It has single-digit millisecond response times. I mean, what do you think Amazon.com runs on? So, I hope you enjoy working with Dynamo in this exercise. Remember, if you get stuck, forums, forums, forums. Oh, and once you have DynamoDB working, we'll simply adjust the Lambda you did in the last exercise to query it, and then check the website to make sure you can get a temperature back. But that's all pretty easy. And I've added a load of notes in the exercise guides for you. Anyway, hope you enjoyed creating your first NoSQL serverless database. Best of luck. Welcome to week 4. Wow, you made it all the way through to the last week. Congrats. We're almost there, the home straight. Now, before I tell you what I have in store for you on your last week, let's reflect on what you've learned and built. We covered DynamoDB, IAM, Cloudfront, how to set up an S3 website, Lambda, and Lex. But what have you actually built? You now should have a working, serverless, data-driven website that solves a critical business need, knowing if it's too cold for your cat. Well, if you think about it, this app has a lot of serverless topics all stitched together. So I think that's pretty cool, considering we haven't had that much time together. So what do I have in store for you now? Well, I'd like to take the user experience to the next level by integrating the conversational functionality of Amazon Lex with your web app. Now, normally, to do something like this, we would need to introduce more services like Amazon Cognito or Amazon Poly, but we're not going to do that. We're going to cheat. We're going to leverage the innate features of a browser to demo a voice user interface on a web page. The idea is that you can hit a button on the website and start talking to Lex. Lex will respond to the browser, and the browser will convert that text back to speech. Cool, right? Remember, there's no code to write. We've written all that part. All you need to do is adjust the backend API gateway to point to a different new Lambda function that allows us to pass messages between the user and Lex. So by integrating Lex and voice in the browser, we turned a basic data-driven weather extraction app into a fun conversational voice chatbot in the browser. Now, is making Lex fully data-driven and truly conversational easy? Not so much. But lucky, we have John, and he's going to spend most of this week discussing how to make Lex smarter, and he's going to use what we call validation hooks. And once he's done, I'll come back and talk about the lab, where you get to build that into your website and have your very own mission-critical business app, Cat Weatherbot. All fully serverless, of course. Anyway, I hope you enjoy this last week's videos and exercises, and I'll see you at the end.
In week 1, I told you about Lex, and we had some fun in the console with a simple book trip bot. There are a few components that I did not discuss during that lecture, and most of it had to do with the Lambda integration. Now that you know about Lambda, it's time to discuss the interaction between Lex and Lambda. Let's take a look at our book trip bot again. It has 2 intents, book car and book hotel. We're going to go on book hotel. When a user enters a utterance, Lex chooses the right intent and then uses prompts to ask questions to the user to fill every slot of the intent so it can be fulfilled. So we can see many slots are at the bottom in here. As I mentioned, in the Lambda integration wasn't discussed. This includes the Lambda initialization and validation as well as the fulfillment. The reason to use Lambda for fulfillment is the same reason as to why you will use Lambda to replace servers. You only pay while your Lambda function is running, and it's serverless, which means you don't need to manage the components behind Lambda, and you can concentrate on your backend code. In this bot example, I will want the Lambda function to include the pricing for the hotel booking and car booking at the fulfillment time. Let's first look at validation though. When the intent is configured to invoke a Lambda function as initialization and validation code hook, Amazon Lex invokes the specified Lambda function on each user input after Amazon Lex understands the intent. If the intent is not clear, Amazon Lex can't invoke the Lambda function. Why would we want a Lambda function invoked for every single utterance or prompts? Validation, of course. But don't we already do validations in the case where we select restrict to slot values and synonyms in a slot type? As an example right here, restrict to slot types. Well, yes, but sometimes we don't control the slot because it's a built-in slot. As you can see the slots down here, the Amazon ones. Let's take the location slot of the book hotel intent as an example. What if we only had hotels in a very specific list of cities? We can't change the Amazon US city slot type to include only the values that we want. It's a built-in slot type. That's where Lambda comes to our rescue. It allows us to extend the capabilities of the bot. Let me show you what happens when I book a hotel in Moscow right now. As you can see, it prompts me back to supply a city. Let's supply Moscow. It continued on. As you can see, this city is accepted. However, what if it wasn't one of the cities we had hotels in? Well, there's no validation here. Of course it will let me go. We will need to fix that. Let's finish this iteration with the bot to refresh your memory of what happens across this entire bot. So in here, what day do you want to check in? I'll answer tomorrow. How many nights will you be staying? 5. And then finally, what type of room would you like? Queen, king, or deluxe? Queen is good for me. I get a confirmation prompt. Okay, I have you down for a 5-night stay in Moscow starting on 2019-02-21. Shall I book the reservation? Yes. And I get back the normal fulfillment that you have seen in the past. To add validation, we first need to create a Lambda function. I will be using a blueprint as the Lex team was nice enough to give us a template for the Lex sample bot that we already used. From the Lambda console, I'll click Create Function. I'll select Blueprints and then search for Lex. I can see that the Lex book trip Python blueprint is in here, and that's the one I will use. I'll click Configure at the bottom of the page, and I'll need to supply a name for it. I'll give it a name like Lex book trip. And then I will have to choose a role for my Lambda function to be able to send logs to Cloudwatch logs. Let's not look at the code yet, though. I'll create the function. Let's go back to the Lex console to modify our bot to send this traffic towards this Lambda function. In the Lex console, I will modify both intents to use this Lambda function for initialization and validation as well as fulfillment. So in the book hotel, I am going to go to the section of Lambda initialization and validation, select that checkbox, select our Lex book trip function, and I'll get this pop-up. That is asking me to allow Lex to call our Lambda function. Else, Lex won't be able to send that request to it. I'll click OK here. Let's do the same with the book car intent as well as the fulfillment in there. I'm starting the build now for my change to take effect. With the power of recording, I will skip ahead for the build to finish. Okay, it's ready for testing. Let's try the same example as earlier. Book a hotel. What city will you be staying in? Moscow. And I get this prompt. We currently do not support Moscow as a valid destination. Can you try a different city? Doesn't seem to want to let me go forward with this city. That is normal, as Lambda is now doing the validation and only allows a specific set of cities where we have hotels. You are welcome to look at the Lambda code if you feel comfortable with Python. It will explain a few things that are in here. However, instead of looking at the code itself, I will explain to you the flow of the data passed back and forth between the client, Lex, and LAMBDA. Let me explain it to you in a diagram now. As you can see in this picture, I have a user on the left-hand side, Lex in the middle, and LAMBDA on the right. The user inputs book a hotel. That is sent as a utterance towards Amazon Lex. Amazon Lex will parse the data and send it as an input JSON to LAMBDA. LAMBDA will do its validation and then return some output JSON statement towards Lex. And Lex will finally send some of that response back towards the user, which will probably prompt for in which city by that point. So the user can now enter Moscow at that time. Now, remember that the first step is the data sent from the client into Lex. So if I roll back a little, I have book a hotel, the data gets sent into Lex. Let me restart this test that I have here by clicking on Clear Chat History. I'll book a hotel. Let's see what is sent into Lex in this case. Because remember, I have the utterance that is now sent into Lex. Let's take a look at that JSON payload. This is the data that is being sent. You can see that there is the client sending a post towards our book trip in the alias latest and for a very specific user. I will come back to this user a little bit later in this lecture. I also can see the input text data, book a hotel. That is what will be sent towards Lex. The next step is for Lex to send that data to LAMBDA and input JSON. Let me switch back towards the input that was sent, and then this is it. A lot of information is here, but let's take a look. The invocation source is set to invocation source, the dialog code hook. This is how the LAMBDA function knows that it's supposed to do validation of the entries and not do fulfillment, as that will be the other option that we will see later. We can see the bot name, book trip, in there in case that this same LAMBDA function was used for more than one bot. The current intent name is pretty important though, because I'm reusing that same LAMBDA function for book hotel and book car. It's currently set to book hotel, which means Lex was able to figure out that we wanted to book a hotel from the text that was sent. That didn't seem that difficult. All of the slot types are currently set to null, as you can see. So LAMBDA doesn't need to do much validation at that point. So to itself, it doesn't really do anything there. However, it will need to send some data back towards Lex. Now that LAMBDA has done that processing, which means that it's essentially nothing this time around, as it's only the initialization, it will send data back to Lex. Let's take a look at it. This is how a response looks like. It needs to be a dialog action type. I will have a dialog action of type delegate. This means, or that directs Amazon Lex to choose the next course of action based on the bot configuration. That next course of action is to prompt for the first slot, which is the city. Right? If we look at our configuration of our bot, we can see that the first slot is the location. So it needs to say, what city will you be staying in? So that data will be sent as a Lex response back towards the user. Let's take a look at what that looks like. What I get is, what city will you be staying in, sent back towards the user, as you saw inside of the console. I'll now go back into my Lex console and write Moscow. Let's go back to our diagram now. What did I just do? Well, I've just sent a prompt into Lex. I just fulfilled the slot. It is the exact same 4 steps that will need to happen again here. Let's take a look at all of those 4 interactions payload, and then we're not going to really come back into this diagram now. So the next section is the client sends Moscow. As you remember, the input text is set to Moscow. Next, Lex needs to send that data into LAMBDA. So the data that is now going to be sent is towards the current intent name book hotel, and then the location is now going to be set to Moscow. LAMBDA can now process the city and validate it against its list of cities where there are available hotels. In this case, Moscow isn't part of it. Here is what LAMBDA sends back. It will say dialog action type of type illicit slot, which informs Lex that the user is expected to provide a slot value in the response. The intent name is specified, book hotel, and the location is now set back to null, as it wasn't valid, and the slot to illicit is now set to location, which is the important one. We now tell Lex which slot to prompt back the user for. However, instead of using a built-in message, we also supply a message to the user. We currently do not support Moscow as a valid destination. Can you try a different city? That is what will be sent towards the user. That data is now sent back to the client. Here's what Lex sent. We currently do not support Moscow as a valid destination. Can you please try a different city? This time around, the client is ready to choose a different city. Let me pick another one, Chicago. Oh, it seems it let me through. Let's go and take a look what happened there. The client sent Chicago. Input text, Chicago. Lex sends the data into LAMBDA. This time around, current intent, name book hotel, and in the location, Chicago. Nothing really has changed in this case. Now LAMBDA will need to validate this city. Chicago is a city where we have a hotel, so this passes the validation. This is what LAMBDA replies. Dialog action type, delegate. A delegate type as we want Lex to continue its processing to the next slot. As you can see, Lex is now asking for the check-in date. What day do you want to check in? Yes, it's the next one in the order. If you remember well, I have the location, and then the number 2 is check-in date. So that's why it used that prompt. We've now seen how validation works between Lex and LAMBDA. In our next video, I'll go over how to do fulfillment with LAMBDA and the usage of session attributes. I'll see you there. In our previous lecture, we used LAMBDA to validate slot values. I will continue from that example to discuss fulfillment and session attributes. I'll start by interacting with the bot and fill all of the slots this time. Book a hotel. What city will you be staying in? I will select Chicago. What day do you want to check in? Tomorrow. How many nights will you be staying? 5 nights. What type of room will you like? Queen, king, or deluxe? Queen. I'm now getting a prompt confirmation, but something has changed here from the time where we didn't have LAMBDA integrated. If you look, a price is provided for this hotel. Don't worry though, it's just a generated price randomly. It's not that expensive to stay in Chicago. Well, I hope not. To understand how this happened, you will need to understand another concept called session attributes. They contain application-specific information that is passed between a bot and the client application during a session. Amazon Lex passes session attributes to all LAMBDA functions configured for a bot. If a LAMBDA function adds or updates session attributes, Amazon Lex passes the new information back to the client application. Session attributes can also be used to add more information in the prompts to the user, as you can see it here. How long are those sessions being kept? Well, if we go under the settings of our bot, under General, you will find the session timeout here. We can see that it's currently set to 10 minutes. You may also be wondering what constitutes a user to Lex. Well, when a request is sent to Lex, a user ID is also passed, and that's what Lex will use as its key to associate all of the session's attributes until the timeout is reached. Your application is responsible for generating it. When testing with the management console, it is generated automatically for you. That's why we never had to worry about it. Back to our interaction with the bot, we just sent the last piece of information to Lex. That was the last slot to fill, which looks like the following. As you can see, it is a post for Queen as my bed, but you can also see the user ID right here. That's what I meant by the user IDs being sent into Lex. Lex then sends that information to LAMBDA. The LAMBDA function will need to realize that all of the slots have been filled, as you can see it right here. And it will need to use a session attribute called current reservation price, it's up to the LAMBDA function to decide that, to store the price of the hotel. LAMBDA will send back that data to Lex as you can see it. It uses the delegate function to let Lex continue with its processing, provides all of the slots again. But there's something a little bit different here. The session attribute is currently set to current reservation price $1,195, which is what we saw in our prompt. Let's take a look at the prompt that will be using this information here. Back into our editor, I will go towards the confirmation prompt. Clicking on the little gear icon, I can see the price of this night, amount of night stay in the location from check-in date is square bracket current reservation price. As you can see, there's two prompts. One of them makes use of those square brackets referring to that current reservation price. This is the way to invoke session attributes within a prompt. The client can now confirm that the entry is correct at that point. So I will type yes here. The input data for this is going to look like the following. As you can see it, input text equal yes. This time, Lex will invoke the LAMBDA function with a different invocation source. As you can see it here, invocation source, fulfillment code hook. That is how LAMBDA knows that it's supposed to fulfill this. It can use all of the slots data to do the booking in the backend system. LAMBDA will need to send one last dialog action back, and that is of type close, with the fulfillment state set to fulfilled. A message can also be supplied, or the response section of the bot will be utilized. In this case, we use the message. Lex will send that message back to the user, and then now our interaction with our bot is now finished. However, the session is still alive. It's set to 10 minutes. And if the user wanted to continue booking a car, there are some slots that are already filled from our previous interaction with the bot during our book hotel. Let's test that out. Let me book a car. As you can see, it asked me a question. Is this car rental for your 5-night stay in Chicago around that date? It found that information. If I look at the summary, it even figured out the pickup city Chicago, and it figured out my pickup date and my return date and did the math for me. This is done using the LAMBDA function and the session attributes that can be passed between all of the different intents. I'm inviting you to explore the code to see how this was done if you're familiar with Python. Soon, you'll put to use everything you have learned about Lex into an exercise. Thanks for watching. If you want to extend your bot further, let's see how I can integrate different channels with my Lex bot. This is done using the LAMBDA function and the session attributes. I'm inviting you to explore the code to see how this was done if you have the time and if you want to read some Python code. Now that I have a bot that is fully tested, I can publish it and show you the channels tab. On top of easily integrating Lex in the web UI like you will do in the next exercise, or in your mobile application via the AWS Mobile SDK, you can integrate your bot with Facebook Messenger, Kik, Slack, and Twilio SMS. Let's see how to do that with Facebook Messenger. First, we need a name. I'll input serverless chatbot. Then, I need to fill which alias I want to associate to my Facebook page. I'll use prod that we've created before. Then, I need to select which key management service key I want to use to encrypt all of the data that I will use below. I'm going to leave it as AWS Lex. I need to input a verified token that I will use and reuse it, in fact, on the Facebook developer portal. I'm going to use the very secure token. It's a very secure token. For the other two parameters, I need to go on Facebook to get those. First, I will create a Facebook page. I hit the Create button and select Page. I will use community or public figure by clicking the Get Started button. My page is going to be called Serverless Chatbot, and then the category is going to be Just for Fun. And I will click Continue. I'll skip the next two steps out here because I don't really need that here. Now that I have a page, I will need to jump over to the developer portal of Facebook, a little bit different website. In here, where I'm already logged in, I'll create a brand new application by clicking on the My Apps menu at the top and clicking Add New App. For the display name, I'm going to use Serverless Chatbot. They don't need to match, but it's all right. I'm going to make them match. I'll click Create App ID. I'll confirm that I am not a robot, and I'll click Submit. Going under the settings, under Basic, I am going to find my app secret. I'll need to click that Show button right here to display it. I'll take this app secret, go back to Amazon Lex, and enter it as my app secret input here. Next, I'll go back to my developer portal in Facebook. I will go under the products page and I will add Messenger, and I'll set up Messenger here. I'll go under the token generation and I'll select the Facebook page that I created called Serverless Chatbot. I'll continue as myself. Now, this gives me a page access token that I'll copy and paste back onto my Lex console. I now have all of the data that I need to create my channel in Lex. So let's activate it. I will get an endpoint URL. I will copy this endpoint URL that I will then use a little bit later. So, still under the developer portal, under the setting of Messenger, I'll go under webhooks. I'll click the Setup Webhooks button, where I will input this endpoint URL that I have just copied from the Lex endpoint. Then I need my verified token. If you remember, that was the very secure token. Then I need to specify subscription fields. Those are messages, messaging postbacks, and messaging opt-ins. I'll click Verify and Save, and it seems like it worked. The next step is to subscribe under my webhooks, subscribe my serverless chatbot page to this application that I have right here. So now that it's subscribed, it's time to test the chatbot via Facebook Messenger. In my Facebook page, I will add a button by clicking the Add button. I'll select Contact You, send a message, click Next, select Messenger, and hit Finish. Now, this Send Message button allows us to send a message to the chatbot. I'll test it out, so putting my cursor on top of Send Message and clicking the Test button. My chatbot is now available via my Facebook page. So let's do a quick chat. Book a hotel. What city will you be staying in? Huh, that sounds familiar. It looks like I'm interacting from Facebook this time all the way back to our bot. Exactly, that's how channels work. It's an integration between a few different components, Facebook, Twilio, SMS, Kik, and Slack towards your bot. Soon, you'll put to use everything you have learned about Lex into an exercise. Thanks for watching.
John has covered a lot of ground with Lex, which is awesome. So now we can leverage that information to help take our website to the next level. Firstly, we want to make our Lex bot smarter. Because currently, if we ask our chatbot, can my cat go outside in banana? It's going to say, you want to know if your cat can go outside in banana? Got it. Far from ideal, right? Well, by creating a LAMBDA validation hook that John talked about, we can make Lex query Dynamodb directly and get temperature information back. And if for some reason it doesn't understand the city, well, it'll just prompt them for a different location. What you'll notice after implementing this validation hook is that the very basic chatbot you created in the Lex console in week 1 suddenly will become a lot more lifelike because it's actually making decisions during each conversational interaction. Now, it's all well and good having a smarter chatbot, but how are we going to publish it and help other cat owners around the world solve such pressing problems? We can't just keep using the Lex console for this, as that's only for developing. We could have considered wiring this up for Alexa because it's the same engine and that would have been a relatively easy export. We could have gone with what John showed you, one of the Lex channels like Facebook or Slack. The challenge there though is that's just text. And I wanted to have all of you create a voice-enabled one. So for this lab, we're going to build a web-based, voice-enabled user interface for Lex using JavaScript. We could have used Amazon Polly and Amazon Cognito for some of this, but we really want to save those services for another course. Instead, we're going to cheat, and we're going to use a browser to convert speech to text and text to speech, and simply proxy the message back and forth to Lex via API Gateway. It will feel like you're having a natural conversation with your browser. And don't forget, you'll need to provide all the right permissions for both this proxy function and the LAMBDA validation hook. Fear not, all of that information is in the exercise notes. After we build our LAMBDA proxy and mimic Lex payloads with test cases, we can go over to the website and ensure that we can hold down a, should we say, conversation with Lex via the browser. Then at last, we will establish if our cat can go out or not. So to recap, number 1, we're going to create the validation hook and set your permissions. 2, you're going to create a LAMBDA proxy behind API Gateway, set its permissions and test it in the console. And finally 3, you're going to go over to the web-based voice-enabled application in the browser and test it. All the code is written for you. All you need to do is follow the exercise instructions. Now, as a final thought, I wouldn't trust Lex to know if I should let my cat out or not, as we're not using real data, we're using random temperatures in the database. If you want to know how to work with Amazon Dynamodb and real-time data, well, that's something we can look at in a different course. So, off you go. Best of luck with your final exercise. And if you do get stuck, where'd you go? That's right, the forums. Have fun. Wow, you made it. You got your cat weather app working, right? Awesome. So I'm hoping at this point, you can think about how you can take what you've learned into the real world. Now, even if you don't use all the products in this course, we've covered enough bases in the time we've had together for you to get some use out of this. There are a lot of people that go into making a course like this, So I'd like to acknowledge that and thank everyone for helping make this course a reality. Don't worry, I'm not going to do an Oscars speech and thank everyone by name. You guys know who you are. Thanks. So where do you go from here though? Well, I'm going to ask you to refer to the course notes because that's the best source of up-to-date information. That will tell you about getting access to resources and provide links to more sources of information. We're preparing new courses all the time, and each time we produce a new course, we learn something new just by going through the process. But we're always looking for ways to make it better for you guys. So if you have suggestions, ideas, or even criticism or compliments, or if you just want to say hi, bring it on. Dive into the forums. We are listeners, and our goal is to provide the best learning experience we possibly can. So, I'll let you guys go now. Keep an eye out for our upcoming courses, and I look forward to seeing you again. Thanks. Bye, y'all.